looks something like this. And he's the founder of Digital Sutra, which is a company that helps roofers to get clients by digital door knocking. Now, Pulkit decided to work with us on 31st January 2019, back when he was only making 37,000 rupees per month, with the target of making 1.5 to 2 lakhs. So Pulkit was doing a job as an IT employee, and he wanted to create something where he could work remotely without getting stuck in traffic jam in India. He tried different kind of things like drop shipping, SMMA, and even Googling 499 courses on how to become Ambani. But unfortunately, none of that worked out. To achieve his goals, Pulkit decided to give one last shot by booking a call with us. On the call, we revealed to Pulkit that there are a lot of business owners out there which may require his services like websites, social media marketing.
Check, check. Check, check.
ಬೆಳಿಗ್ಗೆ ಸರಿ ಟೆಸ್ಟ್ 1 2 ಅವ್ರಿಗೆ ಬರ್ತಾ ಇದೆಯಾ
Hello, check, mic, check. Hello, 1, 2, 3. Hello, hello, check. Hello, hello, hello. Hello, check, mic, check. Hello, 1, 2, 3. Hello.
Good morning to all. Yeah. So welcome to the second day of the third international conference on public key infrastructure and its applications. So before I start for the sessions of the day, I request Dr. S.D. Sudarshan, Executive Director, C-DAC Bangalore, to the stage, and I request him to introduce the speaker. Welcome.
Namaste. Welcome to day 2 of the PKIA 2022 conference. It's a pleasure to have all of you here. And the weather has held beautifully. Bangalore is known for its good weather, and it has held up very nicely. And thanks for being on time. And today, actually, we are starting the day with something that is challenging across in general. That is, what does the industry practice? What does the policy and regulators communicate? And what does the standards want and academia tells? So the triad, how they are connected, or they remain that many degrees away from each other. That is simply a challenge between various sectors, various domains, TRL levels, and the fundamental purpose of doing that work. Somebody does it because I am a scientist. Somebody does it because I need a technology. I want to demonstrate my ability. Somebody does, it's a profit-making company. Somebody does it for a social welfare cause. So that creates a dichotomy in several places. In this case, the digital signature technology, PKIA is back, is actually gone through ages now. And today we are happy that we have someone from an industry demonstrating use of digital signatures in actual industry, that is both particularly OT, operational technologies, which is considered very challenging, integrated with IT at a higher level, so the digital industry can evolve. So in that direction, if I recall, we did have a couple of technical expo and some closed door meetings with select participants last 2 days. One of the key things that came from the certificate authorities, who are actually people issuing certificates, sub-CS as they call them, they brought out this point that other than certain, let's say, regulated and state-owned websites and certain transactions that are mandated by federal agencies, followed by federal institutes or that are regulated, they are the only ones who are actually adopting these digital signatures. Others have not taken it on board. That was a concern, because unless there is a widespread adoption, there will be less need for interoperability across borders. And then we may not be able to realize a truly digital, transparent world where everyone can best available best across the globe. That the global village concept, to evolve that, it was needed. So that is where I think today we have at least one specific use case where we have Mr. Sukumara. He is actually having more than 25 years of experience in R&D. And he is leading Cyber Defense Evaluation Cell Center at ABB, Global Industries and Private Limited. And he is also the global cyber security manager for complete electrification across ABB entire globe. So I'm very happy to welcome Mr. Sukumara on stage, who will actually, please sir, my pleasure, good to have you here. Yeah. So just to give a couple of more small things, that is what he says, but to me they are big things. In spite of being in core industry, he has a number of publications, and he routinely presents in SIGRE kind of events, where the top of the industry and academicians and others meet when it comes to SCADA and electrical related security, electrification, whatever you call it. So he is very active in those areas, and he also has an MBA, so he knows what business is from a theoretical perspective as well, in spite of being an engineer. And he has a passion to groom youngsters. I know he does take a lot of interns so that they get industry exposed. That is a very good thing he does. And my privilege has been, I'm also associated with him in one of my earlier avatars. So I have a couple of publications with him, at least a couple of filed patents with him. So that way we share. I know a little bit of him, more than a normal outsider. So we are happy to have you, sir. And he is going to probably walk us through how they are using digital signature, not just for site certification and all, but even for embedded systems, OT environment. How do you can even authenticate? We always talk about a kind of hash kind of thing when it comes to integrity of a system software or anything. We just get some number or what is. He is trying to use digital signature even for those kind of applications. So it will be a very interesting session. So I'm very keen and looking forward and want to learn from you once again. It's an opportunity. Thanks for joining. I hand over the stage back to him. Please enjoy the tutorial for the day. Thank you.
Thank you. Thank you, Sudarshan sir. Thank you for the nice introduction. Good morning, all. I'm not that as from the OT world, we know how to use the PKI, how the deployment of PKI and into the field, what challenges we face in the OT domains. Can you just speak that? Yeah. Hello. Yeah. I mean, okay. Sorry. So how the OT world sees this PKI infrastructure? Hello. Yeah. So the adaptation challenges with respect to OT systems and the international standards, what they talk about the the cybersecurity. Yeah. What the international standards which talks about on OT systems, the compliance perspective. What are the challenges and how we adopt the solutions? So the interoperability and the standards and the compliances, and then the seamless adaptation of the certification into the secure communication between the systems. So this is what our experiences while implementing these things and as a part of R&D and into the deployment under the field. So that's the experience that I would like to share and today's presentation. Yeah, thank you, sir, for a nice introduction already. So yeah, this is in a typical small agenda that what we have this our today's my session. So what the standards in the OT domain and what are different standards in the actively being looked into, and how this the seamless integration of the certificate support in our OT products, and what are different aspects other than secure communication and digital signatures, how we adapt into our products and systems, in especially in the OT. So as we all know that OT systems is a part of a critical infrastructure for us, right? So everywhere we have an OT system, there are millions of IoT devices and the traditional OT devices already in the field. The beat and a power and electrical, the electricity generation, transmission and distribution, and energy storage systems, and the nuclear power plants, oil and gas, the railway networks, the aviations. So everywhere you have millions of OT devices already in the on the field, and they are not there today. So they are there from last 40-50 years. Once this communication capability has adapted into this into the OT world, the basic SCADA system started with all the protocols like Modbus, DNP protocol, I650, a lot of protocols which brought us an interoperability between the different vendor systems. So there are so many vendors are there: Siemens, Honeywell, ABB, Schneider. There's so many the companies which are deploying a critical infrastructure projects across the world. So and this critical infrastructure under the tremendous the pressure or what do you say to protect this infrastructure from the security incidents or the hacking attempts. So how we defend our architecture of our product and systems and with the perceived attacks. There are various incidents already shown that not only the amateur hackers or even the state-sponsored the hackers are getting into the system, trying to get in system and disturb the and the power systems or the critical infrastructure systems. So this is a typical an Indian power map. You can say the energy transmission distribution. It's basically a transmission. You can see how the transmission lines all over India. So we're talking about around 400,000 megawatt capacity in India. So both non-conventional and conventional energy. And we have around 300,000 circuit kilometers of the only I'm talking about transmission, high transmission, the EHV transmission, 725 kV, 400 kV, 220 kV. So we have around 50,000, more than 50,000 electronic devices. We call protection relays or IEDs, controllers, gateways. This protecting this protecting this infrastructure. So the many of systems are still electrostatic, or with some basic communication from the first level intelligence from the primary system to the first level intelligence, then to the SCADA system, then to the control centers. The whole chain should work seamlessly. So the focus was on to make the system interoperable and work seamlessly, to make it operation, to optimize the performance. But now the focus is shifting towards cybersecurity, how to protect this infrastructure. So there is a burden on the system, because already this the core embedded systems or OT products already they perform their core operation. These are protection algorithms or the operation related logics are implementing. Now the security aspects and add on to that the communication infrastructure, the Ethernet communication. There are so many protocols to implement, to communicate with the transfer the data, and on top of it, now the cybersecurity architecture is coming to the picture. So the electrical, the grid or infrastructure, not only in India, all over the world, it is aging. So almost like the US or Europe, the electrical infrastructure is almost 60-70 years old. Unfortunately, in India, we have developing last 20-30 years. We already started with an intelligent electronic devices which has the communication capability, but we didn't foresee the security aspects that time. But when we started adapting to the security implementation, we saw that there's a tremendous pressure on the device architecture, because yeah. So the merging of IT and OT infrastructure, as Dr. Sudarshan nicely put it. So we have a CIA triad: the confidentiality, integrity, and availability. So for IT systems, confidentiality is a core of the system. In the priority, high priority, then next comes that integrity and availability. Whereas for the OT systems, and availability becomes a primary objective, because see, when there's a power transmission, when the power trips, or in the power plant, when the power due to overload or due to fault, So you're supposed to operate the system in 10 milliseconds, detect the fault and trip the line, protect the grid from the rest of the faulty system. So the devices which is on the field are deployed, they're supposed to use is continuously monitoring the power signal, the fault cases in that. So that system supposed to perform this core operation, whether the communication architecture is working or not, if the data is going to the control center or not. The communication comes the secondary aspect, but core operation is to monitor the primary system, the power system, and take the action. So that's why the availability is very, very crucial for an OT system. Of course, the confidential integrity is the coming as a along with availability, but we perceived that in the beginning to 15-20 years, okay, we have an air gap system, so our the networks are isolated from the internet, public facing networks, but it is not really true. So we have seen the recent incidents in Ukraine attack, or the worldwide many attacks in the US and the water treatment plants, or in the oil and gas network. So we saw that that the people, the hackers, able to get into their IT network. From there, they're getting into the OT network. So the systems are not fully air gap systems. So there are systems which are already directly or indirectly connected to the OT, and so the challenge is how to build a defense in depth architecture. Okay, build a multiple layers of defense, and so that we able to protect the operations, the critical infrastructure projects from the IT hacks, right? So if you today, anybody, if you see this simple, there are search engines. This is one of the search engines called Shodan.io. Simply, if you put in a Modbus or DNP or I690 protocol, you can see there are thousands of devices, public-facing devices. You can see which are facing to the public internet. Okay, so this search engine crawls into the network, and it try to find out all the OT devices, predominantly OT devices, which is supporting the common protocol like FTP, HTTPS, DNP, Modbus. So just checks those devices. And try to access with some basic default password, username, admin, password 1234. So there are still this kind of password, username still there in the OT the products systems. So just using that password, they're able to get into the OT the products. So you can imagine if they're able to control that OT product, and in turn they can control the one power grid. So if they're able to trip the one line or one nuclear power plant, how much havoc can create into the system. The Stuxnet, we have seen that the state-sponsored hackers are able to get into the OT system via their IT network. So there is no one layer or one security solutions enough for us to think of. You should build a multi-layer of defense, so that it is making it a little difficult for the hackers getting into the primary system of the OT world. So a recent one of the study report given, if you see a simple search of the protocol called Modbus or BACnet or DNP3, even US, South Korea, France, there are more than 30,000 devices publicly exposed. You can penetrate, this Modbus protocol, DNP protocols, all these are not secured at all. They are basic communication protocols. The Ethernet-based protocols, they carry data. They don't have any the security layer built on top of the protocol layer. They're simple, still text protocols. Of course, they started as the basic serial protocols, RS-232, RS-485. Slowly, they evolved into the TCP/IP based protocols, but still security is not in place, because for the vendors or the customer, the interoperability is very key. For us, okay, you are giving me a new device with a lot of security. What happens to my existing system? How I can integrate these two? These are the questions they're asking us, customers. So they expect our OT infrastructure to provide a support of 20 to 25 years of life cycle. So which is these days, with the fast moving technology, the processor architecture, so it is compared to other domains like consumer electronics or be it and defense. So the technology is getting changed very fast. So when we are giving in, expecting, there are substations, there are power stations, they built almost 40 years back, still they're running. Okay. So of course, there are electrostatic, electromechanical systems still on the field, but there are systems which are kind of a basic text protocol still working worldwide to monitoring or controlling or protecting the critical infrastructure. So this gives us where we are today and how vulnerable we are across the world. I'm not talking about even Europe or US or India, everywhere. So there are, maybe this is because of the product designer, developer, vendors, the big vendors which are developing the systems, and the customers who are operators who are operating these systems. They are not much familiar with the security concepts. Though the security concept will be there, they keep it at a default state. So they're not updating, they're not configuring properly the security. So we are such a level. So one side we are talking about the high-end PKI infrastructure and secure communication, quantum cryptography. But on the field, if you see, we are just quite behind the people, the primary people who are operating the systems on the field. They don't know how to configure the system, how to maintain the system, how to protect the system. So they left that intelligent device the same as like we have a lot of people, we have smartphones and we have hundreds of features, but hardly we are using 10 features, right? So this security feature is just one of the features in the product, but they left it to the factory default state without enabling or configuring, making it a complex, the right configuration, that those systems become vulnerable. So this is the one recent the evil PLC attack. This is how we can one can attack into the OT systems, making the PLCs and controllers gateways into they themselves become a kind of a rogue systems which can attack into the into the primary systems. So as I told you, so once the hackers come to know, okay, there are products or systems publicly exposed, then using that those protocols, they're pushing the malwares, ransomwares into the primary systems, the OT devices. From OT devices, they're getting into the engineering stations. From there, and commission engineering laptop. Then once it goes to engineering station, then it is go to entire plant or even entire grid. So this is how they are able to penetrate into the critical infrastructure, and they can create an havoc. Okay, so this study, the Clarion company has done it, and they were saying not just one vendor or one product developer, all across the companies who are developing these OT products, their systems are vulnerable. So that they are able to provide us information. Of course, they, as soon as they found information, they informed to the OT vendors, the product developers. Then they fix the issues. Then only after that only they publish this article. But see, today our OT products highly vulnerable, how highly scrutinized. The researchers, universities, or the hacking companies, everybody trying to buy the system and see what loopholes in the OT products. Look, so and they're reporting, yes, I found some vulnerability in your product. So for the companies, it's becoming a challenge. Like say, for example, red teaming and blue teaming, right? So as a product vendors, we are R&D, we are as a blue team, we are defending the architectures and we defending the whereas it is easy for hacking people to find the vulnerability in the product, right? It is a constant challenges. So when we are say, for example, an R&D team designed the product and deployed in the market, maybe this 10 years old, suddenly there is new vulnerability reported on the device. So the deploying and patch onto the product which is on the field, it's very complex. Unlike in mobile, if you say, okay, they're given a patch within 2 minutes, they will enforce update this patch. So otherwise, simply the mobile will say not operate. So then immediately you do update the patch and reboot your mobile. But rebooting or update the patches and rebooting the device is not so easy. If the OT product is on the field on monitoring the centrifugal pump in the nuclear power plant or the crucial substation, 400 kV substation, or generating plant, it is a controlling. Nobody want to take the patch update seriously because they don't know disturb the system. The plant shutdown is they have a target to reach a 98% availability. They have to meet the target. They don't want to give us a commissioning the time for patch updates. So that much of complexity is there, and with this, the patching update has become so frequent. We know that Microsoft every month he releases second Tuesday or something. Every month he releases a patches. He thinks so easy to deploy, but deploying the one patch onto the OT product is a quite complex. Yeah, that are challenges the OT product vendors are facing today. Yeah, so one is okay, you are making the product, the architecture robust enough to withstand this the cybersecurity attacks, and the building the system around it, right? It could be a physical security and electronic perimeter security, and then the implement a proper authentication with Active Directory, whatever. So like you are logging into the laptop and you connect it to the Active Directory server and validates authentication. We have to take that into the a small sensors which is monitoring a transformer, oil temperatures, or motor start stop sensor, the smart sensor. So you want to bring that and activation or authentication into that level. How difficult it is, but because you don't have a keyboard or you don't have a mouse or to operate the device, it doesn't have any user interfaces to write username passwords, right? So this is challenges when we have this kind of medium and low end, the smart IoT devices, or it is an OT devices on the field, where you need to log in and do some configuration and change the parameters, read and write the parameters, right? So we recommend usually to the vendors, okay, you build a system. So you make it kind of a multi-layer security layer. So, and you protect this, the external communication with your proper firewall or IDS systems. But here at individual product level also, you should see, okay, if somebody able to penetrate your firewalls or IDS systems, getting into OT products, how you defend your architecture. So how you detect this is an hacking attempt. So what are the procedures? How you find it is in a DNS attack or the fuzzing attack. So and detect and see, ensure that any DNS attacks are not affecting the core operation of your OT device, right? So that is a challenge we always face as R&D team. Yeah, the OT device, security device architecture. If you see OT device, like I said, it is a dedicated the embedded computing system or product, you can say, which is performing the core operation. There are thousands of protection algorithms which is actively monitoring a transformer protection, or be it a transmission protection, or be it a nuclear plant protections. So they have an algorithm to run, which is very intensive. Your analog current and voltage signals are coming at 50 hertz per second. You sampling at 1 kilohertz, 4 kilohertz, and then you measure the analog sample, convert it digital, and measure identify the fault, and then take an action and trip that particular faulty product or transmission from the rest of the grid, which has to happen in 20 milliseconds. So for example, 50 hertz a power cycle, which is a 20 millisecond per cycle. So you have to trip the breaker or protect the power system in the 10 milliseconds when the zero crossing is there. So that is a core operation of any device. Now the communication is ADAC. So it has to communicate with the control center, and it has communication with the SCADA systems. When the cyber attack happens onto the OT device, it needs the system resources. It takes over the CPU processing power. It takes the runtime memory. So then the trade-off between, is it the core operation is important, or it is a communication security is important. So that's where how you prioritize tasks, how you ensure that your the attack onto the OT device is still not affecting the core operations. How you segregate, how you build your architecture, the embedded architecture to handle this kind of attack when still the device performs the core operation. So that's how we constantly look into it, and we scrutinize our products into that, create that attack scenarios and see how the OT product is able to withstand. So different the OT standards predominantly providing us any guidelines or the compliance requirements. This is an IEEE standards, or it's NIST standards, ISO standards. and the NERC standards, and every country is coming up. Every country is that there is an regulatory committees. They are bringing up the guidelines, the trusted vendor concept, supply chain security. Yeah. So the SCADA interoperability, then the cyber security. So authentication, the encryption, the secure communication. There's so many requirements. So for us, the challenge is to meet this the standards, the compliance requirement, get product certified, and then at the same time the seamless integration to the system, to have the effective communication, the transfer data to for the effective the monitoring and control of the grids or the critical. So this is the challenge. So the predominantly we see this 62443 is quite popular and across the world. It is started as a simple ICS, industrial control system standard, but today this standard is being adopted almost all critical infrastructure domains, be it in energy storage systems or be it in oil and gas, water treatment plants, the aviation, railways. Everybody wants they want this compliance to 62443 standard. This is a vast standard. It covers all the aspects of system security, product security, everything, and standardization requirement, the testing, certification. Yeah. This is the 62443 kind of the number of parts we are talking about. There are so many the standard parts. So predominantly we see the 3-X, which is called of system security. When you build a system, the critical infrastructure system, how you protect the system. And there is a different layers of there is a process IO layer, field device layer, and this control network layer, then the enterprise network layer. So how you build the system, how you secure the system as a network architecture. Then the 4-X, this part called individual product level security requirements. How you implement authentication, how you implement your secure communication, how you implement your trusted vendor, the code signature patching practices, all those requirements which is coming under 4-2, the 4-1 and 4-2. So this is the compliance, the standard compliance which always we try to adapt. And sometimes what happens, these standards will, okay, this is a requirement. Okay, then how you'll implement it, that may not be that clear, but that we need to see how we practically implement these standards expectations. Yeah, so this is a typical, for example, you can take a substation or it's a kind of the thermal plant or hydro plant. So where we have this different network layer, so FD and the bottom layer, field IO layer, and this is the second layer is the process control layer. Then third one is the demilitarized zone, and fourth is the enterprise network. So where the IT system come into picture. So we talk about a firewall in between different layers, and we have IDS systems, and yeah, in between we have a wireless connectivity. You connect to the wireless modems, or you connect to the remote stations. So how you safely create a kind of a secure conduits into the different layers, so that you have you are able to validate the information before getting into the primary system. Yeah, so here we know as I mentioned, so there are the product suppliers standard requirement and the system integrators and this asset owners. So these systems, the different the parts, the product is product supplier layer, where you have embedded devices, you have a network components, where your switches, host devices, your applications running on this product level, and the system level, where the third-party integrators who takes the products and builds into the system for the customer, and asset owner, the end operator or customer, an oil and gas plant, an operator, so who owns asset and regularly maintains assets. So what is his requirement from the cybersecurity perspective? So just how this PKI system being referred in this standard. So the challenge what they're talking about, how we secure our communications between the devices to the control centers or to the SCADA systems. So the 62443 standard, when you devise an OT product and embedded controllers, gateways, RTUs, protection relays, so we look into standards. They talk about, yes, you should be able to support the PKI infrastructure. So your certificate must be signed by PKI. Okay, correct. Okay, fine. So what are challenges there? Our devices are directly connected to PKI every time? It's not possible. So all devices are not directly facing the public access to the CA system. So what are the fallback options we have? So that is something which we need to think of. Every customer or every small operator in small and the kind of paper and pulp industry or in a kind of an the small and steel factory. So they may not have a connection to the 24/7 PKI infrastructure. So how you support that kind of a small industries and your products should be still able to provide some basic protection. Yeah. So then comes up the size. So what should be the PKI size? What is your symmetrical key size? What should be your RSA key size? Is it 1024, 2048, or 4096? Is it enough? What standard says how the IT world is moving? So whether your system can take, because the system has to communicate with the multiple masters or the clients. So every one particular device is communicating the local maintenance system, the local engineering station, local operating station, then remote control center. It is establishing a parallel sessions, and every session has a TLS handshake, and every session has a security the certificate check. How much it takes a system. So what is the impact on the performance of the device? So so that is a challenge. So that is we kind of a design engineers will face. Okay, well, what the system is capable of and how much that can impact on the operational performance of the device. This is 16235 standard. This is mainly, as I mentioned, is a power system management standards. So this is the standard mainly followed in the electricity, the power and energy automation project. So this has a more detailed implementation methods. They have proposals like how we implement. So especially the part 9, it talks about cybersecurity key management, how you manage your keys, how you manage your certification, how you manage your signatures. So this is what we would like to, we usually refer. Okay, what is the compliance requirement? So this is one of the chapter talks about certificate handling. So how you there are three scenarios. One is a product vendor who's manufacturing the product, and it goes to the system owner and the device itself. So the system owner is the end, the customer, and who's installing the system in oil and gas plant or a substation. So how the certificate is created, how the certificate is installed in the device, and the lifetime of the certificate, and how the device should take the certificate and use it for its communication, right? So these are the production, can then registration, commissioning, enrollment, and renewal. So all these stages where the vendor comes into picture, where the system integrator comes into picture, and where the customer is coming to picture. So what his responsibilities? So most of the times what happens, OT product, off the shelf product. So we have a production relay, we have a gateway, we have a controller. So most of the times the companies are not the one who goes and integrate into the system. In oil and gas commissioning is taken over by done by some company who is basically system integrator. He takes the product from multiple vendors. So he integrates and makes a system with his own engineering stations and commissioning systems. So multi-vendor device. So when we develop a product and deploy the product, we give the product to the system integrator. System integrator purchase a product from us. So what should be the factory default configuration? Okay. So because we don't know, because we are not the owner of the certificate, so we don't know which certificate the customer wants to finally put into the product. So it is up to them. If he has a customer has his own PKI system, for example, Bescom is a Bangalore electricity supply company. If he is commissioning 133 kV substation or 132 kV substation, so he may have his own PKI system. He wants his certificate to be there in the product, right? So we can, when we produce a product in the factory, so okay, by default the product will go in the self-sign certificate. Okay, so if there is no certificate inside the device, okay, we update the firmware and we start the first time. Okay, the firmware should check. Okay, there is no certificate. What happens if the customer doesn't have any certificate PKI infrastructure, or he don't have an connectivity to the PKI system? At least we should have one self-sign certificate. Okay, as soon as the device boots up, it says the first time it checks. Okay, there is no certificate inside. Okay, let us create one self-sign certificate. As I told, the life cycle of the product is being expected minimum 15 to 20 years of life cycle, be it in aviation or be it in railways or any product we sell. The customer expect, okay, how much support you can get it next 20 years? Can I use this system? So that is the expectation set by the expected by the customer. So whether the certificate, we should keep the 20 years of validity, and whatever the key we use, 1024 bits or 2048, is it enough after 5 years? We don't know, right? So that's the kind of a constraint we face during design stage. But usually we put that self-sign certificate as a factory default. Then the customer is able to upload his own certificate. Then it should be able to take that new certificate. So that's how we plan that in a part of as a part of design. As second is the manual external certificate. So okay, the customer has a certificate. You want to deploy that onto each and every OT device in the field. Okay, so we have an engineering tool, and you generate a certificate and trust a certificate from a CA. Take it to the using the engineering tool. Just you deploy into the device, and in the device we ensure that we need to keep it in a safe and secure location, which is not so easily accessible by the any other SCADA protocols. So that option we should have it. Then the third is automatic exchange of a certificate, which is it should have a connectivity to the PKI, which is that there is a possibility for that OT device has a direct connection to PKI. Okay, then the device can generate its own keys and send a public key as a CSR signing request and send it to the CA, and CA signs it and sends it back, and we store it in the device. So we should have all these three options to be given the customer based on his infrastructure. Whether if a small operator is a big operator, how much infrastructure he has, he should be able to use this system or product into his system. So if the customer doesn't have his own PKI system, okay, he can live with the self-sign certificate, yes, but engineering is a complex. So you know who's your client systems, your HMIs or your control center maintenance engineers. Okay, you take the science leave certificate and you do the pre-install so that okay, your HMI systems can only recognize only that pre-installed certificate. So that is a constraint, but still it should work as a basic defense. So the manual certificate update, where you have a different tool, you have your local CA or your public CA. So you take the CA and you generate a certificate and you bundle it PKCS 12 and transfer it securely to your engineering tool. From there engineering tool you deploy onto your OT device. So this option also will help how securely we generate certificate and we store into the device. And of course, as we all know, this is automatic certificate exchange, which is quite predominant, popular, means regularly being used. So how the OT device should implement these features with minimal resources. The four steps, like okay, you request certificate signing, whether you want to generate your own key pair internally device, whatever resource you have, either you have OpenSSL stack, you are in random generation key generation mechanism inside a device, or you have your own TPM inside the device. You generate the key pair and send the public key for the send a CSR to a PKI, then request for an auto enrollment, and then you get the enrollment and you receive back the certificate back to the device. automatically. Then you keep monitoring the expiry of the certificate. So these are looks very small, but when you start implementing embedded systems where you have to write your code on the C or whatever the embedded software code, the renewal, you put a timer and put a low priority task to check that expiry of the certificate. Then before 30 days, then you apply for renewal. Then check the revocation status of the certificate. So there's also one low priority task, check the revocation status and connect to the CRLs or OCSP, how you have an access to the CRLs, CRL deployed machines, points, distribution points, or your OCSP responder. You allow to configure that, then you monitor the certificate revocation before establishing connection. So these are the basic steps for any PKI infrastructure when we implement that in the OT product. So keep it straightforward and with a minimal implementation and keep it seamless. Now, how the customer would like to pre-install, what the infrastructure he has. So you should keep it in mind, provide all the option to the end customer. It's not a one solution. So this is the solution which could be allow any customer or the product integrator, vendor, an operator, starting from a small the oil and gas station, or it's from the aviation and a ship inside the ship, an aviation system. He should be able to integrate this into his system. Yeah. So yeah. So as we know that as the OT device, you should have a kind of a small PKI client component inside an embedded systems, which request for the CSR. So this also kind of as the 623 standard 9 so talks about how we can implement your the CSR renewals. So what different options you should give, whether CRLs or OCSP, what options the customer has, whether he can support all the options. And deploying automatic certificate update on field. So how the commissioning engineer or C administrator, the steps the C administrator take, then he configures NDS service, and then the devices goes to the field. You deploy it onto the remote oil plant, the oil extraction platform in the sea. So you deploy that, your production systems there. Then your commission engineering, we provide the CA certificate, the thumbprint into the device. Then you have request go to the RA server. If you are able to reach the RA server, then you send a CSR request and get the certificate and keep monitoring the renewal and the expiry date of the certificate. So there are chances that your device is not always online. There are chances that your product is not always able to connect to the PKI because there could be connectivity issues. How to monitor whether he can survive with the existing certificate or expired certificate, what decisions the product has to take. Okay, whether we can live with the expired certificate or we should prohibit an operation on the device. So these are the challenges in the OT product vendor and customer face. Yeah, the certificate renewal options. How you create the certificate, and renewal, wait for the timing out and implement that. Then with respect to that CRLs and OCSP implementations. So there are trades how much CRLs list you can store in your own your memory location, because there are memory constrained devices that the dedicated device may not have your huge memory like a big HMI server or PC based system. So whether you can connect to CRLs or you can give both options, go for an CRLs. The CRL, the challenge, the CRL, okay, the CRL is checked before your TLS handshake, or if you OCSP, then you first establish session, then check the OCSP status. So how it can support both. You give an option to the customer. Okay, so if you have a CRL capable CDP in your systems, yes, then you can choose this option. If you have an OCSP option, okay, you can choose this. So like that, and the product vendor or developer, so they should provide all the option to the customer. Should consider these things in its design, product design. The second aspect is the way the PKI is coming into the picture is the digital signature, because the trusted vendors concept. The image patching what comes from our product vendor, whether it is coming from the authorized source or not. So that is the device has to check that the validity of the patch. So that's where then you sign you store the public key of your CA into the product, and you deploy that product onto the field. So then when the patch is released by the trusted vendor, then the patch is verified from the CA. So it's okay, verify the signature of the patch. So this is where we also use the support, whether say like we have the option of like, okay, we have our own local CA, or we should go for a PKI infrastructure where our key signatures are our private keys are held by the PKI team, like DigiCert, semantics, or various options what we have across the world. So then you get the signature signing request during as a part of our build, then release a patch to the customer. Then the customer, when he's deploying under the field, so that system has an access to the PA to verify the signature. Okay. So yeah, so we have seen that this signature verification, code signing, is a part of our secure boot implementation, is a hardware root of trust in the OT device, whether we'll have a safe secure memory location or it's a TPM inside the OT device, where you verify the signature. So predominantly we are seeing the two major implementation. One is UEFI secure boot, or it is a U-boot based secure boot. UEFI secure boot mainly predominantly used in the PC based architecture, where you have a BIOS, a UEFI BIOS, and where it supports your signature verification, and it allows you to store your hash, signed hash, or the public key certificate itself into a safe memory location, NVRAM. So it's not only your signature, also it needs as a UEFI standard says, it needs the public key, platform key, and key exchange key. So which key used controls access to your database, the DB and DBX, where it's a DB has this valid signature and DBX has a block list the signatures or certificates. So during your signature verification, so you go the certificate is during operation, your patches are verified by the code signing, the CA and signature verification before starting from the pre-bootloader and bootloader, then kernel, the OS kernel, then your root file system. So everything you need to sign to ensure that with the public key inside your secure memory location, ensure that only authorized vendor or authorized softwares are booted. Otherwise, once if you leave the room there, already the standard clearly says that okay, you should have your own, the product should have its own hardware root of trust, and the possibility of use of TPMs or secure memory location should be allocated within the OT device. So that's where you store your the keys, important keys, and the respective database within your architecture. So the high-end devices like controllers, gateways, where we have industrial computer grade systems, which can have a good amount of memory and processing power, they usually adopt this UEFI. Or if it's a kind of a primary embedded systems, which is a very minimal memory and the communication capabilities, we go with the U-boot based, the ARM architecture based embedded computers, where the U-boot, the bootloader provides an access to then a TPM, and it allows you to signature verification, allows you to implement your secure boot. So based on the what device we have, where it goes on sit, whether the station computers or the station controllers or the field devices. So based on that, so based on different architecture, we implement this the code signing with the support from the PKI infrastructure. Thank you. Then yeah, so there are standards or guidelines which accepted worldwide. So we are these standards are keeping in touch with this all the IETF other standards for the latest happening in the PKI world or in the cryptography world. So they update that guidelines into these standards, and as a product developer or companies, we look up to these standards, and these customers also say that okay, your product must be compliant to this, certified by this standard. So we design our product, implement our the secure development lifecycle practices or the product requirement in compliance with these standards. And yeah, so these standards have the already the provision or the telling about the product vendors take into the consideration of PKI infrastructure in your design, how to integrate PKI infrastructure into OT or product at the primary system level to the high-end system level. You provide a seamless integration support or into your product architecture. So these things we keep in mind during our product and development. Of course, once product is deployed, it's not that it's safe. We know that after the device is there in the field from last 5 years, then suddenly there's a vulnerability reported on the particular Linux OS or embedded Linux OS. Then again get panic starts. Okay, then you create a patch and deploy it the customer, and the customer has to have a time to deploy that patch into the field. So under the product, it's very complex life cycle, but still, so that is making the system is vulnerable, and we are in a catching up mode because we have a lot of other challenges like operational challenges into the system. The security becoming kind of an additional task onto the existing product architecture, but yeah, the standards are so changing so fast. Like first they came to TPM 1.2, within 2 years that no, TPM 1.2 is no longer valid. Now you go to TPM 2.0. So it's not so easy. So say the products are deployed and say that within 2 years the TPM is no longer standard, then you cannot say the customer, okay, the TPM 1.2 is no longer used, so you should go for a TPM 2.0 upgrade. Then customer will ask us, come on, I have purchased the product just 3 years back. You cannot say that it's now no longer usable. So that's the challenges we face, not only in India, in everywhere, across the globe. The product companies, the customer, there is a the kind of a heated discussions, but in these where I think these standards are helping us. Okay, see, this is standard, this is the neutral standard. It is developed by or maintained by a neutral organization, and organization like TUE organizations, they are certificate agencies. They work on along with this standard companies. So we take their the compliance audit, and they will certify our product. At least that gives a neutral ground for us. Okay, see, the standard changed, that's why we are changing. We have to adapt it. So there is a balance we try to maintain. Thank you for time. Yes, because this is as I said, these standards are global standards. Everywhere, even the Indian, so for example, CA or IEEMA in India, so the regulatory bodies, so they insist that our product must be certified by these standards. So we have
But you have been mentioning in one of your slides, the CA certificate issued by DigiCert.
Yeah.
But that is not in MeitY,
No,
right? In one of the CA slide, just go back.
We just say CA. We don't say that which PKIA or it is this thing. So the CA could be anything.
But if you're going to the CA slide, DigiCert interest varies on.
Yeah.
So these are the CA which is not even related to my PKI ecosystem.
Yes.
Then how your product is with this international standards going to apply us?
So for example, as a product vendor, we don't say that okay, we'll go for this CA or that CA. Okay.
So when you want to come into my you want to come into my PKI infrastructure of my Indian ecosystems, you have to go with my CAs.
Correct.
For entrusted root.
Correct.
Our CC India route.
Correct.
If that is not it, then you are going to rely on the outside third party.
Correct.
Then it means that you are going to follow the outside standard in my Indian market.
Yeah. So here the standards.
No, when you come back to Indian market, you have to come back to our PKI systems.
Correct. So our products are not dependent on any particular CA. So our product, the product what you develop in the OT product, they're supposed to support any PKIs. For example, the product developed is, so for example, Reliance, the oil and gas, you want to install a product. our certificate should be signed by CA. So definitely product should provide that option. The import those certificate or connect to the local CA.
That's
and
why
get
Reliance
signature.
has now became a CA now
Yes,
with us.
yes,
This is the reason behind that, maybe.
yes. The product should give that seamless integration. So that's why we don't say which CA it is. Any CA, okay, you tell you configure that CA. So okay, this is a CA where the certificate must be signed. So the product should support that. It's not only anybody. This is how the standard says. The standard will never say you go for this PKI, this PKI. This should be PKI enabled. So that's all. So the standard doesn't talk about any vendors. So they are pretty neutral, which is followed across the world and across the domains. So
If I understand right, they are using the self-signed certificates for internal
self-signed
activity.
certificate is just a factory default. So when the product goes to the from manufacturing company, because we are not owning the product ultimately owned by the customer. So we don't put our own certificate in that. So we give the product the self-signed certificate. Then we provide option to the customer to configure his own CA and put his own certificate during the commissioning stage. During commissioning.
So finally, commissioning stage, they are coming
Yeah,
back to
the
CS.
deployment in the on-field deployment, the customer has his own CA. He should be able to put in his certificate onto the product, and he should connect with his system.
But try to come back to my infrastructure.
Yeah.
So that will value the more to the Indian
Definitely,
ecosystems.
this product should that's the idea is any OT product should provide the support the local PKI infrastructure. So that is a core. Even the standard also says, doesn't say anything. So you should be able to provide a seamless integration to the local regulatory bodies or local CAs or local PKI systems. So that is anyway is very clear.
Thank you.
Question, renewal and revocation
Yeah.
have always problems.
Correct.
If people are scanning.
Yes.
So how do you overcome that?
Which one, sir?
Scanning,
Yeah.
when people are renewing or when the revocation or when it has delegated and the certificate has revoked because revocation is not monotonic.
Correct.
These are the serious problems in which the failure happens.
Correct.
How do you handle that?
Yes, sir. So that is challenge actually, as you rightly said. The product vendors or system vendors cannot control this because what happens after 1 year? 1 year we don't know the certificate which we deployed in the systems no longer valid or is already revoked. So it is again the customers the decision that we have an option where you can specify which CRL to be checked, which CDP should be connected to check your CRL distribution points to be connected to request for the verification or which OCSP responder you need to connect. So that's where the configuration points are there. But ultimately, it's the customer, he has to provide the right configuration path. Okay, as a OT product, you should reach out to this CRL or list or CDP or this OCSP to validate certificate before establishing the communication. So ultimately, the system owner has to take care of that.
Thank you, sir. Thanks to all of you. Thanks for a wonderful presentation, Mr. Kumaraji. As a small token of appreciation, I request Dr. K.K. Sundrapandian from the Office of CCA to present a memento. Thank you. So the next, I think there is a very short tea break. We can actually, tea is getting served outside. You can pick the teas and come inside. We have the international speaker, Professor Ramesh Kari, waiting for us. So we'll just start the session in 5 minutes. Okay, so 11:08, 11:03, 11:08 we can start. Connection time.
वही मुझे आश्चर्य हुआ। नहीं चल रहा है, वाईफाई यहाँ दिख रहा था। नहीं वही मैं बोल रहा हूँ, ये मुझे भी नहीं समझ में आया।
I request members who are standing out, please to pick their coffees or teas and come inside, please. आवाज नहीं याद है, you can tell. Your message remove. No. Message, yeah, that is important. What is he waiting? Duplicate.
स्विच करो इस, हाँ डन ठीक है।
You first ask them the people to come. Professor Ramesh Kari, sir, just can you wait for a couple of minutes, sir? We are waiting for the audience to join here.
Sure. Can you
Sorry
enable?
for the delay. Actually, the session got a little bit delayed.
That's okay.
Previous session.
Can you hear me? Hello? Can you hear me?
So welcome back. So today we are delighted to have Professor Ramesh Kari from New York University. Good morning to you, sir. So
good morning.
I'd like
Can you
to
hear
briefly
me?
give the Professor Ramesh Kari here. Ramesh Kari is a professor of electrical and computer engineering at New York University. He co-directs the New York University Center for Cybersecurity. He also leads the Cybersecurity Trust of the New York State Center for Advanced Telecommunication Technology at New York University. He co-founded the Trust Hub and organizes the Embedded Systems Challenge, the annual Red Team, Blue Team events. He has a PhD in Computer Science and Engineering from the University of California at San Diego and a BE in ECE, Electrical and Communication Engineering from Andhra University, India. His research and education activities in hardware cybersecurity include trustworthy ICs, processors, and cyber physical systems, security-aware computer-aided design, test verification, validation, and reliability. Hardware security, he has also conducted hardware security competitions, done benchmarks and metrics. He has discussed on biochip security and also contributed to additive manufacturing security. He has published over 300 articles in leading journals and conference proceedings. He is a fellow of IEEE. His work on the hardware cybersecurity has received Best Paper Award nominations across several conferences, awards, and he is also and VLSI Design Award in 2012. He has received ACM Student Research Competition Award in 2012, DAC, ICCAD 2013, DAC 2014. He has also been the winner of the ACM Grand Finals 2014 and Kaspersky Challenge and Embedded Security. Good morning to sir. We are privileged to have you and listen to. We are happy to listen from you, sir. Over to you, sir.
Thank you. Can you see my slides?
Yes, sir. We are able to see your slides.
I'm not okay. So yes. Okay. Thank you.
Yes, I'm able to see your slides. Yeah.
Thank you. And you can hear me, I guess. So let me also.
Yes. I'm able to hear you very well.
And, cool.
We are able to hear you very well, sir.
Good. Okay. Thank you. Thank you for inviting me. And thank you all for joining this meeting. Thanks for the introduction. New York University, what I'll do is I'll do it a couple of things. How much time do I have? About 35 minutes or so, because we started a little late. Should I still keep it to?
No, sir, you have 30. Sorry. You have 35 minutes, sir. We can have a 10-minute question answer session also. So totally you have 45 minutes.
Okay, thank you. So what I'll do is split this talk into 2 or 3 pieces. The first piece will give a high-level overview of what we do at NYU Center for Cybersecurity. And then the second part is where I'll talk about the high-level approaches to hardware security, which is the emerging regime of hardware cybersecurity. So NYU CCS continues to impact the emerging world of IoT, wherein the basic trust in society is at stake. It does so in at least 3 ways. First, what we do is we build secure systems at scale, and we make sure that the systems are unhackable. We consider systems at the hardware level, at the software level, the firmware and embedded systems level, holistically, and deploy them at neighborhood, at city scale, and global scale. Second, we secure the important supply chains, such as the electronics, the software, the control systems, and the digital manufacturing. Finally, we fight cybercrime at a global scale, including financial cybercrimes and cybercrimes, for example, against children. Just to reiterate, cybersecurity at NYU is a global scale effort. CCS spans multiple schools. For example, School of Engineering, where I am, School of Arts and Sciences, the Law School, and the Business School, among others. CCS has a strong presence in the Middle East. CCS Abu Dhabi in NYU Abu Dhabi is our beachhead in that area. CCS Abu Dhabi, besides offering all the advantages of routine advantages of being able to do cybersecurity research, offers us to investigate the cultural perspective of these emerging cyber threats. Here is the core cybersecurity team at NYU. This team looks at cybersecurity from multiple angles in a holistic fashion, as I mentioned. We see it as an IT and as an IS, as a CS problem from the chip level, firmware level, embedded systems, all the way up to the networks and systems. We see it as a human psychology problem. We see it as a human rights problem. We see it as a risk and risk management problem. Of course, it is an economic risk problem. We've been addressing cybersecurity since roughly 1998-ish, before cybersecurity became important. For example, in the USA, we are an NSA Center of Excellence in cybersecurity research. Our faculty, about 20 or so, mentor about 80 PhD students and over a dozen researchers. Some of our current research areas span critical infrastructure security. For example, that was one of the talks that just preceded my presentation, including in the power grid cybersecurity, transportation, and digital manufacturing. We also have expertise or research in supply chain security, hardware, software, digital manufacturing, for example. We also look at security of AI, the most recent being security of what are called the large language models, backdoors in machine learning models, and all the way to deep fakes and so on. Finally, we also look at AI applications in security, securing the hardware, in securing the firmware, and in securing the software, and in securing the entire system. My colleagues serve on the technical program committees of leading cybersecurity conferences. So, for example, IEEE SNP, Usenix, CCS, NDSS, and so on. Our center has dedicated space in Brooklyn, New York, 10,000 square foot, and about 8,000 square feet of space in NYU Abu Dhabi. We offer, this is something probably of interest to you, we offer a dual degree program with IIT Kanpur. And we also are building a joint PhD program in cybersecurity between NYU New York and NYU Abu Dhabi. We collaborate and partner extensively with universities, the governments, and the NGOs and industry. Our research is funded by various organizations, including DARPA, ONR, and so on and so forth. We have raised over $40 million to conduct research over the past 66 years, rather. We've been addressing cybersecurity, as I said, for close to a little over 15 to 20 years. We are only a handful of institutions that have the trifecta of distinctions for excellence by the National Security Agency. As I mentioned, we are an NSA Center of Excellence in Cybersecurity Research. Besides, we are an NSA Center of Excellence in Information Assurance Research and in Cyber Ops. The excellence in Cyber Ops recognizes and celebrates NYU's rigorous, practical, hands-on approaches to cybersecurity. And cybersecurity, both in terms of offense and in terms of defense. And it pervades our curriculum, underpins our research, outreach, and capacity building, and of course, workforce development activities. We have strong federal agency ties which include training students for the government service. We offer, for example, we also offer an MS in cybersecurity and an online program called Cyber Fellows in cybersecurity, and a joint with the NYU Law School. We offer the MS in cyber risk and strategy, and we have also we do what's called the bridge to cyber to help transition non-STEM students into the cybersecurity workforce. This is something that we are most passionate about, besides, of course, research and education, outreach. NYU CCS has a 20-year strong outreach program. CISA, for some of you who may be aware, is the largest student-run cybersecurity event in the world. It is held simultaneously in North America, in Europe, in MENA, and in Asia out of IIT Kanpur. CCS has about thousands of participants. CISA has thousands of participants annually. It organizes numerous competitions. For example, CTF, we call it Embedded Security Challenge. I call it Capture the Chip, cyber policy competitions, and so on and so forth. If you go to the website cisa.io, you'll see the events for this year. We also organize, one of the things we do is our classes that we teach use many of these challenges as examples and homeworks. These challenges and the outcomes of these challenges are also used by other institutions. We organize the Successful Women Leaders in Cybersecurity program. We have a Hacker in Residence program, and so on and so forth. Let me see, where am I? Yeah. So coming back to the topic for my presentation, over the years, electronic hardware has become the core root of trust for all systems, from buildings to pets and everything in between. However, globalizing the electronic supply chain over the last 2 decades has introduced numerous security issues. And because of this, the electronic hardware root of trust is no longer trustworthy. The systems that use them are no longer trustworthy. What I'll do is I'll paint my vision of hardware cybersecurity and the implications on how integrated circuits and systems will be and should be designed, and more importantly, continuously validated. High-level synthesis, when I say high-level design approaches, I mean high-level synthesis, especially in the context of hardware. It's a design methodology that translates high-level specifications, for example, in C and C++ into gates, either as an FPGA or as an ASIC. HLS research started in early 1990s. However, it did not take off until very recently as a commercial product. The reason was it was not ready for prime time. Performance, power, and area metrics were not good enough. In those times, circa 1990, logic synthesis was sufficient and effective in managing the complexity of the designs. So fast forward 2010 or 2012 or so and beyond, designing at these higher abstraction levels has become a prerequisite to manage complexity. High-level synthesis at the same time has become competitive in terms of the PPA metrics. Besides, it offers at least 4 benefits. 1, it reduces the design time. 2, it manages design complexity. 3, it reduces verification effort. And finally, it enables hardware, software, co-design, and co-verification. Mentor Graphics, which is now Siemens Mentor, Cadence, Intel, Xilinx, and other companies offer HLS tools. Several of the top 20 semiconductor companies use high-level synthesis tools. The cumulative annual growth rate, CAGR, of gates per centimeter square is about 59%, roughly, according to this study by Semico. At the same time, the CAGR of design or designer productivity is only about 25%. And this has created a design productivity gap, as you can see here. By raising the abstraction to the high level C or C++, HLS or high level synthesis allows bridging this gap, hopefully. It allows for early design exploration, and the applications typically used by HLS include data-dominated applications such as image processing, crypto, machine learning, video, vision, and so on and so forth. Video components in the Tegra X1 chip are designed or were designed using Catapult HLS from Mentor. NVIDIA 4K processing unit was designed with C-based HLS. Qualcomm designs parts of its Snapdragon processor using, again, Catapult HLS. Okay. Here is a related trend. IC and system designs are using third-party IPs. For example, while there were about 16 or so IP blocks in a typical phone at the 90 nanometer node, it is projected that there will be about 200 or so IP blocks at the 22 nanometer node. So the increasing number of accelerators has its benefits. Quick design time by trading off integration for actual design. Benefit from specialist focus on these individual accelerators and specialized cores. On the graph, you see the red line. It shows that by about this time, or about in a couple of more years, about 95% of a design could be mostly integration of accelerators sourced from third-party vendors. On the other hand, these accelerators and the third-party IPs may compromise security of your system. Attackers in these third-party IP vendor companies may embed, for example, backdoors and insert Trojans in these accelerators. Now let's look at the blue line. It shows the cybersecurity investments, both actual in the historical sense and projected in a futuristic sense. Some of this will be to deal with these accelerators, some of which will be to use these accelerators for security. So here is a typical HLS design flow. I don't know if you can see it clearly, but the background is a little dark. Hopefully you can see it, but on the top left-hand side is a specification that is translated into an intermediate representation called the control data flow graph. That's shown in the middle. And this is what software compilers do as well. HLS leverages these state-of-the-art compilers, for example, GCC or LLVM. And then in the scheduling step, operations in the CDFG are mapped to clock cycles. Some of them may take a single cycle, others may take multiple cycles. One can get fast schedules that are resource intensive or slow schedules that are resource constrained. In the next binding step, right on the middle and top of that figure, the scheduled operations in a clock cycle, maybe let me see if I can. Yeah, this is right here. The scheduled operations in a clock cycle are bound to operators. For example, multiplication operations are bound or mapped to multipliers. Addition operations are bound or mapped to adders, and so on. Similarly, data transfers that span or that cross clock boundaries are bound to registers. Finally, you get a data path as shown below right here. And a controller as shown there. The controller sends control signals to execute operations on the specific chosen operators. Since operators and registers are reused, you see multiplexers sitting in front of them. The select signals of the multiplexers in the data path are controlled by this controller. Let's see if I can. Cool. So let's look at a current application domain of crypto, and more importantly, post-quantum crypto. Since quantum computers can break RSA and ECC that underlie public key crypto, and since quantum computers cannot break AES and SHA, which are the private key crypto and hashing, PQC asymmetric crypto replacements for RSA are being developed. So the US NIST, National Institute of Standards and Technology, is standardizing PQC algorithms. The process started roughly about 4 or 5 years ago. In round 1, there were 82 submissions. In that round, they were mostly evaluated for security strength. For rounds 2 and beyond, that is round 2 and 3, implementation trade-offs were considered as well. As of a month or so ago, NIST announced these winners. And for those of you who are following this, Saga, one of the potential 4th round candidates for key encryption, key encapsulation has already been broken. It's called Psyche. So to manage this aggressive standardization schedule, we used high-level synthesis to study the implementation trade-offs. We started with the input C codes from NIST PQC round 2 submissions. We changed these C codes to make them HLS ready. And this requires a lot of effort anyway. Verified the changes using the known answer test that the submitters provided to the NIST. We used, at that point in time, Xilinx HLS to study these implementation level trade-offs in this tight time schedule. These codes are publicly available for both the C codes and the scripts for HLS are publicly available. While the designs might still not be as efficient, they're customizable and they're useful for design space, rapid early stage design space exploration. And that was, in some sense, informing the standardization process. So we've seen how HLS can be used to accelerate or used to design crypto. We started with C-based design and translated into ASICs and FPGAs. So now I'll talk a little bit about the security awareness of HLS. So let me consider or suggest using security as a design metric. Most hardware security research has focused on the gate level, the netlist level, and beyond. Obviously, at this stage, in these stages, one loses important semantic information and are left with structural information. So securing the right parts is hard. Security-aware HLS allows one to secure a design at the high level. So high level or algorithm level security secures or uses meaningful semantic information. For example, even a non-security conscious design engineer can easily identify or easily suggest artifacts to protect sensitive info at this high level. High level synthesis and register transfer level, which is a step below, have sufficient semantic information, while gate and layout level have structural information mostly. So if we stop right away, these are going to be the takeaways, and I will spend time on these takeaways in the next 5-10 minutes before I close down. So what the key takeaways are: high level is a promising level to design accelerators, including security accelerators. High level is a promising level to build in or design in security. High level synthesis can be used for a variety of security awareness tasks, such as Trojan detection, Trojan isolation, watermarking, and obfuscation. High-level synthesis can also be used for incorporating taint propagation in designs. Some of you may be aware of taint propagation in software, but you can bring that into hardware as well. It also has its drawbacks. High-level design can be, or HLS generated designs can be reverse engineered. Time permitting, I'll spend some time on this. For example, similarly, a black hat can use high-level synthesis to undermine designs, weaken crypto, drain battery, and so on. With those key takeaways, let's come back to the foundational question of: can HLS or designs generated using HLS undermine security? So let's look at a threat of reverse engineering. Here, an attacker tries to identify the device technology used in an IC, identify the functionality in the IC, or the design itself. Reverse engineering is typically a precursor to Trojan insertion and piracy attacks. Anyone in the downstream of an IC design flow can do reverse engineering. For example, the SoC integration house can try to reverse engineer the third-party IP. The foundry could be a reverse engineering actor, or the end user can reverse engineer the products that they buy on the market. Typically, the reverse engineering at an IC level takes an integrated circuit, depackages it, delayers it, images those individual layers, and annotates them, and analyzes the images and extracts the design. There used to be a company called Chipworks. I think it was been taken over. I don't know who took it over, that performs reverse engineering. So let us consider the reverse engineering attack on HLS created designs. The attacker obtains the IC or IP from a third party, from an IP vendor or a foundry, and the reverse engineers for example, the layout, obtains the design specifications, for example, the clock frequencies, the IO ports, and so on, from the data sheets of the IP. But we assume that they do not know the controller. If you remember when I showed you the HLS, there was the data path and the controller. We assume that it is hardened using logic locking and other techniques. Their objective is to recover as an attacker the controller, or even better, the original C code. Their attack plan is somehow to use the heuristics used by HLS to generate these designs. So let me rephrase the attack as follows. Consider this super CDFG, as I call it. Here, each vertex is an operator in each clock cycle. Each edge is a possible data flow between the vertices. The attacker starts with this super CDFG and prunes away all infeasible CDFGs out of this super CDFG. And hopefully, what remains are, or ideally is, a single CDFG that is implemented by the controller that we showed you on this slide. Right here is a controller. So we don't know that. He does so, or they do so, by using the heuristics of HLS to reduce the number of plausible CDFGs. The question is, how many CDFGs can be implemented by the design? So ideally, as I mentioned, the heuristic-based pruning should recover the original CDFG shown at the bottom here, out of the from the super CDFG at the top. For that, we'll use a variety of constraints, 3 key sets of constraints. The data path constraints involve investigating the register transfer level blocks and interconnections between them. Like, for example, answering the question, which blocks write to which registers by looking at the multiplexer points. For example, either multiplier 5 or add 2 writes to register R5. If you go to controller constraints, some of the heuristics are as follows. Identify select signals, signals that connect the controller with all the multiplexers that sit before the registers and the operators. Identify relationships between select signals and state signals. For example, in states 3, in states 4 and 5, add 2 writes to register R5. In state 2, for example, the multiplier 5 might write to the register R5. But we know that only one state is active at any time, because each state is associated with a clock cycle as an artifact of high-level synthesis. So that is either state 2 or 3 or 4 or 5 can be active at any time, and so on. So the next thing you want to do is the input-output constraints. The IP, for example, the input arrives, say, at cycle 0. So the operator connected to it should compute, for example, should compute in the next cycle. For example, the IP, the input X that may arrive at cycle 0 is stored in register R1. I don't know if you can see these things here. Similarly, when is the output ready? It could be ready in some cycle X. If so, an operator connected to it should write to the registers, output registers in the previous cycle. There's also the latency consideration. Some operators take 1 cycle, some operators like multipliers take 2 cycles. So if you combine and put all of these constraints and impose these constraints, apply these constraints as part of your reverse engineering step, you could potentially recover the original CDFG. So here I have a table where we have some HLS benchmarks. The number of CDFGs without any of these prunings are shown in the next column right here. Then you apply the constraints iteratively. And at the end, if you look at the rightmost column, you'll see the pruned away CDFGs. At the end, you started with a large number, for example, for AES, 2 to the large number CDFGs, to about 512 equivalent CDFGs that are functionally equivalent and oftentimes structurally equivalent as well. If you look at the BQF, again, you start with 2 to the 53 possible CDFGs and come to prune them down to 2 to the 2 or 4 equivalent CDFGs by applying all of these constraints. you come, these are from here to here, you apply data path constraints. From here to here, you apply the data path plus controller constraints. And the last step is to also bring in the IO constraints. So we applied this attack on commercial and open source high-level synthesis tools. We call them A, B, C, D, and E. We don't name them. We formulated all these constraints as SAT formulas and used a SAT solver to derive these CDFGs. We checked the recovered CDFGs to make sure that they're functionally and structurally equivalent. We checked that all the CDFGs, in terms of functional equivalence, we call it's the IO equivalence, input-output equivalence. In terms of structural equivalence, we also look at results at the intermediate points. We call them the compare points, that these intermediate results are also equivalent. So this is one way. This is an attack of on designs that are generated using high-level synthesis by applying or repurposing the heuristics used by them. See, let me see. So yeah, so the question is, will obfuscation help in protecting the IP? So I think I'll be getting there in a second or so. Thank you, Dr. Ananda Mohan. Just looking at this. So the next threat, we have, what time did we have, how much more time do I have? I can usually go through the slides or skip the slides and continue on the discussion. Any suggestions on how much time I have? Okay. So let's look at 3P, third-party IP and malicious third-party IP. Here, instead of talking about an attack, I'll talk about a defense. The threat model we consider is one of rogue 3P IP vendors. This could subsume bugs in these 3P IPs. Of course, one has to trust someone. We trust the SOC integrator in this context. And the SOC integrator has control only over the integration, but not over the internal details of the IP. And we assume, for simplicity, Trojans that can cause wrong outputs. Furthermore, if the 3P IP modules are sourced from the same vendor, we assume that they can collude. These are what I call distributed Trojans, to make it slightly interesting. Okay, so this is a classic high-level synthesis example. On the left-hand side, that's the high-level code. On the right-hand side, you have the CDFG. This is a simple specification and a simple CDFG. The modules here are sourced from IP vendors. We don't know if they are trustworthy. We assume that they are untrustworthy. The objective is then to generate an RTL for a trustworthy system that can detect or mute the effects of Trojans in the sourced IPs. So one straightforward approach is duplication. And this is what we do for detecting natural faults. You make it copies and make sure that the original and the duplicate do not share hardware. The classical assumption here is at most one module is faulty. The approach is straightforward. What you do, you duplicate, you map the duplicate copies to run on disjoint hardware. Checkers detect output mismatch. Key assumption, at most one module is faulty. Now let's come to malicious 3P IPs. The third-party IP vendor sells Trojan-infected, potentially infected, or even buggy 3P IP modules. Integrator synthesizes SOC using these IP modules. And anytime you instantiate an IP, it's replicated every time that happens. Right? So if you look at this, if you duplicate a module, if it is infected on the from the same vendor, then even if it is a distinct module, it has the same Trojan. Components with Trojans produce same malicious outputs. That's the other thing. So checkers cannot detect malicious outputs because this violates the assumption for reliability. Right? So reliability does not imply security. I hope that. So besides just replication, Trojans may collude, as I pointed out. There are at least two types of collusions: parent-child, where both of them are from the same vendor and they could potentially collude, or parent-to-parent collusions, where if the modules from the same vendor, then they could potentially collude as well. So, for example, to prevent parent-to-parent collusion, you should make sure that at least one of the parent operations, for example, this one, O1, operates on a module from a different vendor, so as to break the dependency. So a quick summary here is it's not just about duplication. You want to do diversification of vendors. If you want to, for example, if you want to prevent, for this example, parent-to-parent collusion, you need at least 3 vendors, and the colors give you the vendors. And so this can be done during high-level synthesis, after scheduling, during mapping. Of course, the overhead is the number of multipliers now increases to 5, and the number of adders remains 4. So the cost, it's not just about duplication and so on. You need to procure these multiple IPs from multiple sources. As Dr. Ananda Mohan pointed out, you can also do high-level synthesis for obfuscation. This is a different way of, IP theft is a different way of looking at reverse engineering. The threat model is one of, as I said, IP theft. Obfuscation is the proposed defense. Obfuscated design typically goes through the untrusted phases of the IC design flow, all in the obfuscated form. And after production, once the chips come back, the correct keys can be applied and activated. There are different kinds of obfuscations. And to keep it at a high-level synthesis for obfuscation looks something like this. And this is, as you can agree, is quite intuitive. There are control flows, there are constants, operations, and dependencies between operations in a design. So each of those 4 ways, you have then, each of them present 4 ways to obfuscate an algorithm. For example, obfuscate operations. It's easy to apply. Reasonable area overhead, pick the dummy operations that are already available. Each operation type has you pick a predefined set of alternatives and so on. So you can do obfuscate operations. But something even more intuitive is obfuscation of constants, where you have coefficients, for example, in your filters, you remove them from the circuit. Instead of synthesizing them, you store them in registers. This suddenly offers dramatically more protection. It results in, of course, less logic level optimizations and increased area overhead. So in contrast, logic level and netlist level operations operate on optimized logic synthesis. In some sense, some of these things are already baked in if you don't do obfuscation at the high level. So this is roughly the obfuscation flow. Take a design and do obfuscation during high-level synthesis. You get an obfuscated RTL, then you do synthesis, go through the backend flow, you get an obfuscated netlist. The problem here is now you have to integrate the obfuscations into an HLS. But so there's another way of doing it where you get the RTL from the various HLS tools here, for example, Mentor, Xilinx, Intel, BlueSpec, or Cadence, and apply obfuscations at the RTL. This is still before the netlist and gate level, so they still have some of this semantic information, high-level semantic information. For example, you can still do constant obfuscation, and you can still do control obfuscation. So on that note, what I'll do is I'll pause here, stop here, and conclude. As I said, these are the takeaways I highlighted initially, and I want to reiterate those takeaways or conclusions. On one hand, high level is a promising level to design security accelerators. It is a promising level to design and security. HLS can be used for Trojan detection and isolation. I showed you one approach. HLS can be used to watermark designs. If you just Google, you'll find a few papers. HLS can be used for meaningful design obfuscation. We started looking into that. We have a few papers. One of the tools that we have developed is called Assure. Again, you can Google that. HLS can be used for seamless and meaningful taint propagation, complementing the software level taint propagation. However, you got to be careful and mindful of the drawbacks that are associated with HLS. HLS generated designs can be reverse engineered. A black hat or an attacker can use HLS to undermine designs, to weaken crypto, to drain battery, and so on and so forth. On that note, thank you, and time permitting, I can take questions, and thanks for your patience.
Thank you, sir. Thank you for the wonderful presentation, and thank you for taking your precious time out. I know that you are traveling, but despite your tight schedules, you were consented to be part of our conference program. Thanks a lot, sir. So I would like to open it to the audience for question answers. Okay, there is a question here. Mike.
Maybe I can stop sharing so I can see you.
Hi, Ramesh.
Hey,
Can you hear me?
yes, I can.
Yeah. What about this tranching insertion? How do we analyze, or how do we check it out during the fabrication level? Is there any process we can undergo so that at the fabric, even giving the net list to the companies, so without the knowledge of the given concern, it has been inserted, and moreover, the logic cannot be changed when we check the algorithm also.
Mhm.
So moreover, it doesn't have a big impact in the gate level, netlist level. So how do we analyze that?
So this is the beauty of this particular area of hardware security. Most questions that you ask are possible questions.
Rameshkari, we are not
research.
able to hear you. You are muted.
I'm not muted. I think maybe you muted me somewhere. I could.
No. Okay.
Yeah, it's
fine.
okay. Now it's clear. Yeah.
Okay, good. So just want to repeat. I think the area of hardware security is still emerging. At least I would like to think so. So most questions that come out of these presentations are usually questions for research. So the question here is, you have an IP that has Trojans, and you did not catch those Trojans. They were deeply embedded. And then how do you catch that during fabrication? So security verification at every step, post RTL, post gate level, post netlist level, and even during the, so you got to do verification at every step. And each step, hopefully it is a different party that does the verification. So hopefully they catch it. But this is the problem with just like is problem with the Trojans, whether be it in software or in hardware. There is no guarantee that the resulting chip has no bugs or no Trojans. The only thing you could do, and this is what typically you do this is the difference between test and trust. In test, all you have to do is make sure that the chip does the expected thing, right? You can do verification and you can guarantee that it does the right, it matches the specification. In security or in trust, you want to make sure that not only does it do the expected thing, it doesn't do anything else. And that opens up a huge problem space that is beyond the scope of a typical VLSI test community or a verification community or a validation community and is an open problem. I hope I answered your question.
Yeah, that's the reason chip manufacturer and device manufacturer should have a test and a trust.
Yeah.
Thank you.
Yeah, hi Ramesh. So I wanted to ask you, what about putting a wrapper about the chip so that it only gives me the function what I want? For example, if it is a time bomb, if I make the clock of hardware go reduce rather than increase, there will be no time bomb.
Mm-hmm. Yeah. So for every, I don't know, I mean, I'm from.
Every chip can be caught. So
I know. So I'm trying to. Yes. So my take on this is a slightly different take. So I'm from Andhra. So my mom says for every daridram, there is satakoti daridraliki anantakoti upayalu is what they say. For every fix, there are many ways of going around the fix. That's for those of you, many of you understand Telugu, I guess. So the answer is yes, you can have wrappers. In fact, there's lots of, even in testing, you do security wrappers and so on. At some point, you want to make sure that the wrappers themselves are not buggy, right? So there are other approaches, not even running it slow, but you can also reset the clock. That's another approach to defending against these time bombs, right? You can periodically reset the clock, reset the state, and the time bomb dissipates or goes away. But for whatever is useful for the defender can also be repurposed or used by the attacker. As computations happen in the field, you can use these capabilities of resetting computations for suddenly resetting some sensitive computations. So that's similarly for test was used typically to identify bugs, and JTAG attacks and scan attacks that we showed a long time ago were essentially repurposing those beneficial capabilities. So that's my answer. Again, although you can have wrappers, you still have to verify them. You got to make sure that those wrappers do not have use cases where an attacker can benefit from them. And usually there are use cases. Does that make sense?
Yeah, it makes sense in a sense, there is no provable operating system and there is no provable secure hardware.
Yeah. So in that sense, there is a guaranteed job. So security is never going away in some sense, whether it is software or hardware or the system level thing.
These are all undecidable problems from a theoretician.
Yep. And we had this discussion the last time I visited you at IIT Bombay.
So any more questions?
If not, thank you so much for having me. And thank you for bearing with my schedule, moving schedule. I was initially not supposed to be in Scotland, but I was asked to be in Scotland. So here I am, St. Andrews. And thank you.
Thank you. Thanks a lot. On behalf of the participants, both who have joined online as well as offline, as well as the organizing committee, and of course, I'm part of the general chair of the conference, because of which we got you. We thanks you for your taking your time out despite your busy schedules. Thank you, sir. A big round of applause to you, sir, for this.
Thank you.
Thank you. Thanks. So now, let's move on to the paper presentations. The next theme of paper presentations is in the area of PKI algorithmic implementations. For that, we have Professor C. Murali, who is an academician and educationist with more than 4 decades of academic experience at various levels. He is a distinguished fellow of IEEE. He has worked as an expert for NBA, UPSC, and proficiency at IISc Bangalore, Indian Institute of Science, Bangalore. His areas of interest include computer networks, wireless network consultant, and he is also a board member for various educational institutions. He is a former vice president of IET in New Delhi. He has several awards to his credit. Welcome you, sir.
Just one. So you. So actually, I was not knowing I will be chairing a session only after the tea. Dr. Balaji came to me and asked me to be the chair. So basically, I am a communication person and with not much background about the security and other aspects. But I will try to do whatever is possible within my reach. And if you have to accuse me, because I came as a listener, I wanted to sit at the back bench, but somehow I have been pulled to the front bench. So as a teacher, I was used to always on the stage. Now, once again, I am going to have that type of work. There are 4 papers in this session. The first paper is by Anirudh Shipriya M, Dilip Kumar Barman, and KK Sondrapandian. We're going to talk on or present a paper on a hybrid hyperchaotic based dynamic key stream generator using Perturbenz process for public pre-infrastructure application. Let me copy. चलो बाहर है ना Good afternoon. I welcome you all for this today's event, which have been organized by the CCO office under the aegis of in this international conference on PKIA and its application. I take this privilege to be here to present my research paper, which is not recent, which is a couple of years back, along with my students. So what we have planned is that key generation. Basically, I have to concentrate more on the key generation than the key algorithms. So how do I going to generate a key so that I can be able to utilize for the transmissions as well as the encryption process. So as Ramesh was talking about, I've been working with the Ramesh and Huda. So we have been working more on the algorithmic side, how to generate a random numbers. So how to make it more random so that we can able to kill the encryption as well as in the hardware security level. So we have been working in the VLSI hardwares. So we basically work on the chip level fabrications
where we want to go for a two random numbers so that we can make a hash out of it. So how to do that activities? So these are the ways where we keep on working how to manufacture this key generation. So different ways of activating this for PK applications. So let me figure out how the outline of this presentation goes. What is a cryptography? Since the audience is basically from cryptography background, so you might be knowing what is a cryptography and what are the dimensions of cryptography. And we have been talking about more on the hardware and software security. That's what I've been putting a question on Ramesh. How about this hardware trojans? We cannot detect. So each and every device manufacturer says there is an end of life, end of service. It means the trojan is going to get active because there are always a passive and inactive trojans, which is going to enhance or which is going to get activated after a couple of times. So that's where the test and the thrust comes into picture. So this is where the hardware and software, still the hardware is more rugged towards security. And moreover, what are the research gaps and what are the how do we got the motivation out of it, and what are the proposed algorithms and how the results have been analyzed. Basically, what is a cryptography? It is a security essential by transmitting the information via the network, where the applications like military, government documents, online document transactions. So these are the ways where I can able to utilize my information security to be in a standardization. What is a cryptography? It's a study or method to protect the informations. I have to maintain my confidentiality, integrity, and the availability. So these are the ways where I have to make my trust in the platform. So that's what the PK application does, as well as in the quantum world. These whatever the existing traditional RSA, as well as the what Ramesh was also quoting it, and RSA and the hash is going to be cannot be able to retrieve back, or it's vulnerable. So these areas where we have to focus more on the dimension of cryptography, where we have to analyze towards symmetric or the post-quantum algorithms. These post-quantum algorithms under shortlisted by NIST, but still it's under process going on. And what are the attacks has been possibility, which has to be years and years will take to understand by the researchers to analyze each and every round, whether the trojans can be inserted or not. So these are the ways where we can able to go ahead with the applications. So I've been talking about the dimensions of cryptography, the way we substitute, the propose, the transposition, how the plain text can be moved out of it. These are the ways where the blockchain or the block cipher, the stream cipher can be taken into account, and the symmetric ciphers. As you all know, it's very strong in the post-quantum world. The only challenging is that how to transmit my private key. So again, there's a post-quantum communication has come out where we can transmit the key as well, and we can make a more secure channel of information, and it can be utilized for the PK application. So these are the different ways where I'm going to utilize my self practical private key. I don't require my public and private key to be integrated, because in post-quantum world, instead of going for a NIST post-quantum algorithms, which have been shortlisted recently, still there's a other channel of operation can be enhanced, where the PK application can be enhanced to that. This is what we have been analyzing of many years. What is the security basically? Whether it should be in hardware or software, how the trojans are inserted, how do I make it more rugged to my system? The hardware is more rugged than the software, because software runs on any platform, any operating systems, which can have a malicious codes. So these are the different ways where my software is vulnerable, more vulnerable, which cannot be activated or which cannot be stopped activating it. So these cryptographic algorithms, like which performs the general purpose of computing with the operating systems, and cryptographic algorithm can be easily updated. It's a flexible mode, but in hardware, it's not possible. You have to change the whole IP code, whole ASIC design. If it is a FPGA mode, we can able to reconfigure it. Otherwise, we cannot be able to continue it. So these are the small ways of application where the hardware and software security can be enhanced, and more vulnerable can be found out in the Trojan's point of view. So when we talk about these are the motivations why I want to go for a hardware security. So rather than the software security, our software security, I have to give for every time there's a patches. The patches knows where's the vulnerable, where we have to fetch it, where I have to stop it. That's why every time Apple phone comes up with the new updates to secure the modules in the cryptographic module, which you have inbuilt with the chip. So this is where the trojans, they keep updating so that they stop the movement of the data flow within the chips. So this is where every service provider, every OEM, every chip manufacturer has their own constraint towards the implementation. As you all know, what is a public infrastructure? So I've been discussing many times with this, the 2 day sessions. I've been working with for the last 7th onwards, we have been talking continuously about the PKI. The PKI solution is going to give my trust. That's what the PKI solution is going to implement, and it has been integrated along with the system to enhance more the element with my certifying authorities. So where the trust has been performed along with the certificate root certificate India, so that is CCA route India 2022 and 2040, which has been already existing in the market. So these are the certificates where the identity of the digital signature is identified as it has been trusted, has been maintained with the root. So this public key infrastructure, the public key security, basically public key infrastructure, basically the public key security. So where the security exists, where my integrity is maintained, where my authentication is integrated and integrity and non-reputation. So these are the facts where the public key security has to be maintained, and it has to be best suited to solve the business needs, that is infrastructure, where my certifying authority is going to enhance with my output, that it has to be utilized for this Indian ecosystems. What are the research gaps we have found? Basically, the non-linearity and correlation immunity in order to make the algorithm resistant to attack. So there are something like, if you talk about this existing algorithms where we started with the symmetric ciphers, why I went for symmetric cipher basically? Because asymmetric cipher is basically like the key management. They don't generate any algorithms, or they don't have new formulation of resistance to the attacks. Where symmetric ciphers, basically they have used the feedback functions. These feedback functions do not have a linearity. They have to go for the non-linearity for non-reputation process or to maintain the integrity in the systems. So these enhance the researchers to approach the empirical approach to get the gate complexity. So the moment I increase my new algorithm, I cannot compromise on my gate complexity as well as the throughput or the latency. So these are the main challenges that we have been facing out when we started moving towards the new research fields in the symmetric ciphers. So this enhances to get a larger key length. In asymmetric cipher, if you like RSA 4096 2048, if we keep on increasing the size of a key bit, the strength of the security is more. Rather, you have to increase the complexity. Again, the throughput. Again, everything keeps on increasing in the resistance to the bit enhancement. Same thing when you talk about the symmetric ciphers, when I'm keeping the larger length, when I have the safe channel mode of transmitting this private key, I'm safe. So this is where the post-quantum world, the Shaw's algorithm says, so we can able to manage my algorithm, manage my key length more secured rather than even in the public key infrastructure when I'm able to transmit in the post-quantum communications. So this is where the all implication comes with the new researchers, where we have to enhance the activity towards the, apart from NIST shortlisted algorithms or the post-quantum algorithm in the post-quantum world, the inbuilt with the generator. These generator you can decide. It's not, you don't need to go for a true random process or the new algorithm which is existing with the symmetric ciphers. This key management systems, which is going to have a flaws in 1 or 2 rounds, can be able to be easily identified with the Trojans. So when you insert a Trojans, any asymmetric ciphers, you can able to retrieve back the key. This is what the more implication in the symmetric and asymmetric ciphers. So why do you want to go for a hardware-based cryptography? The secure key generation, key stream of larger length with minimum number of stages, so that my gate complexity is reduced. I can increase the more throughput, low logic complexity of a nonlinear Boolean functions, low hardware complexity, and high throughput. This is what the main idea I want to take it forward, this hardware-based cryptography, so that I can able to achieve these at the shortest level of implication in the gate complexity. So what I want to achieve in this efficient algorithm, the architecture, and they generate a new non-recursive larger pseudorandom sequence to secure my privacy information with a low hardware complexity and high throughput. So that is what the goal of every researchers. We have to go for high throughput and low logic complexity. So when we want to go for these new algorithms, keep in mind always the attacker's point of view or the threat point of view. We have to analyze at every stage of information. So this will make us a more implication. The security of the system must rely on the security of the key, not on the algorithm. So this will show, this is the Shaw's principle 1883. So still it implies for all the symmetric keys such as well as ascertainment such as how the key has to be manipulated or managed. So, yes, sir. So the proposed algorithm basically utilizes the hypothetic systems which have unstable equilibrium points. These equilibrium points have been analyzed at every point of view so that I get a hypothetic system so that it's confusion mode. Basically, this confusion makes me to understand I'm able to generate my true random. basically I cannot, when I go for a true random, I cannot be able to retrieve. I should go for a pseudo random. But further, this hypothetical system will give me my more true random sequence so that I can have a larger length. So this is the algorithm steps, how we want to follow this nonlinear feedback shift register with the self-shrinking generator sequence. So this is able to achieve my the proposed hyperchaotic systems with these equations. So this is available in this paper. You can just have a flow of the hyperchaotic system follows this architecture with the nonlinear feedback functions. So when I want to go for the research and discussion, I have been not able to go through all the fault analytic analysis, cryptanalytic, because there is a shortage of time. So we have been doing it some of the Lefno exponents analysis, where the proposed algorithm is much better than the lambda, lambda 1, lambda 2, and lambda 4. So the moment I get the minus 15, it means I am able to achieve a stable equilibrium with the hyperchaotic systems. So the brute force attack, basically, it's the initial possible values of around 10 power for p dash at equivalent to 22 power 13. So this will able to have the initial value with the more key space cardinality of a nonlinear. I can able to achieve the stages of 2 pi n plus 13 p plus. So these are some statistical analysis which have been analyzed with the NIST test, randomness frequency, blockchain, the block frequency, cumulative, the run test, longest run test. So these are the every different analytic static analysis we have been able to operate where my probability value is more than the thing. Certain analysis cannot fall in true, that may not be able to succeed, but still we have been able to analyze for something like 1 lakh bits of sequence. So with this, I'd like to conclude. Any new sequence generator with this hyperchaotic system or any sequence generator, you have to make sure that your key is generated in a stable manner. It should not fall under any correlation sequences or the immunity or the fault analytics. So these has to be enhanced so that every key generation can be able to transmit between the two stages of information. So this how we have to be able to achieve our like a new sequence, and it can be able to take it to the PK solutions. So this is the one way where we can use it for the self-signing signatures also, which is a very closed environment where we can utilize for safe mode of transmitting the private key. It doesn't going to be in an outside market. So these are the ways where we can able to enhance before this post-quantum world comes into picture, and we have to be strengthen our own PK system. Thank you. So I have this is my final proposed methodology where I've been using my whole architectural design. So from the hardware point of view, I used totally in an FPGA board where we are able to analyze the transmission between the structures. So from analog to digital, digital to analog, the transmissions where I made one of the exemplar nuclear reactors where I cannot go inside or near to the reactors. So these are the places where I can able to utilize my applications. I can put a FPGA board or any hardware device. I can able to transmit in safe mode of channel. I can able to retrieve the data. So this is a small way of information. I have been proposing it out, and it has been working with some of the applications in my lab. Thank you. So any nuclear reactors, the data transmissions, they won't be able to transmit the data. Now, as of now, what they are doing is they are transmitting other mode. So when you want to encrypt the data at the same point of view, and you want to transmit, so this is the best way where you can have a hardware, internal operation, usage as a PK solutions, and transmit to in a safe mode of quantum communications or any other mode within the circle as self-signed signatures, and you can able to transmit.
But isn't it, for example, our own nuclear installations, they are technically secluded from internet.
Yeah.
And so why do you need such things?
I'm talking about the master to the slave,
Huh?
the master to the slave mode.
Uh-huh.
In that also we can able to secure the operational activity, because since they are in online mode also, so this we can make it in offline.
Our nuclear stations, they are never on online.
Online,
in
yeah.
my opinion.
It's like fully offline. That's what I'm saying. So fully offline solutions.
I think the whole thing is the process is an important thing. Like what happens in the election, electronic election.
That is also offline.
The process is the important thing. It is not one. If you give me the hardware device, I can hack it, but it does not prove that the election has been hacked. It's a process you have to see.
Yeah, the process is, yeah, that's true. That's what I've been talking about to Ramesh also, how we want to go for a Trojan reverse engineering. Yes. That's why hardware-based cryptography is still in strengthening its power. Thank you. Thank you. I request the authors to report to the time. You can take 12 minutes for presentation and 1 or 2 minutes for the queries. The next paper is on random number generation for PKIA using control Anderson PUA by Aditi Roy, Kokila J, Ram Subramanian and Shabika Begum.
Miss Aditi, can you start your presentation?
Yes, sir. Am I audible?
Yes, yes. Please just. So you have 10 minutes plus question answer.
Okay, sir. I hope my screen is visible.
Yes.
Okay.
You have to show full screen.
Yes. Is it getting shown?
Yes, now it is okay. Yes.
Okay. So a very good afternoon to one and all. Today I'm here to present my paper on random number generation for PKI using control Anderson Puff. So myself Aditi Roy, I'm a research scholar in the Department of CAC of NIT Trichy. So my agenda will be introduction, problem statement, literature survey, proposed the Puff, Anderson Puff, then the implementation details, the results, and I'll be then concluding with some references. So talking about why we start with random number generation. So the fundamental aspect of information that is being communicated must be protected to maintain the message integrity, service availability, and the data confidentiality. So to cope up with the security needs of internet technology, various security layers are added on top of the TCP/IP transport layer protocols. So this security layers uses cryptography techniques. The cryptography can be of two types. One is private key cryptography, another is public key cryptography. The former uses only one key and the latter uses two keys. So this public key infrastructure that uses two keys is a guideline which is having two keys for encryption and provides confidentiality and authentication. So here we can see in this diagram, the client is encrypting his or her message with a public key, and then the encrypted message is getting decrypted by this private key by the server. So here the public key needs to be stored in the client and the private key needs to be stored in the server. So instead of storing this cryptographic key inside these devices, we can have a special hardware structure called physical unclonable function. That is unclonable because it has no mathematical representation, transformation function or representation. It is a hardware security primitive that uses the manufacturing variations to generate random sequences output. So this can be embedded in the hardware and can be used whenever it is needed on demand. It can generate the outputs. The other important aspect of public key infrastructure is random number generation, because any implementation of a secure cryptographic key protocol requires a secure random number which can be used as a key or nonce or both. So in an ideal world, all random number generators would be based on unexpected physical processes, for example, thermal noise. But such systems are known through random number generators. But such systems are having some drawbacks, such as high price, a large size, and so slow generation of numbers. These drawbacks make them often impractical for use. So our proposed approach will be overcoming these drawbacks, as we are talking about using puff, Anderson puff. So here all the existing TRNGs will be discussed on the puff based TRNGs. So here in the first reference, SRAM puff has been used, where the randomness of the original SRAM power and values is fairly low. First, let me talk about this SRAM puffs. SRAM puffs works by using the flipping of startup values between different power on cycles. So next reference is also based on SRAM puff with combining hash function with periodic reseeding. But this has a drawback of large amount of memory. And the next reference is with based on RO puff. RO is string oscillator based puff that works by creating a self-oscillating circuit using statistical delay variations of transistors and wires in the integrated circuit. So it has identical ring oscillators, that is called ROs. Then the drawback is here worst entropy. Next reference is also this linear feedback shift register, where crossed SR latch and flip-flops are being used with linear feedback shift register. But this technique is also vulnerable to key recovery attacks. Next, again, ring oscillators are used, but as we know that a ring oscillator need identical ring oscillators to be placed, and fixed placement and routings are needed. So this needs hard macros. This is a drawback here. So RO puff with chaotic circuits are vulnerable to input-based attacks. That is shown in reference number 7. Then other references are again chaotic circuit with puff to generate the initial state. Chaotic circuits are this non-periodic oscillators that creates waveform that never repeats. So this with combination of puff, the use technique have this extra drawback of chaotic circuit implementation as it's analog based. So then logistic map algorithm, it is also a function that generates pseudo-random number generators that implementing a mapping function. The random numbers are generated. This also has the drawback of extra hardware. Then the double RO puff structure. Here also randomness is not good. And so the other tools are having hard macros and 2 extra error correcting mechanisms. Then why we used this Anderson puff? First, what is this Anderson puff needs to be discussed. So this first Anderson puff was proposed in reference number 13, which is shown here. There are 2 shift registers, and there is a carry chain which is having 2 multiplexers. From the shift registers, the initial values are given, which is opposite. If shift register B is having 1010 pattern, then shift register A will be having the opposite pattern. So this patterns will be acting as the select lines to both the multiplexes in the carry chain, and this output of the last multiplexer will be acting as a preset input, so that whenever there is a signal transitional hazards, that is 0, 1 or 1, 0 glitches that we have in electronic circuits, depending on that, the preset input will vary and the output will vary accordingly. So this depending on this hazards, puff responses are generated. The puff's advantage where its use of within the FPGA computer aided design flow and its small silicon area. We are not using any extra circuit here. we are just utilizing the already available that logic cells in the FPGA circuit. So the next, there are modifications on Anderson puff, where in reference number 14, authors use NOT gates with flip-flops instead of shift register, so that puff can be placed into other slices. Slices are the logic, the lookup tables in FPGAs are having configuration logic blocks that are consist of slices. So this Anderson puff does not depends on delay produced by the fast carry chain as well as the shift register. So in 15, reference number 15, authors suggested to employ the XOR gate, because there is XOR gate in the carry chain that can be used. So in reference number 15, they have used OR gates as well as the multiplexers. Then additional path will generate sufficient delay because of the XOR gates. Then in the reference number 16, extra multiplexer were added to combine the challenge ability. But none of these papers investigated the randomness properties of the puff. So we modified this Anderson puff design, where you can see this we are having two shift registers and two carry chains. In one carry chain, 4 multiplexers, and with each multiplexer, one XOR gates will be there. So we are using this 2 carry chains, and there are 2 extra 2x1 multiplexer to add this challenge ability to the circuit. So the connection is in the design are as follows. The output from the shift register 2 is connected to the top shift register is connected to the select pin of the top multiplexer, that is called M5, and the output from shift register 1 will drive either the M1 or M2. So this driving of either there is a choice of selecting either M1 or M2 here in the multiplexer by using this extra 2 multiplexers, which is deriving by this shift register 1 output. So when the challenge input is 1, the shift register 1's output is directed to M2 select pin. Alternatively, if it is 0, then M1 is driven by the shift register, increasing the delay chain. Again, in the top part, by using the XOR gate output and fixing the next select input of the bit delay width has been increased, the generated signal is carried till M5, the last level multiplexer, and then M5 is generating the preset input to the D flip-flop, and here from the D flip-flop we are getting the response bit. So why such design we have chosen? Because there are 4 XOR gates with each block of carry chain. We wanted to utilize the FPGA fabric logic cells. So one of the there are 4 XOR gates with each carry chain block, and one of the XOR gate is used in the design. The additional path will generate, because such a way that additional path will generate sufficient delay. And the advantage of using this control signal is to have the choice of adding more delay or not. Here to add the multiplexer M1 or M2, whether we are driving the multiplexer M1 or M2, because here the output of the shift register 1, depending on the choice select line, challenge select line, it is driving either MU1 or MU0. So the output of MU1 or MU0 is driving M2 and M1. So like this, we are having the choice of adding more delay or not. So the shift register 1's output is directed to M2 select pin, and when CH is 0, M1 is driven by the shift register, increasing the delay chain. The implementation details are as follows. The proposed puff has been implemented on 2 kinds of devices. One is Zinc UltraScale plus MPSoC, which is high-end board of 16 nm technology, and another is Zinc 7000 series associate chip Z board, which is 16 nm technology, Both of these are having different applications. Z-board is having applications such as advanced driver assistance system, medical endoscope, professional cameras. And MPSC boards is having multiple cores where it is having also real-time processing processors, and it has it has application of next generation advanced driver assistance system, and then 5G wireless, and then industrial IoT. So the complete puff circuit was designed using Verilog HDL code, and no routing or placement constraint was needed in this design. So we have no constraint of fixed placement of routing. As mentioned, the proposed design make use of the configurable logic block resources that are available in the FPGA fabrics by Xilinx. Yes.
Please conclude.
Yes. Okay. So these are the results. NIST test has been performed. This, if p value is larger than 0.1, so sequences are distributed. So we are having random values. These are resource utilization. So as we can see here in the result discussion, in comparison with the other existing TRNGs, our proposed work has shown less area footprints than other existing TRNGs. So concluding with this, I'll conclude like the motive of this work was to propose a good random number generator which does not take up more hardware resources. Towards this aim, the control addressing puff has been suggested, which can be utilized for cryptography applications. So it has been implemented using Xilinx Sync SoC device, and we ran NIST test, correlation test on our puff to ensure its randomness, and passed most of the tests. The comparison of utilization of resources has been shown. Okay, thank you. These are the references. Thank you. Any queries? Yes, I have done NIST randomness test.
Any questions or queries? There are no questions. Thank you, Aditi Roy.
Thank you, sir. Thank you.
The next paper is on experimentation of usage of PQC algorithms for e-sign by Pawan Gloria, Ankita Bhargava, Shrikant Shailada, N. Subramaniam, Janavi Bodhankar, and Ajay Kumar.
Good afternoon, everyone. So I am Srikant from C-DAC Pune. So we have been working in the project of eSign. So we wanted to implement the PQC NIST approved PQC algorithms and test how it can be implemented in eSign process. So first I wanted to know, say simple things about what are the effects of quantum computing in present scenario. So at present, we use RSA or ECC mainly for eSign process. So by introduction of quantum computing, it can use Shor's algorithm or Grover's to break and or we can say weaken the present algorithms such as RSA, ECC, and AES. Here Shor's uses like prime factorization. It can break prime factorization mainly. So which affects RSA and also ECC. When it comes to Grover's algorithm, it actually makes the search algorithm faster. So usually for AES 128, it takes 2 power 128 bits, 128 iteration to find the solution. But when it comes to Grover's, it can like it can like square it off n times of complexity. So to overcome this, post-quantum cryptography has been established. So post-quantum cryptography is nothing but like cryptographic system. It has to be protected against classical and also quantum attacks. So it uses presently it uses lattice-based cryptographies, code-based, hash-based, and multivariate-based, and etc. So NIST has started this standardization of PQC algorithms. So it actually has 5 levels of security based on how much it can break AES 128 or SHA 256 and AES 256 and AES 384. So these are level security levels from level 1 to level 5. So based on that, whoever submitting the papers have to implement either 1, 2, 3 and also in 4, 5 security level. So first I wanted to introduce about eSign. So eSign is an online platform where a user can get electronic signatures done for his documents. So in this process, we have mainly three parts, which are application service provider, eSign service provider, and eKYC service provider. So in application service provider, user can provide his document to be signed. So application service provider actually converts this document into hash and sends the hash value to eSign service provider. Then eSign service provider authenticates the user by getting eKYC details from eKYC service provider and also generates key pair on behalf of the user. So here we can use ECC or RSA to generate the key pair. So then we generate CSR and send it to CA to get it signed. So even for CA we have key pair which can be RSA and ECC. So here then the our CA sends back the digital signing certificate back to eSign provider in PKCS 11 format, whereas eSign service provider includes this hash and the certificate in PKCS 7 format and sends back to the application service provider. So our idea is to like how we can which algorithms can be used in place of ECC or RSA for generating key pairs on behalf of user and also for the CA certificate. So usually in this third round, actually Crystal, Dilithium, Falcon, Sphinx, Gems, Picnic and Rainbow were selected, but after completion, only Crystal, Dilithium, Falcon and Sphinx were selected. So among these, Crystal, Dilithium and Falcon are lattice based and Sphinx is hash based. So Crystal Dilithium is a lattice-based algorithm. Its structure is based on fiat chamber with aborts, which is like non-interactive zero-knowledge proof. And the strength of this algorithm depends on module learning with errors along with the short integer solutions. So it has mainly 6 variations, which are Dilithium 235 and Dilithium 2 AES, 3 AS and 5 AS. So in Dilithium 235, shake is used, whereas Dilithium AES 256 is used to in some mathematics followed during the key generation or digital signing. So in Falcon uses GPV framework, which uses hash then sign method, and its hardness is based on short integer solution problem over NTRU lattices. So when it comparable to other lattice based algorithms, Falcon provides smaller shorter signature size with the same NIST security level. So in a NIST in Falcon we have two variations, which are Falcon 512 and 1024. So here Falcon 512 provides NIST level 1 security, and whereas Falcon 1024 provides NIST level 5 security. Another contender, another finalist was Pinks Plus, which is a stateless hash-based signature scheme. So it has a multiple tree levels, whereas we have a parent node and it has child nodes, and every child node again has some child nodes. So in that way, the tree is a hypertree with multiple level of tree structures, and then each child node is uses OTS, which is one-time signature scheme, whereas the bottom level child uses few time signature schemes, which so that it can become stateless. If we go with only a one-time signature scheme, it will be stateful algorithm. So even here, Sphinx provide multiple variations, which are using the hash algorithm, very different hash algorithm, such as SHA-3, SHA-256, and Haraka. And again, these variations have sub levels depending on how, like, if it is a simple, depending on the size, and also of fast operation, and simple or robust. So these have the variations, and also depending on the NIST security level, it provides NIST security level 1, 3, and 5. So I am extending these algorithms with respect to final round. So we have Picnic and also Rainbow for the final round, but which could not get shortlisted. So in Picnic uses zero knowledge proof along with hash functions and block ciphers, whereas Rainbow uses multivariate algorithms where it depends on it follows unbalanced oil vinegar structure. So even it provides security level 1, 3, and 5. So what our experimentation was, developing a QSign platform where we use OpenSSL fork, which provides these NIST finalized algorithms using OpenSSL. So in the second point, you can see the algorithms which are present, which were present inside the OpenSSL fork. So we used these algorithms to generate CSR and also to sign these CSR using a CS certificate. So we also made we also have, like, to analyze the performance, we have a page where for given number of iterations, how much time does the CA take to sign the paper, sign the CSRs. So these are some screenshots of our QSign platform, and these are the results where for I think 25 25 number of times it has to sign. So how much milliseconds of time does every algorithm takes? So here we can see Dilithium and Falcon take less time when compared to other algorithms. So these are some comparison table where we have security level, public key size, private key size, signature size, and signing time for each signature. So for usage in the eSign, we were thinking to use with the NIST security level 3 and above. So from these algorithms, we were considering only Dilithium 3.5 and also Falcon 5 because of these security level, and also when it comes to signature size and signature signing time. So we are like thinking to consider Dilithium 3 and Falcon 1024 whenever they are available for in terms of HSMs, because we usually use HSM to generate key pairs for the user and also to sign the CSR certificate. So in our future aspect, we are thinking to provide PQC algorithms in complete eSign flow, where a user can upload the PDF and we can embed this digital certificate using this post-quantum algorithms inside that PDF. Thank you.
How the timings compare with RSA or ECC?
In actually in the what do we say, structure, it makes the difference, like what type of OID it provides. So it will be reflected inside the certificate structure. Sorry, what? Yeah. When we embed the
bank says it has been e-signed, right?
Yeah.
So now how do I check?
Actually, in terms of PDF, when we get e-signed, you can see that in Aadhaar we get green tick or question mark. So when we open that green tick, like click on that, our certificate gets opened actually. So inside that certificate, user details, CA details, and also I think CCA details also, we can look into the details in the certificate. So it proves the authenticity of the user and also signer.
No, I have asked a question, how the timings compare with RSA or ECC?
Oh, okay. Actually, we did not compare with the RSA and ECC right now. We are comparing only these algorithms, like PQC algorithms at present. Because RSA, ECC are quite.
But it will be interesting to know, does it take a lot of time to put a post-quantum signature, or that is, what is the position?
Actually, RSA and ECC take less time when compared to these PQC algorithms.
No, by how much? That is the question. Okay.
Oh, how much? We did not compare actually.
Okay.
Yeah. Thank you. Thank you.
Okay. You showed us, I think, falcon, picnic, rainbow, and species, right?
Yes.
So this is being like used for signing the certificate, or it can be used even for signing the document.
Signing the document itself. We if e-sign flow itself is signing the document.
Means you will be signing the hash of the document, right?
Yes.
Okay. So in the signature in the signature response, when we get when you submit it, so is there any change in the response of the signature, like the size of the response? Anything you have been identified?
We actually right now we did not include these algorithms in e-sign flow. That is what I mentioned in future scope. We are thinking to like compare again with the RSA and ECC with the present Dilithium 3 and Falcon in the e-sign complete flow. Right now we did not make any comparison with e-sign complete flow.
Okay, thank you. One more last question. What version of OpenSSL you have been used to do this?
It is actually OpenSSL for 1.1 something.
Okay. Yeah. Thank you.
Thank you, everyone.
Are there any HSMs that support the PQC algorithms?
Right now, they are like, what we know is there are some manufacturers, they are ready to provide, but not complete HSM. Like even they are like implementing the said algorithms from C program into hardware, and they are ready to provide it. But officially, they are not there yet.
They are not available.
Okay. Thank you, everyone. Ruby, can you present?
Yes, sir. Is my screen visible, sir?
Yes, please proceed, and please stick to the timing.
Okay, sir. A very good afternoon to all. I am Ruby Mishra from NIT Rourkela, Odisha. I will be presenting the paper titled FPGA-based high-throughput substitution box architectures for lightweight block ciphers. Co-authors are my supervisors, Professor Manish Okade and Professor Kamalakant Mahapatra. So this is the outline, introduction, motivation, and then I'll be discussing regarding the general architecture of lightweight ciphers, then the proposed S-box architecture, then we'll discuss the implementation and results, and then I'll conclude with the future scope. So recently, the design and implementation of encryption algorithms, both on hardware and software platforms, has been quite significant in the research domain. Basically, a dedicated hardware definitely improves the performance of crypto algorithms for a specific target applications. So mapping an algorithm to a optimized hardware is a crucial task which has to be taken care by the design engineers. Basically, the hardware implementations can be carried out in two approaches. That is, either we can go for FPGAs or ASICs. FPGAs are field programmable gate arrays. Basically, for prototyping our designs, we use FPGAs, and it is a faster method of bringing the concept to hardware. And if we go for application-specific ICs, these are custom ICs, which need to be carefully observed by the designers. And before fabrication, we have to take care about the optimization as well as the security aspects of the design, which opens the area for hardware security in this aspect. So the target is to design a compact and high throughput architecture for target applications. And we have chosen symmetric lightweight primitives because it occupies less area and performs well in terms of area, throughput, power, etc. So the motivation behind choosing lightweight algorithms are we have seen that there is a significant surge in the demand for IoT-based consumer electronics, and there is also a thirst for computation anywhere and at any time. So coming to the requirement of these IoT devices, we want that the device should be smaller in size. Only then it will be mobile or portable. Device should communicate with each other in the IoT environment, and also with the user. It should talk with the user so that we can call the device to be a smart device. Again, for this, we need a connection, and the choice is a wireless connection. Also, we want that the battery life of the device should be longer, and it can be achieved only if the power consumption is optimized. So apart from all these requirements, we also know that the devices deployed in the IoT environment are continuously involved in handling sensitive data. So this raises the concern for privacy and security. And keeping all these things in mind, the conventional crypto solutions may not be suitable for IoT devices. And hence this has led to the emergence of lightweight cryptography, which we'll discuss further. So the design considerations for lightweight block ciphers are, we need to choose or design the lightweight block cipher in such a way that they should provide security which is sufficient to the target applications. So if we consider the research domain, we can either alter and analyze design, or optimize an existing cipher, or develop a completely new cipher. We have, in this work, we have optimized an existing cipher. In order to evaluate the lightweight block ciphers, we evaluate in terms of area, power, throughput, and energy. And it depends on the factors like the individual architectures of the submodules present in the encryption algorithm. And it also depends on one of the crucial block, that is whether it is a substitution permutation network style or whether it is a Fichter structure style. Then the dependency is on the frequency of the clocks, which is used to drive the circuit, because it affects the performance of the circuit. Then comes the key scheduling process, which differs from algorithm to algorithm, and it solely affects the performance of the design. Again, for area consideration, we need to keep in mind the block size and the key size of the encryption algorithm. In this work, we have chosen clean, Midori, and Gift lightweight ciphers for evaluations. And now coming to the general architecture of lightweight ciphers, we have chosen a 64-bit data path, and here the input plain text is of 64 bits along with the output ciphertext. We have an internal module, that is a key scheduling module, but the key bits are different as mentioned here for the individual ciphers. And we have the another internal module, that is the substitution permutation network, where the substitution layer is a nonlinear layer and the permutation layer is a linear layer. We have focused on the substitution module because it comprises of the S boxes, and these are crucial for security as well as for the performance of the ciphers on hardware platform. Again, this process of mixing of plain text with the key bit along with passing it with the SP module occurs for a certain period of time called as round operation, and the number of rounds are stated in the literature of these algorithms. And now coming to the design considerations for the SBox model, as I said, we have focused on the SBox, the non-linear SBox model, and here for a 64-bit data path, we have 16 SBoxes, and in most of the lightweight ciphers, we have 4-bit SBox, that is 4-bit input and 4-bit output, and this is more beneficial in terms of area and delay as compared to the 8-bit SBoxes. Then coming to the architectural variants, which are options available for us to design an SBox, are the lookup table based, which are already done by the existing works. But the problem here is the designer has no control over the area and performance, because if a table is fitted in the code, the tool automatically maps to the architecture of the device. Then we have the logic functions, the Boolean functions, which need to be obtained from the SBox. And the problem here is we have a delay. The delay is more, the critical delay is more in case of gate-based design. Coming to the mux-based design, which we have proposed in this work, here the delay has been considerably reduced because it efficiently maps with the FPGA architecture. And there are other forms of architecture options like composite field, which can be seen in case of AES, but again the area consumption is more in this case. Coming to the algorithm for proposed for the SBox architecture, here we have the input to be as input bits as I0, I1, I2, and I3. The output functions to be generated are O0 and O1 and O2 and O3. The idea here is to fix the LSB bits as the select lines, and here we have used a 4:1 mux for efficient mapping. And then the logic functions are generated with the help of the MSB 2 bits, and after minimize it and reuse the minterms wherever possible. Now coming to the logic functions, from the algorithm we have generated the logic function. This table 2 represents the logic functions for mux-based design. We see that for the gate-based design, which are obtained directly from the Boolean functions, even if after minimization, we see that the number of literals, if we take the example of O0I, the number of literals has reduced in case of mux-based design, that is from 9 to 6. But in case of also the number of logic operations has also reduced in case of mux-based design. Similar observations can be seen for other output functions also. So this is a block diagram. As I said, the logic functions are initially generated and then fed as input to the muxes. Here we require 4:1 muxes to generate the output logic functions. Now we have chosen FPGA as the implementation platform, and we have implemented all the designs by constraining it to 13.56 megahertz, which is quite appreciable for RFID applications. The parameters are slices, LUTs, and flip-flops for determining the area parameter, and the maximum operating frequency is denoted as Fmax. These are the FPGA devices, and here we see that for GIFT, MeitY, and Clean, for the case for mux-based approach, we see that there is a significant reduction in the number of slices due to efficient mapping, and there is a maximum increase in the maximum frequency of operation also. Similar observation is seen for MeitY, and for one of the cases for Clean also, we find that the area has been reduced along with the maximum frequency of operation has increased. Coming to the performance, we have calculated the throughput. And at maximum frequency and also at the RFID frequency, and the power and energy, power is determined from the tool and energy is calculated as Fmax. So here we see that the throughput at Fmax has also increased, and we see that the energy has been considerably reduced. Also for MeitY and Clean, we see that there is an improvement approaches for the said devices. And now we have tried to design a prototype for the Clean architecture so that it can be used for healthcare database. The idea here is to embed a security module in the healthcare gadgets or the wearables which we use, which definitely which are used in the consumer electronics, and they are dependent on the RFID frequency. So the idea here is to convert the raw data to a test data and then pass it through an encryption process, which will include a lightweight cipher. and then store the data or transmit the data. And this will be possible only with the key present with the authenticated entities. So we have collected the data from the Fitbit data set, and these are the parameters age, weight. We have taken the input as the plain text as age parameter, and age_e, for example, is the ciphertext or the encrypted input. So here we have taken the key bit to be fixed, and now we have validated the results in Nexus 4 DDR, and we see here that after the done signal is high, that is the encryption is completed, and we get this output. And if we, this is just the LSB to MSB, so if we do the reverse round, it will be 1100 1101, that is CD, which is obtained in this for identity 1 for in this table. So so in a summary, we can say that the designers has to take care while designing the lightweight ciphers, because there are always trade-offs. And whenever we go for definitely, if we go for more number of rounds, we may improve the security, but again the performance is hindered. Again, if the key bits are increased, definitely the security increases, but we have to take care regarding the area of the cipher also. If, for example, for architecture, if we go for a parallel architecture, definitely the performance will improve. But again, there can be more area, and this increases the cost. So with this, the designers should take care and should decide which parameter has to be optimized depending on their target applications. So with this, I can conclude. With this, I conclude that the designs, with the conventional designs of modifying the architecture like serial and parallel, instead of doing that, we have tried to modify the S-box architecture, because these are repeated again in the substitution layer, and it significantly affects the area and throughput of the design. And we have also constrained it to 13.56 megahertz so that it is suitable for IoT applications. And the future work is to implement the proposed designs on ASIC platform, and we also intend to construct a lightweight, secure S-box for in the future. So these are the selected references. Thank you. Okay. Yes, algebraic normal form can be used, but again it increases the delay if we go to the microarchitectural level. It increases the delay of the design, overall design.
No, but that is your conjecture. Have you done it? That is the question. No, what you have to write expressions for the 4 outputs of the S box, and then synthesize that, and then you will know whether area is required is more or delay is more.
Yes,
Or fault
I have tried that, because this gate based, which I showed in this slide, in table 1, the input functions which I was showing, here which I showed is the direct Boolean functions. We have used all the logic gates, mixed gates.
No, direct Boolean functions are not optimal, because using Karnaugh map you can design 1000 designs. Okay,
yes, sir,
but
yes,
algebraic normal form is only one solution you get, and that generally people implement because supposed to be the most optimal. Anyhow, don't worry.
Yes, sir. But for FPGA, we have moved for these marks based designs.
Okay.
Okay. Thank you. So I will request our senior director Sri B.S. Bindu Madhva to felicitate the session chair.
I was telling you earlier, I am not a person on security and other aspect. The only thing I want to tell you is it's a connected world with more than 7 billion people on Earth. And it is expected by 2025, at least 7 devices will be connected on an average to each person. Means we are expected to have at least 50 billion connected things with human beings So that's what is expected, and enormous amount of data is going to come into picture. And then you can imagine what will be the amount of security and other aspects needed. And once again, with 5G and artificial intelligence, with IoT complementing each other, coming into picture, the enormous amount of, that is a wireless world once again, where security is going to play a bigger role. And most of you are youngsters and young engineers and maybe students and young engineers from various parts of the country. So it is really a challenge for all of you. And once again, you can never have a perfect security. The basic thing of ethics is needed. Unless we have got human beings ethics, the security may not be solved at all. So this you have to keep it in mind and have a better future so that you'll be having a better, secured, connected world. Thank you.
Thank you, sir. So we'll start with our next session of paper presentations. It has two papers. The theme is security analysis and validation. And I will request Sri Deepak Kumar from the office of CCA to be the session chair for this paper presentation session. Sri Deepak Kumar is a scientist in office of CCA. His educational qualification includes AMIE, MSc, and PG diploma in information security. He has almost 15 years of experience working with DRDO and now in the office of CCA for the past 7 years. And he has been looking into various aspects of PKI and digital signature. Sir, over to you.
Thank you, Anup. Thanks for the introductions. So this will be the last session before the lunch. So as Anup told, there will be two papers in this session. So the first paper will be presented by Divyashri Guha, Debashish Bera and Bhaskar Bishwas. And the title of the paper is Security Analysis of LDPC Code-Based Encryption. So I invite the presenter to present the paper.
Thank you, sir. Am I audible?
Your voice is very low.
Is it okay now?
Yes, a bit better. Please share your screen.
Yes. Okay, a very good afternoon to everyone. Opening with a brief introduction, my name is Divyashri Guha and I'm presently researching on the topic of cryptanalysis of LDPC code-based crypto system under the guidance of Dr. Debashish Bera of the Indian Institute of Information Technology, Kollam. So he is also the co-author of this paper titled Security Analysis of LDPC Code-Based Encryption along with my fellow colleague, Mr. Saurabh Biswas. Without much further ado, I would like to resonate what Shrikant Sailadas said, that the need for post-quantum cryptography, also which is known as quantum resistant encryption, is basically driven by the increasing belief that quantum computers which have power to break the current public key infrastructure cryptography will be available within a span of maybe 5 to 10 years. So in lieu of that, NIST started a competition to select standard post-quantum encryption algorithms back in 2016. Now, NIST's call for proposals identified 3 basic aspects of evaluation criteria.
So the aspects are basically security, cost and performance, and thirdly, algorithm and implementation characteristics. So based on that, we are basically focusing our research on a quasi-cyclic low-density parity check code-based public key encryption scheme, which is known as LedaCrypt. And LedaCrypt had made its way to the second round of the competition by NIST. So before going to LedaCrypt, I would first like to give a brief background on code-based cryptography. So in the search for good alternatives to classical crypto systems, where
I think you have to speak a bit louder. Not able here.
Okay, sir, just give me 1 second. Maybe there is some problem with the mic. Sir, is it better now?
Yes, yes, now it's definitely better. Okay, go ahead.
Okay. So as I was telling, with number theory as the backbone, the good alternatives to classical crypto systems, code-based systems has emerged as a strong competitor for post-quantum cryptography. Now, the reason behind that is that decoding a random linear code is a non-deterministic polynomial time problem, and that would not depend upon the computation power of the adversary. Now, public key crypto systems are mainly aimed at ensuring secure data transmission over an insecure channel. And forward error correcting codes, basically what is the basis for code-based system, they are concerned with minimizing errors when sending data over a noisy channel. Now, data sent from one point to another not only needs to be untampered from malicious interventions, but they must also not undergo changes that might be attributed to the drawbacks of the communication medium. So it was back in 1978 when McAleese proposed a public key crypto system based on coding theory, wherein he found the interrelation between public key crypto systems and forward error correcting codes. The main idea of McAleese was to send more information or redundant information through the channel than what is actually needed. Now, if this redundancy has a structure, then it would be exploited in order to correct possible errors that might occur in the data transmitted. Now, code-based cryptography uses this very concept. The original McAleese system used GOPTA codes as the component encoder, which has a very big drawback, which is that it results in large key sizes, and hence it is difficult to actually implement for real-life applications. This actually forms the basis of our study on quasi-cyclic low-density parity check code-based encryption, which is the LedaCrypt. Now, LedaCrypt has McAleese as well as need-editor crypto system as its basis, as its basic building block. Now, the main advantage of using QC-LDPC codes instead of GOPTA codes is that these codes have sparse and circulant nature for the parity check matrices, which allows a considerable reduction in the key sizes. And in turn, this actually renders to efficient decoding techniques. So hence, I proceed to discuss in brief the McAleese crypto system. So it basically comprises 3 algorithms, that is the key generation, the encryption, and the decryption. For the key generation, the receiver first chooses an arbitrary GOPTA polynomial, say Gx, with a degree t over the field Fn2. So this is a field of order 2, and it has got n elements. Now, using this, the receiver will compute something which is the generator matrix. It is a k cross n generator matrix of the GOPTA code. And further, 2 other matrices, S and P, one is an invertible matrix and the other is a permutation matrix, will be chosen by the receiver. Armed with these 3 matrices, he computes G dash, and the public key would be the G dash. So G dash is SGP, and T is also part of the public key. The private key consists of polynomial Gx, the original McAleese, matrix G, that is a generator matrix, along with the S and P matrices. So the sender can encode his or her message. So it is a k-bit message M by computing mg dash plus E. So M is the message, multiply it with the public key, and the error E is basically the random error vector which has been added for transmission. The decryption part, the receiver will use his permutation matrix to compute Y dash. So Y dash is the Y, the message that actually was sent, P inverse. So it is basically mg dash P inverse plus P inverse applied also on the error vector. So likewise, we get msg plus EP inverse. Now, EP inverse is the actual error that has been added, since P is the permutation matrix. So from this, the message M can easily be recovered. Now, any adversary or an attacker has two basic attacks to try. One is to recover G from the public key G dash so as to be able to use Patterson's algorithm. So the problem with this is that this is difficult because if the sufficiently large sizes of n and t, so if n and the number of errors and the actual parameter n is quite large, it is there are a lot of possibilities of the values of S, G and P. So for McAleese, there was around 10 to the power 149 types of GOPA polynomials that could be possible. So that is not possible. So this attack is rendered not possible. Apart from this, another attack could be to recover the message M from Y without learning G. Now, this is also a difficult problem because this would involve decoding an NK arbitrary linear code in the presence of T errors, which is, as I said, this is an NP complete problem. So this renders the attack infeasible as well. So next we proceed to describe the QC LDPC code-based McAleese. So LEDACrypt basically, it involves a quasi-cyclic code C of the order Pn0, Pk0, where the Cnk is basically a binary code which maps a binary sequence from 2 to the power k field to 2 to the power n field. The generator matrix and the parity check matrix of the quasi-cyclic code is basically a collection of n-naught number of P cross P block circulant matrices, where block circulant matrices are matrices wherein every row or column can be obtained by circularly shifting the very first row and first column respectively. So just the knowledge of one row or one column will enable us to generate the entire matrix. And the information length for QC LDPC is K0, which is P times N0 minus 1. Now, the parity check matrix of LEDACrypt allows for efficient decoding techniques, which are called bit flipping decoding. This is allowed for the sparse, this is applicable for the sparse nature of the QC LDPC code. Now, the BF decoding, the bit flipping decoding algorithms, it relies on the notion of flipping the bits in the error affected code word as long as either an all zero syndrome is obtained, which indicates the all zero syndrome indicates the removal of all errors from the code word bits. Or it would stop and if it reaches a predetermined number of iterations, say I max. The public key of QC LDPC code-based McAleese looks somewhat like this, where Z is a P N0 cross P N0 identity matrix, which is composed as a diagonal block matrix, wherein we have N0 minus 1 replicas of the identity matrix I for I from 0, and M is constructed by L N0 minus 1 inverse into Li. Now this L is nothing but the private key, basically of QC LDPC based McAleese, which is actually computed by combining a block circulant matrix H and a quasi-cyclic matrix Q. Okay, so this would give us the private key, and the public key would be a combination of the inverse of the last block of the private key along with the other blocks of the private key. Now, next we proceed for the security analysis. Now, different types of cryptanalysis are possible on this type of QC LDPC code-based system. My main focus is on information set decoding, and Information set decoding dates back to 1962, where it was invented by Eugene Branch, and later on it was improved upon by a lot of scientists, and I'm mainly focusing on the improvements by Lee and Bricken and Stern in the year 1988, and finally it was revisited recently, if I may say so, in 2015 by May and Ozerov. Now, before going into information set decoding, what I have done is how this can be applied for the attack on QC LDPC based MAC ALIS crypto system that I have discussed. So basically, a key recovery attack is possible by exploiting information set decoding. So given the public key of MAC ALIS crypto system based on QC LDPC code, a passive attacker may wish to perform a key recovery attack. So he considered two distinct integers, I0 and I1, and a matrix P is defined as follows. The matrix is P cross N0 P. So A is basically a matrix where there are N0 number of P cross P circulant blocks. And it has got a certain pattern, speciality, that is every block of A is 0 except two blocks, Li1 and Li0. So Li1, AI is Li1 if I equal to I0, and AI is Li0 if I equal to I1. From this particular form of the matrix, it is found that if we multiply this with our secret matrix L that we were talking about, so AL transpose would actually give us a 0. So what we have found is that A is the null space of our private matrix, this private secret parity check matrix. So this actually goes to show that the rows of A are code words of C. So for a matrix to be a parity check matrix of a code word, the code must be the null space of that matrix. So this is driven by the logic that if H is the matrix and C is the code, and C are the code words of the particular code, then H into C transpose would give us a null. So this actually goes to conclude that the rows of A are code words of C. Now, as each block of Li is a circulant matrix, as it has to be since it is the multiplication between H and Q, thus C must have a minimum distance of 2B. Now, if an attacker is able to determine one of the rows of A, then he will be able to recover two blocks, Li and Lj of the secret matrix L.
Hello. Yeah, please conclude.
Yes, sir.
Please conclude faster.
Okay, sir. So this is the basic key recovery attack that would be exploited by ISD. So ISD basically we are using ISD to find low weight code words. So for that we actually perform certain calculations or computations over the given parity check matrix. So instead of using the parity check matrix H, what we do is we permute it and we pre-multiply it with a matrix U. So that gives us H dash. So H is transformed to H dash, and the similar permutation is allowed on C, the code word. So C gives us C dash. So P is chosen, that is, a permutation is chosen in such a way that the first R columns of the transform parity check matrix are made independent. So H basically becomes H dash, which is of the form X followed by the identity matrix of dimensions R cross R. So this very form is exploited by the different ISD techniques. So the technique by branch, what it does is that it assumes that the permutation that we are applying on the code word, that permutation takes all the weight, the entire weight W of the code word in the last R positions, and the first K positions are kept as 0. This has been little improved by Lee Brickell, where Lee Brickell allowed P number of ones to occur in the first K positions, leaving W minus P ones in the last R positions. Stern further improved the timing on this by dividing the first K positions into two halves, that is K by 2 and K by 2, and P1s are allowed to occur in the first K by 2 positions, P in the next K by 2 positions, and the last positions will be W minus 2P. Ozerov actually does the same thing as done, but instead of just randomly looking for the set of P1s, it actually involves nearest neighboring technique in order to make the search faster. So here I have a table where the different ways in which the code word is broken up has been discussed, and the stopping condition. So basically this is a representation of the algorithm of the different ISD techniques. So after this, we proceed to perform our results and analysis. So on the basis of the data available with us and the parameters that are provided by the LedaCrypt authors, it has been found that as expected, LibRickle has a lower cost, and LibRickle has a higher cost, sorry, and the latest one, that is Ozerov, gives lower cost. So this, in short, is the security analysis that has been done by us. So on the basis of the three information set decoding algorithms, and this is the results that we have found. So I would like to acknowledge my fellow researchers, Mr. Shantan Chatterjee and Dr. Bhaskar Biswas, and this work actually is a part of the project sponsored by SAG DRDO, and I thank Mr. Harshdeep Singh, the scientist of SAG DRDO, for valuable inputs. Thank you, and I would like to have some questions if you have.
Yeah, questions, any questions? So if there is no question, then we may move to that
I had one question. See, what I wanted to know, if you look at this expression for Y, it is same as in ring learning with errors. Or, even NTRU, Y is AM plus E. E is errors and some message, and A is a matrix. Now, what is the relation between McAleese and RLW? Is there any relation?
Sir, will you please repeat relation between McAleese and? Hello, sir. Hello, sir.
I'm not getting it.
Is there a similarity between McAleese and ring learning with error because of
Yes.
So basically, the LedaCrypt, it uses the basic idea of key generation, encryption, and decryption processes of McAleese. So
The audio is not audible.
is it better now?
Yes.
Yes, sir. What I was telling is that LedaCrypt actually uses the key generation, encryption, and decryption techniques, the basic techniques of McAleese. They have been modified.
No, that I know. See, what I am asking is just out of academic interest. Is there any similarity between ring learning with errors and McAleese? Because finally Y is made up of some errors and message and some matrix. This matrix in the case of McAleese is different. So I'm just curious to know whether anything relationship can be built or something like that.
Okay, sir. Actually, we have not pondered upon this, whether the relationship has.
Okay. Thank
so
you.
I'll obviously think about it. Yes.
Okay.
So we'll move to our next paper. The title is Public Key Cryptographic Implementation Validation, Present and Future. And it will be presented, and the authors are Dr. Anand Mohan, Dr. Abhay Jacob, and Raghavendra Patil. So I think the paper will be presented by Mr. Raghavendra Patil. Yeah. So I invite presenter.
Hello, thank you, Deepak. I'm Raghavendra Patil. Joining me online is Dr. P.V. Anand Mohan. And this is we are the three authors. So this is basically public key cryptographic implementation, validation, present and future. So the work is done under the MeitY project funding. So the agenda is basically we'll discuss about the validation requirements for cryptographic implementations, then the public key standards for both RSA digital signature algorithm as well as the elliptical digital signature algorithm standard algorithm, and the we'll see the NIST shortlisted post-quantum cryptographic algorithms and how we can test them, and the final conclusion. So basically, the two more widely used public key algorithms are RSA and the elliptic curve, and they are extensively used even in PKI environment. So these are useful for authentication and digital signature, and even for the key exchange mechanisms. So digital signature, as we know, the first hashing of the message is done using SHA-1, SHA-2, and latest with SHA-3 algorithm, any of the algorithms. So this implementation can be either in hardware, firmware, or software. The basically the validation concerns with the correctness of the algorithm rather than the implementation of the algorithms. So there are two types of the basically, if you look into the FIPS 140/2, there are two kinds of testing and validation. One is a CAUP, other one is a CMAP. The CAUP concerns with the algorithm validation, and the CMAP concerns with the module validation. So basically, the prerequisites for the CMAP is CAUP. That is, the algorithms you have implemented either on the hardware or software or in the firmware, they have to be certified first. Then you will go for a module validation based on the certain security criteria. So how it happens is, initially vendor has to sign a MOU with the lab. Then he has to upload his security policy. Then the lab will send a certain request files for the checking the algorithm validations. When the algorithm validation is passed, then the certificate will be issued. Then we'll proceed with the module validation. For a module validation, you have 11 requirements. So particularly, specification, module specification, interfaces, specification of the interfaces, roles, services, authentication. Like that, you have related to operational security and the finite state machine and the mitigation of other attacks. Say if you have implemented any side channel attacks and all, that can also be tested. So this is according to FIPS 140/2. Now they are updated to upgraded to FIPS 140/3, and the it is aligned with the ISO 19790. So you have some not an extra, mitigation of the other attacks was optional, say in the FIPS 140/2, now which is made a mandatory in 140/3 and the ISO 19790. So now, for example, this presentation or the paper mainly concerns with the public key cryptographic validation. But since AES used everywhere, so if we take the example test done on the AES has a basically block size of length 128-bit, which is, and you have a key size varying from 128, 192, and 256-bit. So once if you have implemented an AES, once you will be given with a certain test from the lab, like GFS box, KeyS box. GFS box is for the operation of AES algorithm. KeyS box is for the testing the S box implementation in the key schedule. So you have variable text and variable key, and suppose you have a these are for the single message block. Suppose then you since in the practical it will be used in the multi messages will be used. A message can be as long as can be very long. So you have a multi-block message tests also, and Monte Carlo test for the say finding out the any errors in the implementation, say memory leaks or the you would have allocated a memory and may not have freed it. Such things will be found out from the Monte Carlo test for different modes. Now they have introduced the authenticated modes of encryption also, like CCM and GCM. Though tests for those modes are also available. So basically, since we had many discussion on the post-quantum scenario, in the post-quantum scenario, AES 128 bit will become vulnerable due to Grover's algorithm, but 256 will be still very strong. So we need not worry about the, AES with respect to the in the post-quantum scenario. Only we have to increase the size of the key. So now coming back to the RSA. So RSA is widely used in the digital signature and key exchange mechanism also. So usually the suggested is earlier suggested one was 1024 bit, but the NIST now currently suggests 2048 or 4096 bits. So all operations are done on integers. So basically the RSA, the security of the RSA depends on the two primes generated of equal size P and Q, which are the private, and the product N is made up public. Okay, so and basically, you just can't construct any primes. The primes constructed have to be strong, and you just can't do with the whatever explained in the textbook or the examples. So there are certain restrictions. You have to check for the strong primes, and the particularly if you are going for a encryption or the signature RSA signature thing and all, you have to follow certain padding mechanism so that certain attacks on RSA can be avoided. So these are the NIST tests on RSA. So the key pair generation and validation. There are three types of RSA test. One is a key pair generation and validation. Other one is a signature generation, and the last one is a signature verification. With respect to key pair generation and validation, so as I have explained, RSA key consists of primarily two primes, equal size in equal size P and Q. So they can be generated using a provable prime method, probable prime method, and provable with conditions based on auxiliary provable primes. So basically what it says is you have something called a provable prime. A provable prime means you don't generate a random number, then you try to prove it. So for that you have a aegis method, which is a polynomial in time, and other methods, but they are not still practically not feasible. So what we do here is in provable prime method, you construct here the construction of the prime is done. Basically you take the smaller primes, then you under certain conditions you construct a prime where you can prove that it is a prime. You don't run a provable prime test on that, but rather the construction ensures that it is a prime. So that is a provable prime method using a it's based on the Pocklington lemma. Yeah. So and there are probable prime method where you use a Miller-Robbins method and a Lucas method and all. And there is something called then you have a RSA signature generation and verification, which are based. There are three standards basically: ANS X931 and PKCS version 1.5 and PSS. So using these three standards, you will be able to, we have to follow the further generation of RSA signature and verification. So these are the different tests for the key pair generation. So validation test is you have two types. One is for provable primes and the primes with condition. In that case, what the 25 sets of the test vectors will be set for each of the different primes you are generating, and the tester has to generate those primes and has to return it to the lab. Lab will validate whether they are correct or not. With respect to probable primes, you have two tests. One is a known answer test, other one is a key gen random probable test. In case of KAT, so the lab will generate the primes and the public key exponent E and other related parameters, and we'll ask the vendor to test whether they are correct or not. And in keygen random test, lab requests the vendor to send a 10 pairs for each of the primes he's going to generate, and for each of the modulus with respect to the RSA modulus, and the lab will validate whether they are correct or not. So these are the key pair generation tests. With respect to signature generation thing, lab will send a 10 sets of the messages. The vendor has to respond with the different E, P, Q, and message, hash of the message, and the signature. Lab will test whether they are correct or not. Similarly, for a verification, what the lab will do, lab will generate a different kind of signatures, RSA parameters, and will send it to the vendor. Vendor has to some of the things will be intentionally modified for a wrong signatures. So the lab has to, the vendor has to check which of the signatures are correct, which of the signatures are wrong, and has to send back the result. So this is a RSA thing. So with respect to the ECC thing, it can be over the prime integer field or the binary field, and can be over the Koblitz curves also. So with respect to integer primes, you have P192, P224, P256, and P521. So the one speciality of these NIST curves is that they have a simplified structure, in the sense P192 can be represented as 2 raised to 192 minus 2 raised to 64 minus 1. So if you see the exponent of this, you can see this is the multiple of 32-bit. So this leads to the optimization. You can optimize your implementation, and you can simplify the representation of a P192 curve as T plus S1 plus S2 plus S3 mod P. So which will result in the faster modulo implementation of faster modulo operations. So similarly, compared to the RSA, you have 4 basic steps: key pair generation, public key validation, signature generation, and signature verification on ECDSA. So if you take the elliptic curve definitions, so you have this is one example elliptic curve. So you have prime modulus P and the order of NP, order of NPs. So N of P should give the point at infinity. And you have 160-bit input seed to the SHA-1 algorithm, and the output C of the SHA-1 algorithm, and base point JXGY. Okay, I'll just finish. So basically, coming back to the so you have a generation in the signature generation. So key pair generation test, same thing. You basically lab will send ask you the DUT to send the sum of over the curve, whatever he has selected. Ask him to send the sum of the keys, and it will test whether they are correct or not. Signature generation test, lab will generate the the lab will ask the vendor to send the signatures, and it will check for the correctness of the signature. Verification, lab will send the some six signature for each pair of the a public or a private key exponent, and it will intentionally modify the signature, and the vendor has to find out whether they are correct or not. So similarly, we have something called earlier SHA-1, SHA-2 were there. Now we have come up with the SHA-3. NIST has come up with the SHA-3. So that is based on a sponge construction. You can see that here you have a short message, selected long message, pseudo random, Monte Carlo test, and the variable output test. So basically, as others discussed, NIST has come up with the round 3 winners. They have shortlisted 4 algorithms: 1 KEM, Crystal, Kyber, and the 3 digital signature algorithms. So they have 4 alternatives for the next round. 1 is already broken. So Yeah, I'm concluding. So the point I'm trying to make is the whatever the textbook algorithms you have studied, that may not be enough for implementation. So you have to do a rigorous testing to achieve the objectives. So the future is NIST has upgraded to FIPS 140/3, and you have ISO 19790 and the ISO 24579 and ISO 18367. These standards have to be followed for a validation of the algorithms. Thank you. Okay, yeah. Any questions?
Questions we will take offline later.
Okay, thank you. Thank you. You want to speak?
So very wonderful presentations were given by Ms. Dibyashri Guha and Mr. Patil. So I think lunch is already waiting. So we conclude this session now. So thank you very much for the speakers. Okay.
So first of all, I will request Dr. Misbauddin to felicitate the session chair. Either. We will break for lunch, but few announcements are there. So after the paper presentation sessions end here. So after that, after lunch, we have one invited talk from Denmark by Mr. Jacob Nielsen. We have one very important panel discussion on post quantum cryptography, and we have one keynote speech by Professor Jaideep Padya from Rutgers University at the end. So please join us back at 2:15. So I know it's less time, but I think we are running behind the schedule. So we want to finish it fast. Thank you all. So registration kit will be given after. It doesn't matter. So the registration kit will be given post lunch. Thank you.
Good afternoon to all of you. I request the members to get seated. So as we start the second session of the day today, we have an invited talk by Jacob Hojmark Nielsen from Denmark. Good afternoon, Jacob. Happy to see you here. The title of the talk is on why PKI consolidation and certificate ownership are crucial elements of success. I would like to introduce Jacob Hojmark. Jacob Hojmark Nielsen has 20 years of experience in the PKI industry and the last 18 years as a co-founder and the CEO of Trust Zone, which is a Danish IT security company focusing on the commercial aspects of PKI and digital certificates. The mission is to make PKI feasible, understandable, and tangible for a broad audience, and thus communicating and catering the technology and principles of it in a stakeholder point of view. Thank you, and over to you, Jacob. You can share your screen.
Thank you very much for that, and such a...
You can unmute yourself, and you can turn on your camera also.
Can you hear me?
Yes, we are able to hear you.
Okay. So just 1 second, I'll share my screen in a minute. Good afternoon, everyone.
But we are not able to see your video.
Good afternoon, everyone. Now you should be able to see me.
1 second. Yes, you're able to see. Yeah.
So for the third time, good afternoon, everyone.
Yeah, thank you.
I'm very happy to be here. Thank you so much for inviting me. It's a great pleasure and a great honor to have the opportunity to have this short speech today with you. I'm going to share my screen. Oh, I'm getting a message that the host disabled participant screen sharing. Could you help me out with this?
One second. You should be able to share now. Please check it.
I'm getting the message host disabled participant screen sharing.
No, we are able to see your screen, but we are not able to see your slides presentation.
Can you see anything now?
No. Making co-host. 1 second, just.
Thank you.
Yeah, you have been made co-host now. You should be able to share it.
Now I have the opportunity to do so, yeah.
Yeah.
Okay, so hopefully you can see my screen now.
Yes, if you can put it in full screen, the presentation will be good.
Let's see if that's possible.
You may have to press F5 as a shortcut.
Well, for some reason, it's not being displayed as it's supposed to. I'm very sorry about that.
Maybe what you can do is you can unshare this, and again, after pressing F5, you can again reshare it. It's okay. You can just increase the zoom percentage. Oh, yeah, of course, yes. You can. It's fine.
Yeah, I have no idea why it doesn't. It seems to.
It's okay. I think you can start the presentation.
Great. Okay. Well, thank you so much for having me. As I said before, it's a great honor and a great pleasure to have this short talk about why the PKI consolidation and the certificate ownership are crucial elements of success. So the agenda for today, it will be a very short introduction, and I believe it has actually already been done. But who am I? And just a little about Jacob at a glance. Our short stroll down memory lane, talking about the past, the present situation, and something about the future as well. And lastly, I believe that there would be a possibility to come up with a few questions if you have any. So moving on to who I am, I believe it has already been said. 20 years of experience in the PKI industry.
Sorry, actually we are not able to see the slides moving. So I think you may have to put on slideshow mode, in the presentation slideshow mode, and then again reshare it. Yes. Okay, this also is fine. Yeah.
I stopped it now.
Can you try clicking on slideshow in the?
Yeah, for some reason, it's not really being displayed in the way that it is on my screen, I see.
Okay. Okay. I think you have to keep moving on the slides. Right now, we are able to see, we are on the slide number 3, who am I? That's where we are able to see.
Okay, okay, thank you. Well, I am too, but I can see that you have a bit of a different view, it seems like. Let's try to see if it works out. Yeah, so 20 years of experience in the PKI industry. I guess that makes me kind of a dinosaur in this rather young industry. As it was said in the introduction as well, for the past 18 years, I have been the CEO of Trust Zone, which I co-founded with my business partner in 2004. If I'm supposed to, highlight one quality in myself, it should probably be that the commercial know-how that I have combined with the technical flair. That basically means that I am certainly not the technical experts, but at the end of the day, I do think that if my mission is connecting the dots between advanced technology and real people, it's an absolutely crucial quality to have, actually. Oh, I can see the slides are not going at all. Still.
Now we are in slide number 5.
Yes, I will do it like this.
Yes, now we are in slide number 4. Yeah, that's fine.
Yes. Okay, so just a little about the past, short stroll down memory lane. As most of you probably know, the PKI was invented in 1976, and seen from a commercial point of view, I would say that from 76 to 95, not a lot happened actually. That doesn't mean that there was not a technological development going on, but from a commercial point of view, it was, well, not really a lot of interesting news. So in 95, the SSL version 2.0 was released, which opened up for the possibility of actually issuing publicly trusted certificates. And the first one was issued just around 95, 96. And on top of that, in 98, the first version of the Microsoft CA was released with the Windows NT 4 option pack. For those of you who are old enough to remember that, because that is certainly a long time ago. The years after this, I would say that the PKI in general was still in a very immature stage. I think the broad perception of PKI was basically that PKI would equal SSL certificates. So basically that was the one part of the entire PKI framework that you would actually have any commercial value of. In 2005, the CAP forum was established, and that, of course, made or paved the way also for a lot of the things that we see going on today. As you probably know, they are regulating a lot of things, and they are trying to keep up the pace with all the things that are happening in the industry. And another thing in 2015, Let's Encrypt is born, as all of you probably know. And I would say that this was, if I was to say something, one vital thing that has happened in the past 10 years, it should certainly be the birth of Let's Encrypt, who has significantly changed the market for digital certificates from a commercial point of view again. So from 15 and onwards, I believe that we have seen a liftoff in an ever-growing market for digital certificates. It has certainly become much more tangible also, even though that we are not there yet. I do believe that we are looking into a much more mature market now than when I entered back in 2002. So that leads us up to the present. I will start out with the good. So from a PKI point of view, there is certainly a lot of good things to say. One of them would obviously be the explosive growth that we see in the digital world today. So I mean, the first time I heard about IoT, for instance, was many years ago. But fast forward to today, where it is actually materializing what back then was a quite fluffy concept. That leaves us with a great potential and estimated 29 billion connected devices as per today, which of these 18 billion would be IoT devices. And obviously the identities and the tracking of these devices open up a lot of possibilities if we're looking at it from a PKI point of view. Another thing driving the industry in the right direction would be the route towards short or shorter lived certificates. This will, of course, eventually mean that we will have many more certificates as we have been used to. So for quite a few years now that this has been talk of the town in the industry, also from a commercial perspective, and what it will actually take from a technical point of view as well. So it's really hard to say what it should say on X's place here, but for certain, I think it will be fair to say that it will multiply the market by maybe a huge number. Yes, so that leaves the industry in a state where you would be, I think you would be right to say that it is now very close to being mature, if not mature right now. And the drivers influencing the PKI industry seems to be on a very heavy uptake, and I see no indications really that this will not be what we are looking into in the future as well. So yeah, to sum it up in this one, I do think that we have great opportunities when we are looking at the market from a PKI point of view. Moving on to the bad part. So obviously there are still a lot of challenges. There are a lot of things that we still need to address, to solve in order to really succeed with the PKI. First of all, I would really like to highlight the lack of clear ownership and consolidation. What we have seen several times, and in almost all cases, basically, is that organizations struggle to actually anchor the responsibility, and that leads to what we call the silo fallacy and a lot of failed projects. This basically means that you would have a wish of actually moving in the right direction and actually implementing PKI in your organization, but seeing that you have no true responsibility, you have no true anchor in these cases, it will often lead to having projects that are run by departments and not the entire organization, which eventually almost always will fail unless this is something that you have actually counted in to your strategy. Another thing would be the competency mandate, the gap. So as it says here, the experts don't have the mandate and the mandates don't have the expertise. This clearly means that we have a lot of skilled people, and more are joining each and every day. The problem is that these PKI experts would rarely have anything to say when it comes to a strategic decision. That leaves us in a position where the experts might have the expertise but no mandate. And as it says here, the mandates clearly don't really have the expertise to look at PKI in a more holistic point of view. So you have clearly a gap here that needs to be closed before you would actually be able to succeed with a successful PKI strategy. And lastly, we have a few things that all along the way have blurred the lines, you know, distractions and you know, things that will take away the focus of actually succeeding with PKI. I think one of the best recent examples we've seen is clearly all the focus that went on blockchain. And I'm not going into any religious discussions about blockchain versus PKI, anything like that. I am merely saying that the the blockchain rocket took a lot of attention from the market in general, attention that would be turned into blockchain and thus defocusing on PKI. That has certainly also slowed down the PKI industry in general, and thus it has not been one of the good things for PKI. Also, I believe that the industry in general has blind spots. That also means that when new possibility arises, the industry is not always doing a very good job in tapping into these potential opportunities, whether that's IAM, zero trust, or one of the other things that could easily be combined with a discussion around PKI. I think that there is certainly room for improvement here in terms of actually unfolding the potential of PKI in general when these things happen. And lastly, what I'm going to address here is also the communication from the industry in general. For many years, as long as I can remember at least, the communication with the market or potential market from the industry has not always been leveled and performed in the right way. So this means basically that you would have technically complex messages that you would also deliver in a very technical, complex way, which at the end of the day is how it is. But if you are supposed to drive growth in a market, it's just extremely important that you are able to communicate with whoever is at the end of the day going to pay for one of your solutions or going to opt in on one of your solution. So from a commercial perspective, I do think that the communication in the market has been it has probably been miscarried out in general. I think would be the right way to put it. Still looking at the present, there are questions to address here. There are questions to be answered if we are striving to be successful with our PKI integrations. So again, from a PKI point of view, I think going back 5, 6, 7 years maybe, I do think that the toolbox in general was lacking quality. That has changed so much to the better now, I believe. But yeah, 5 or 6, 7 years ago, there was maybe not the right products to facilitate a PKI strategy that to some extent would also include scaling up as one of the important parts of the strategy. So as per today, I think what is very important is, of course, to have infrastructure transparency. That is actually something that seems to be quite hard for a lot of organizations to gain. In general, we do see that the internal lines are quite blurred. You don't have the complete overview, and obviously it leads a bit back to, if you haven't consolidated your PKI as a strategy, I guess that you are back to the question again, well, if it's going to live on a department basis, you can't really get that full infrastructure transparency, which is just very vital if you are planning to do an ambitious and value-based PKI strategy. Another thing, also seeing that the uptake of digital certificates in general have been exploding and probably will still increase also in the future. The need for an automated certificate lifecycle management system is just getting more and more clear each and every day. So I think as per today, as we see it, in general, everybody will be talking about this. Not all us are ready to go to the action phase, but at the end of the day, most people do realize that they do need to address this question, which then leads to the decision part again. And as you can see in this slide, I've written that so far, I believe that this has been a bottom-up decision, unfortunately, so driven by someone who would have the expertise but not the mandate, which again, in many cases, as we've seen, would lead to not really going anywhere. So instead, as far as I can see, if we manage to flip it around and actually pivot this to a top-down instead, my best guess would be that you would have a much better chance of actually succeeding with a successful PKI strategy. So realizing that you need to take this decision from the basement and to the corner office is something that could certainly be a very important factor for succeeding with your PKI strategy. And the potential, I do think that I mentioned a little about it on the previous slide also, but actually realizing the full potential of a holistic PKI strategy. I mean, to my best knowledge, I do think that a lot of the decision makers today, which are not experts, of course, will not really see the full potential of a PKI strategy, as they do not really have the technical competencies necessarily. So I think that unfolding and tapping into that potential is something that could be very helpful also to drive the right decisions and thus driving the strategy in the right direction. But in order to make this feasible and also make it tangible and reachable, I think that there is a need to do a step-by-step approach to actually succeed with the holistic PKI strategy. So in order to actually get this going and trying to break it down, I do realize that we are still very high level. Here are 3 P's to master at least. So the people involved in your PKI strategy will certainly be extremely important. So I have written here that combining the expertise and the mandate will be absolutely crucial. I mean, in the perfect world, you will probably have this in one and the same person. In the real world, that's probably not really doable. I mean, that will make a PKI superhero, and as far as I know, that really doesn't exist. So I would suggest that the people here would be a small group of people combining expertise and the mandate, and actually being able to form the right strategy. The processes, of course, will be important. So when you have the strategy in place, I mean, you will start up a lot of processes probably. So defining and delegating and communicating these processes will be key to also be successful. I mean, what we have seen so far in recent years is that you might have an idea where you want to go, but you have no idea where to get there. And that is where the processes actually kicks in. And lastly, the products to support your strategy will also be important. As I mentioned before, this is not really a concern to me as per today. It is still very important, and it is very important to choose the right one. Of course, we will suggest that you would consider the agility wanted, the scalability that you need, and obviously the robustness and the quality of the products and systems that you will choose, of course. What could confuse decision makers, maybe the market in general, as per today, is that most people can, read the statistics, and they can see that in the IT security industry in general, there are billions of dollars going in, and that amount is just increasing year over year. That also means, of course, that you will have products of a certain quality, but you will also have products now, seeing that the market is so attractive, that would be in a state where you would actually not be able to achieve and be successful with your PKI strategy. So depending on what you would like to achieve here, find the right system to actually facilitate and support your PKI strategy. So moving on to the future, we have tried to break it down in two absolute essentials in terms of how to succeed. So number one would be the consolidation. It is going to be absolutely crucial to make your PKI strategy an organizational priority and not a department project. That is probably the biggest and the most common failure that we have seen in the recent years, is that you would actually like to go somewhere, you would actually like to take your PKI strategy somewhere, but at the end of the day, you treat your PKI strategy as a department project. So you would isolate it in one, maybe two departments, which at the end of the day will be would be not working in the right direction in terms of actually making this a success in your organization. You might be able to succeed in that one or two departments, but that doesn't necessarily mean that you will manage to roll it out in the entire organization. So get the strategy in place first and make it an organization priority. That is absolutely crucial if you would have the chance to succeed. Number two is also the certificate ownership. I think I said that before as well. Seeing that certificates or the market for digital certificates has been exploding for many years now, and will probably do also in the future. We see that there are no real transparency in terms of certificate ownership. And on a low level basis, that is becoming an increasing problem, whether it's internal and external certificates, because it's just a very messy picture we see in general, and it is something that is being owned, or the responsibility is being owned by departments and not the organization. And I think it's quite common human nature, really, that if you have already a busy day, you tend to focus on, well, your own things, your own priority list, your own tasks, and so on, which eventually will defocus the organizational picture. So what happens is that you will focus on the certificates that you have in your department and seeing that certificates are not being anchored anywhere in the organization. Well, you're just focusing on what's on your plate, and that will eventually leave you in a very bad state if you want to succeed with PKI strategy in general, because you will have 10 or 12 or 15 or 20 departments that will be their own king of the castle, according to the responsibilities for their department, but not any organizational responsibility at all. So I've tried to break it down in 7 hopefully feasible steps, and thus creating a recipe for success in terms of succeeding with your PKI. So number 1 would obviously be to define your PKI strategy and mandate at the highest level possible. I mean, if you go high enough in the organization, I think decision making would hopefully be much easier. And if you manage to put together a group where you also have the technical expertise represented, I think you are off to a very good start and in a very good state in terms of actually succeeding. So that's going to be your number 1. Your number 2 will be appointing all stakeholders as early as possible, of course. It is very important that everyone will be looped into this strategy at a very early stage. Partly because, of course, it will hopefully create a much stronger feeling of ownership of the strategy, but also to have the input from different departments in terms of the stakeholders represented. After that, it will be essential to communicate the PKI strategy across all departments. So also, again, including all departments that will be involved in your PKI strategy, of course. So you at the end of the day will have complete transparency in where you're heading and how to get there. After that, in number 4, you would need to create a crystal clear, feasible, and tangible plan for actually succeeding with your PKI strategy. So breaking it down as much as possible, granulating as much as possible, putting teams together, delegating responsibilities, and aligning expectations would be absolutely crucial. We have looked into and looked over a lot of plans that at the end of the day was not feasible, not very clear, and certainly not tangible. And I can just say that you are you are almost doomed to fail if you cannot communicate and create a plan that everybody actually understands in terms of responsibility, who does what and when, and so on and so forth. After the plan has been drafted, you would need a buy-in from all stakeholders before laminating the plan. So get that important nod from all key stakeholders in your PKI strategy. It's very important that none of them are hesitating, none of them might not really believe in the strategy, and thus not having the correct buy-in in terms of actually succeeding with the plan. So do that before laminating the plan. If there need to be done any minor tweaks, a bit of detail changes and so on, that's perfectly fine. At the end of the day, hopefully the essential parts of the plan would be accepted and thus a full buy-in, but leave room for just very small minor iterations. Yeah, after that, I guess it's all about go action and go do what you have planned. It seems so easy when you just look at it in a slide, but this is where the true work of the craftsman begins, of course. So obviously this bullet is very important too. But I would say that if you are not tight and clear with the first 5 bullets, you're doomed to fail with the bullet number 6 here. So, I mean, the action will reflect how good you have been on the first 5 ones with your PKI strategy. So all the work that needs to be done before moving on to the action part is absolutely crucial for how well you would do with bullet number 6. Yeah, and lastly, I think you should when you got there, or when you get there, you should obviously celebrate your success. So wrapping up, I think it would be proper to do the conclusion. I do realize that this talk has been a lot about simplifying complexity. That is obviously a very hard thing to do, but the key takeaways, or the key takeaway should be that it all boils down to one question. Do you have the right people with the right competencies, with the right mandate to drive your PKI strategy? And if you do, I would say that you're in a very good state and the possibility for success is within reach. That was all from me, so I guess that we can move on to the Q&A session, and please fire at will if you have anything to ask.
There is a question in the chat window. What is the impact of blockchain and PKI and vice versa?
I don't have any numbers and figures to relate to. I can just say on a personal level, I've attended several conferences. Now it's probably 3 or 4 years ago, but I did that for maybe 3 and 4 years also, you know, to keep myself updated on what was going on. And what I remember from these numerous conferences is that you would have a lot of talk about blockchain back then, almost no talk about PKI, and obviously I do think that has distracted the PKI industry in general, especially also the commercial parts, because I know for a fact that a lot of large organizations in my region, at least, would turn their attention to blockchain and thus neglecting the PKI industry.
Thank you. Any other questions from the audience here? Okay. So thank you, Jacob. Thanks for taking your precious time out for this presentation. So thanks to all of you. Thanks to Jacob. We'll get back to you. So
thank you very much. Thank you for having me.
Thank you. So now as we move on to the next session, I request my colleague, Mr. Asvija, to come and start the next session, which is a panel discussion.
Good afternoon to all of you, and welcome to this second session in this afternoon's proceedings of the conference. So as part of this session, we'll be now having a panel discussion on quantum cryptography, the various aspects of quantum cryptography, including the PQC, which we have heard a couple of papers also on this subject today. So to chair this panel discussion today, we have Professor MeitY from IISc Bangalore. So I'm honored to have him on the stage, please. Professor MeitY obtained his academic degrees, BE Electrical Engineering from College of Engineering Madras, ME in Control Systems from BITS Pilani, and PhD from Indian Institute of Science in 1975. He worked in the industry, Air India, National Informatics Center, before joining the Computer Science and Automation Department of IISc in 1983. He was the chairman of CSA department during 1998 to 2000. He was invited to head the DRDO laboratory, SAG, in New Delhi during 2000 to 2003. His current research areas of interest are computational linguistics and pragmatic cryptanalysis. He continues to work in IISc on 3 different R&D projects in the areas of cryptography and natural language processing, and on several technical advisory tasks, government policy and academic and research mentorship. We welcome you, sir. May I now request the other panelists also to kindly occupy the dais. Dr. Tapas Pandit from IISc Bangalore. Dr. Tapas Pandit received his PhD degree in computer science from ISI Kolkata in 2017. Before that, he obtained his MSc degree in mathematics from Calcutta University and his MTech degree in computer science from ISI Kolkata. From 2017 to 19, he worked as a postdoc fellow at IISc Bangalore. So his research interests include public key cryptography, predicate-based cryptography, quantum computation, and post-quantum cryptography. Currently, he is working as a specialist scientist at IISc Bangalore. We welcome you, sir. May I now request Dr. R. Srikanth from Purna Pragna Institute of Scientific Research, Bangalore, to kindly occupy the dais. After obtaining his PhD from IISc Bangalore, Dr. R. Srikanth worked as a postdoctoral scholar at the then Center for Theoretical Studies at IISc, and then at Light and Matter Physics group in RRI Bangalore. He joined PPISR as a faculty fellow in 2006, becoming an assistant professor in 2010. He has guided multiple PhD students in the fields of quantum cryptography, quantum noise, and quantum foundations. And he has co-authored over 70 research papers. He is also a consultant for 2 quantum technology startups. Welcome, you, sir. I now welcome Mr. Animesh Aryan, who is the CEO at TACBit Labs Private Limited, Bangalore. So Mr. Animesh would like to call himself as a physicist who loves to learn and is passionate to innovate. He has worked on building the first quantum source of light in India. It is one of the most exciting projects that he has done, and the work done on this project laid the foundation of TACBit startup. So the applications for this work are in the quantum cryptography and quantum computing. Welcome you, Mr. Animesh. So apart from these panelists who are physically present here, we also have 2 of the panelists who are joining online. Dr. Devapriya Basu Roy from IIT Kanpur. He did his PhD under Professor Devdeep Mukhopadhyay from IIT Kharagpur, and did his postdoctoral fellowship at the Technical University of Munich under Professor George Siegel. His research interests include applied cryptography, hardware security, post-quantum cryptography. He's an expertise on developing hardware accelerators for cryptography and side channel analysis. He's currently working as an assistant professor at IIT Kanpur. We welcome you, sir, Devapriya Basu Roy. We also have Mr. Prasoon Srivatsava, who is the APAC head at Thales, who is also joining online for today's panel discussion. Mr. Prasoon Srivatsava is a senior solution architect for India and the SAARC region for Gemalto's identity and data protection business, where he is responsible for delivering turnkey solutions, mentoring partner and channel networks, and monitoring of technical operations in the India and the SAARC region. Mr. Srivastava has 15 years of experience in the IT industry. He was the solution expert of BFSI market for SafeNet in India and SAARC, responsible for delivering business data security solutions throughout the SARC region for the VFSI and payments market. Prasoon holds a Bachelor of Engineering from Vishweshwarya Technological University. He is an enthusiastic public speaker, presenting his technology expertise at multiple platforms in India and globally. We welcome you all, sir. May I now request Professor Veni Madhavan to take over from here. Okay.
Nice to be here and nice to be with lots of friends, starting with Professor Shamsundar, Binduvado, Patel, many Sudarshan from C-DAC, and lots of people from C-DAC and our generally the Bangalore community. We will try to see in an hour some pros and cons and issues and perspectives about this quantum business. Okay. Actually, really quantum business, because it is quantum hype, quantum computing, quantum crypto, quantum communication, quantum everything, quantum governance, and so on and so forth. So I'm fascinated by all the things which happen, and also coming late in the day in our own field, we all have a penchant for making some predictions and things like that, and would be nice to see about your personal predictions and interests, how they go along. Anyway, so I'm very happy to say that we have all this interesting panel members today. So we will, as a format, we will try to do some 5 to 6 minutes of broad shedding light and according to our perspectives on different parts, and then leave a little more open time because I know lots of open, even very basic, sometimes maybe bordering on what people call trivial questions could be there, but doesn't matter. Let's air them and get across. Okay. So during that, maybe there will be a chance for our experts also to highlight some of the points. So obviously the field is vast, so one is not going to give be able to give a tutorial or even a conference presentation. But broadly speaking, it is also to relate to PKI, the theme of the conference. So in order to do that, I set the tone by making some broad slides, and I had circulated and discussed with my colleagues here, very esteemed colleagues from different aspects of this thing, and also 2 other colleagues who are not here. Third colleague, Diman Saha, is not there. I thought earlier I saw his name, but you didn't mention it. So I had put these people's names and what I presumed are their generic interests. Okay, so they are all people. As you can see, many things are connected. But we thought this thing will be about cryptography, about what is called post-quantum, and it's already arrived. And of course, cryptography includes cryptanalysis. And so you can see there's some subtle distinctions up here and there. But that's not all. Communication is an integral part of this quantum game with respect to information security. Okay. So I try to put quantum cryptography, communication, 2 C's. And then, of course, this big business of computing. Obviously, it's outside the purview of, I think there's no time also. But on the other hand, this ramifications about is that going to be there for energizing cryptography and cryptanalysis, or or the quantum communication seems to have arrived much earlier. So there is this thing about hype and in this game. Quantum computing itself came hyped up because of crypto, but I think my perspective is that it's in the background and of course interest finally to only few people. I'm talking about now what quantum computing can do to classical crypto in cracking them apart and all that. And that's the hype. Of course, that's a beautiful theory. It's not a theoretical hype, it's a practice. But if the quantum computing comes, what happens? So crypto, new crypto, and anyway, new crypto was its time was there already, particularly public key cryptography. So we'll have Tapas speak about it. So there's some order. I'll just give some perspective on overall. Then Tapas will speak something about the quantum crypto and the timeline, what's going on, including some communication. And then we have two colleagues from physics and communication, very interesting, where I think things have arrived, native talent plus overseas. There are lots of clientele for this subject matter, particularly the key generation, key distribution, etc. So Srikanth and no, I think we agreed Animesh first and then Srikanth next in that order. It gets more specialized. Then, well, yes, Devapriya is to deal with hardware implementations, side channels, everything for the post-quantum classical ideas-based cryptography. Okay. So that's the technology part of it, which will come in. And then Prasun Srivastav will be some kind of a buffer with the end user and so on. So he will tell us about information security issues. So with all that thing, that's a broad idea. So obviously, there are many tracks. I just highlight, these are bullet point slides. So all the connections are appearing here. Communication, computing, cryptography. But of course, there's a whole lot of excitement in different fields. That's the best thing about quantum, in my opinion. It's bringing together, first time I'm seeing, physics, electrical engineering, computer science, mathematics, at least this many, and then many other people together to facilitate the whole game. Okay. So, but then, there's this great game of new games of material science itself advancing, and because of that, sensing and many other applications of this quantum computing initiative. Okay, so all this will drive the future next 10, 20 years. So, in my opinion, we may not even see a equivalent of a exaflop contemporary Turing machine-based von Neumann architecture machine, which runs in the US, equivalent power, equivalent problem-solving ability in across the field. It's not going to be there at 20 years. Neat. But then a whole lot of excitement in the physics and particularly the physics community and electrical engineering community and electrical communication engineering community who will probably build the machines, okay, which are getting built. We read about it all the time. Every day some news or the other comes from the things. So there's a whole lot of material on that about the computer. And then of course on the communication front, from pseudo to true to in between quantum RNGs and KGs, key generators, and then the distribution. There is a lot of excitement because they are going to solve many practical issues with the realization of cryptography for information security systems. Okay. So there's a lot of happy things there. There's some physics and some electrical engineering more, and electronics and communication, including coding theory and so on. So the trends, I call them the 3 Ts. Actually, those will be the final drivers. Science, technology, of course, which we'll talk about. But it's always the case that do you have a USPs, use cases for things? That's the first question. Business and commerce and trade ask for, and we just had some thought sharing on that. There are this machine learning communities which always are on the wings. They promise much more things. So probably the quantum will do some wonders there. In particular, optimization and search methods are going to change with the revival of certain types of, I would call classical mathematical ideas embedded into the very natural quantum state-based machines. Like, for example, quantum tunneling is something which is interesting counterpart to quantum annealing. And annealing has been a kind of a mechanism used in certain kinds of optimization heuristics, all the gradient methods, which are the core of machine learning methodologies and realizations. So you might have a quantum machine learning app in your mobile phone earlier than a quantum breaking app on a mobile phone. Of course, certain classical, I call it the post-quantum crypto algorithm, which are nothing to do with quantum, Okay, they are classical mathematical ideas in their new avatars. Okay, that will be there on our mobile phones and so on. So some things you will hear about. Now, rest of it, I'll just skip all of these things. I just did some. I've been doing some surveys and catching up on this and trying to wonder where things are going to happen for a non-specialist physicist person, a pure computer science and math person. But something like photonics is going to pave the way. Apparently, some gainer. Certainly for communication, yes, you'll hear a lot more about it. But even computing, photonic devices, which chips and switches and so on. So this is the way towards scalable. Lots of things about scalability, what you might call fragility preserving. They're very fragile. You need to control a lot of things. So the control of this very sensitive quantum state-based computing devices is going to be a new game, and there are a lot of material and newer forms of this. Now, in this front, just one word I wanted to say. I'm particularly interested in only cryptanalysis today. How we can break things, really break, from theoretical to practical, of course. This is a typical illustration of just chatting with people here. My belief is that RSA, okay, let me put some conjectured beliefs. If you scale up today's public key, private key to about 16 to 32 kilobits, okay, we use 2048, 2 kilobit. 16 to 32, it will be phenomenally expensive and probably unrealistic to be able to see any one of those quantum state-based machines. There are 3-4 quantum state properties which are being exploited: the ion traps and superconducting qubits and photonics and nitrogen vacancies and a variety of things. But essentially, any machine which is going to come to be able to do for a 2048, there's an excellent set of papers in the last 4 or 5 years. 3n odd n. N is the number of bits. It's exponential, sub-exponential in the classical breaking. If n is the size of the key, it's sub-exponential in n. It's the current day way of breaking, which I've also been doing for quite some time. But linear, 3n. So it's about 7,000. But this is nothing. This is what's called as a logical from Shor's algorithm. But more important is the number of gates which are required to be architected. It becomes cubic, okay? And circuit depths and all that thing. But more important is to be able to do coherent computing without losing the coherence and so on. So with all these caveats, it's going to be quite hard if you simply scale up current day keys. But then again, I speak from the other side. You don't want to simply scale up the current day keys and preserve the old classical. You go for new crypto, so which are invulnerable to the Shor type of mathematical attacks and practical. So there are lots of this stuff about what happens in post-quantum crypto. You will hear from Tapas. But essentially, the crypto world is gearing up for providing you new crypto, which are theoretically invulnerable a la Shor sense. There is something about underlying group property which does not, it's called the hidden subgroup property, which is in the classical things which suffer from. The newer algorithms do not suffer from that phenomenon. To that extent, and to some other strong theoretical conviction that there are these algorithms which are coming to the fore. So I'll stop here, and then the rest of it. This is all about investments and where we are and so on. I will not belabor that point, but essentially you got the drift of the things: computing, cryptography, communication. So this is what we'll start with today, and I'll request Tapas to amplify. And so some of these unmentioned things, I mean, any doubtful things we'll take it up.
Can I have a pointer? No, I'm not just I need the light ones. Oh, then leave it. I don't need. Okay, so I'm anything. So I'm just going to the slide directly. So because you got delay. Yeah, so I'll discuss, something called high-level description of quantum safe cryptography, or something called quantum safe crypto system. So actually, people might be thinking what are the post-quantum cryptography, what are the something called quantum cryptography. I will give an illustration on that. Yeah, so here thing is that adversary is quantum, that is the quantum machine. So adversary can interact something called target machine classically, quantumly. So if the target machine is classical, then adversary will interact classically, otherwise it will interact quantumly. So yeah, so the thing is that cryptography means study, right? Cryptography, post quantum safe cryptography deals with what quantum safe crypto systems, right? So those crypto systems can be classified into two classes. You can see like classical scheme and quantum schemes, right? And this quantum schemes solely designed for quantum machine, right? And for their security rely on something called principle of quantum mechanics, like something called well-known result. You can see QKD, quantum. Audible? Yeah. Okay. Yeah. Thank you. Yeah. So that quantum scheme, that is designed for quantum computers, and well-known result, something called the quantum key distribution. So, for example, BB84, ECAT91. So actually, those are based on something called the principle of quantum mechanics, like Heisenberg uncertainty principle, quantum entanglement. And this side, you can see something called design for classical computers, like what we are currently using. And again, the thing is that security of those crypto system actually based on some hard problem, like something like likewise in case of here quantum principle, here actually we need some sort of hard problem. So that should be quantum safe hard problem. That means no quantum computer can break those hard problem, right? And those scheme further can be divided into two classes. So one run on classical computer, other on quantum computer. Okay, let's talk about first quantum computer. So this kind of security is called the quantum security. So what will happen? So for example, think of, for example, say digital signature, right? So digital signature, so that now this scheme actually run on quantum machine. So that means quantum adversary can interact quantumly or something called in superposition. So adversary's goal is to produce a forgery. So adversary will get some sort of resource like sign oracle. So in this situation, quantum adversary will ask query in superposition and get the corresponding answer in superposition. So that is the difference between something called this classical security and quantum security, right? And now come to this quantum security. So this security is called the quantum post-quantum security. Okay, so not there are many schemes. So where underlying hard problem is quantum safe, but their security is given under something called against classical adversary. Now the question is that whether same protocol can be used against quantum adversary, or same security reduction can be given against quantum adversary. So that's the question. Question is that if the reduction does not involve either rewinding or random oracle, then same proof will work. For example, there are many schemes. For example, you can see many schemes in the symmetric key setting, even lattice-based scheme. So that can be used here also. Now the problem is that if there is a rewinding or random oracle, then there is a problem. So for that, actually, we need something called new proofs, right? So for example, so suppose you have to handle random oracle. So random oracle means here adversary will interact corresponding random oracle. That means hash is modeled as a random function. That means adversary will ask question to the random oracle in quantum and get the answer in quantum. So that is called also quantum random oracle model. So there are many schemes actually, Falcon, Fins Plus, Crystal Kaiba. They are actually niched NIST candidate after third round of evaluation. And come to this other side, something called rewinding. So rewinding is something called rewinding involves classical setting also. So if there is a signature scheme that is based on Fiat Samir, then their security actually involves something called rewinding. But rewinding in general does not work in the quantum setting. But recent result, so by this Liu, Gentry, and some other people, they have shown that rewinding can be useful in quantum setting. So crystal dilithium is one such a thing that is given security in that quantum random oracle model. So yeah, so these are the things. And thing is that you can see that crystal dilithium, Falcon, Fins, all are actually signature candidate. So for example, crystal dilithium and Falcon are based on lattices, and Fins Plus, that is based on hashes. And crystal Kyber is a key exchange protocol, so that is based on lattice. So these are the things. So yeah, that's it. I think, yeah, I'm just running out of time. Yeah, done, sir.
We can amplify things later.
Yeah. Yeah. Thank you.
We'll have time. We'll try to answer.
Am I audible? It's good. So good afternoon, everyone. I think you have just had your lunch and you'll have to bear through this session. So please hold on. What I will do is that as a part of this presentation, I will take you through that what are the things in quantum solution. And we will start with the first question, that what it is that quantum is offering and why it is a discussion. So this actually comes from the limits we have reached in traditional computing, which is that you cannot keep on reducing the size of the transistors any further. You're already into the nanometer range. So now on the other side of it, there is certain advantage which was developed in quantum mechanics, which led to the development of quantum computers. Now there's a very interesting relationship, which is like the way you represent a data in computing is that you have a bit representation, which is 0 or 1, whereas there is a quantum analog called as quantum bit, which can represent 0 and 1 at the same time. It is the second part of the thing which makes it interesting, is that the power actually increases exponentially in proportion to the number of qubits, whereas in the traditional computing, there's a linear relationship. So the question is that quantum computers are not like going to solve everything, but they are efficient. It is efficient in certain problems, and whereas the classical computers actually are going to be doing a lot of the other stuffs otherwise. So it's not that quantum computers will replace everything. It's going to be a hybrid model where things can be accessed the other way high performance computing came. So quantum computers in general are suited for some of the optimization problems which Dr. MeitY mentioned in some simulations. But the critical part is that what happens is that because of the advent of quantum computing and the quantum computers becoming more and more powerful, the threat of quantum hacking is real, and you have algorithms in place which will render today's encryption invalid. And now something we can kind of take through something in the history. So in 1977, when RSA was first in place, it was said it will not be broken for the next 10,000 years. It was broken in less than 17 years in the year 1994. So what has happened since then is that the key size has got expanded, which Dr. MeitY also mentioned. But even today, when we use RSA 2048, it is claimed that it will take about 1 million years, but it is only for a classical computer. Quantum computers of something like 1 million to 10 million qubits, noisy quantum bits, can break it in real time. So what has happened because of this advent is that any data that you're looking at with about 5+ years of confidentiality is at risk. And the first victims are going to be government, banks, telecom operators, and data centers. This is the risk part of it. The second is that modern communication is designed in such a way that you cannot prevent data harvest. So data is harvested regularly, and you have no idea if what is happening to the data which you're sending on classical channels, right? So what we see is that without having quantum resilient encryption in place, there will be a collapse, and therefore it is the right thing to ensure that whatever methods we are using are resilient to both classical as well as quantum computers. This could be at software, hardware, both, right? So what we do is that we use quantum technologies to build quantum safe communication. So what we offer is that we offer solutions which are quantum resilient, and the security is not based on mathematical complexity. It is guarded by the laws of physics. And when you see that the systems that we have built are actually integrable with the existing infra. Now, this is what typically happens, that you actually need to have an encryption algorithm, a key which is being generated, and a channel to be shared. Now, with the solution in place, we can actually address all three problems, which is that your algorithm will be safe against both quantum as well as classical computers. Your keys are based on truly random number generators. We can talk about it later. The other part is that we are using fiber optic channel. What it means is that even before you release your data onto that channel, you can see if the line is safe. So now this is just a chart for comparative analysis, what happens conventionally versus what happens in quantum. So if there are two people, let's say typically it's Alice and Bob, but if they want to share, regularly what we do is that we have a method to exchange the key over the internet, and then we can encrypt the we can share the symmetry key through RSA or any public key method, and then we can encrypt the data and share the data with the other party, and the other party can decrypt it. Whereas this is not quantum safe. Whereas on the other side, we have QKD, what is called as a quantum key distribution. What it does is that we can generate keys on demand, and where there will be a dedicated line, and then it can be used for encrypting your data, and the other party can get to know. Now, the advantage is that it is one of the methods, or I believe is the only method, which can generate keys on the go without having any trusted party in between. And the security is guaranteed by the laws of quantum physics. Therefore, no advancement in computing will have impacts on its security. And if you use something like one-time pad, then it's basically an unconditional security. Coming to the another point, which is not typically also appreciated, but then is very important, is that whenever you want to share your data onto that channel, any attempts which are being made onto a quantum channel, you can find out if someone is eavesdropping. Now, this is something where you can discard the keys on the go. So you can use a multiplexed QKD systems, and you can ensure that even when you're sharing your data, you know what is happening to the data channel. This is one of the big advantages of using QKD. And since this is an add-on technology, it actually integrates with your physical layer. So therefore, no change. Of course, there are some versions in which some bit of change is required, but this is an add-on technology, and these are the advantages. So what we typically see is that this modeling of the security is based on infinite capability any eavesdropper would have, and will still be okay to use the system. And you can detect intrusion. So just to sum it up, this it's a bit exhaustive, but this is what we see is that in the near term we will have QKD linked networks, and as the PQC part, which my fellow panelist talked about, will also get integrated. So it's going to be more like a hybrid model. And strictly speaking, that QKD only helps in exchanging the keys, after which we use symmetry key methods to encrypt our data. So typically this is how QKD system is deployed, where you have a quantum layer on which the keys are being exchanged, and then the keys are being managed, then used for your communication, right? So this is one of the most, as Dr. Veni also mentioned, that is being deployed across different geographies. China is leading a race where they have a lot of, when they have 5,000 kilometers of quantum networks in place, in addition to the quantum satellites that is used between cities for communication. And the similar developments have been happening in Japan, in US, in Europe, and standards are being evolved. So this is one technology which is not just limited to lab, but is also being thoroughly used in different geographies. So with that, I probably will end because we have 5-6 minutes. So thank you so much. Yeah.
Good afternoon, everybody. Thanks to the Dr. Sudarshan for this invitation, and also greetings to my fellow panelists and to the audience for being present here. So I guess I had sent a few slides, but they're very much a high-level overview. So I think nothing is lost in their not being here. If they arrive, I'll probably use them. If not, I can just build on what Professor Veni Madhavan had spoken, and also my friend Mr. Animesh. So the main point, as already stressed by, there's an overview that was given by Professor Veni Madhavan, and one thing that stands out is that quantum random number generators and quantum key distribution are already visible successes. So probably many in the audience, though you don't have exposure to quantum technology, you're already aware that quantum random number generation and quantum QKD have been great successes. And we do have a representative of an Indian company, TACBit, who are in that technology. So the main question then now, in as far as I understand, in the quantum key distribution area, becomes one of how to increase the range of quantum, how the secure distance of quantum key distribution. Now, one can make use of quantum repeaters. So classically, you're all aware that you have repeaters where you can have these links through which you can boost the signal, and for a point-to-point communication, then you can use these repeaters to have very good communication. But in the quantum case, you have the quantum information is quite fragile, and as a result, you have a massive loss of information. Now, the information loss is not just through what you would call the classical noise, which would be which I would call as decoherence, normal decoherence, but there's a very quantum kind of noise called dephasing. So because of these two kinds of noises, quantum signals can get rapidly degraded. So quantum repeaters is the go-to technology then that we would want in order to have end-to-end quantum communication, say across maybe 1,000 kilometers. Now, quantum repeaters are a tall order with the current technology that we have. So even if we look at the top quantum cryptographers in China, maybe Switzerland and the US, I don't think they are really up to the mark as far as quantum repeaters are concerned. Yeah, so the other one, again, the big technological breakthrough that can help quantum key distribution is satellite technology. So here the idea is that you do not send them through fibers, or you do not send them through free space communication at the atmospheric level, but instead you would make use of satellites to beam down entangled photons, and that would go to end users who can then set up measurements, local operations, and classical communication, and then establish, once you establish entanglement that is reasonably noiseless, then that can be the basis for all sorts of further communication processes. Yeah, so I'll very briefly talk about the issues that come up here. One is something which is called the PLOB bound. And how a very recent, I would say, cute and simple method to extend the range, the secure distance of quantum cryptography has been proposed, and I think that's a very interesting direction that might be explored both theoretically and also technologically. So PLOB stands for Pirandola, Lorenza, Ottaviano, and Banki. So, but it's just called the PLOB bound, or PLOB bound, if you like. So, I mean, here, as you know, the next generation of quantum technology is going beyond the current successes of QRNG and QKD, is that we want to have a quantum internet, and also we want to have a fully secure quantum communication. In that, we might also throw in a quantum internet of things. But the key immediate challenge is extending the secure distance of QKD or quantum communication. And the obvious things is that we need satellite technology or quantum repeaters. But as I said, they're very difficult to implement. So are there simpler ways? And so before we go into simpler bounds, the first question to ask is, how far can I go with the simple technology? By simple technology, I mean just end-to-end communication without using quantum repeaters or quantum technology, using a lossy channel like an optical fiber. So the PLOB bound is what comes in, and what they essentially prove is that you have something like this number that you can take is like 1.44 tau, where tau is the transmittivity. So their point is that asymptotically, the key rate scales linearly with the transmittance of the channel. So an idea, so the idea for that remained for 5 years is that this is a bound that could not be overcome without repeaters. So that is where a square root improvement over it was proposed by the idea of a twin field system. And so the idea here is that you simply have Alice and Bob who send very weak quantum fields to each other. And yeah, so you can look at this figure that I've adapted from the figure at the bottom. So you have a source from which you just have, I mean, you have Alice and Bob on each side, and each of them send towards a central station a weak optical field, and the person, Charlie, who is at the center, will combine these fields and make a measurement. The key point is that these optical fields are very weak, and the measurement that he makes would be a single photon interference or followed by a single photon detection. As a result, when you have a detection that gives rise to a signal, you would have a single photon from one side and a vacuum from the other side. And as a result, you just need to, the degrading can only come from the party that contributes the single photon. So you see, you have a doubling of the distance for the same transmittance. And so that, if you like, is the origin of the square root improvement of transmittance. So having weak optical fields and single photon interference and single photon detection. So the graph here basically shows how this method allows you to go beyond the PLOB bound that I just proposed, I mean, that I just mentioned, but it is still lower than even, even if you have a single repeater as your link. So that would, of course, still give you a better performance. But as I said, we want to try to push the limits of our current technology without using repeaters. Yeah, the other point is that even here, because you have these two Alice and Bob sending these optical signals to each other, you need a very strong phase matching requirements and alignment requirements are there. And so that would have been a weakness of the twin field approach. So there was a modification of the twin field approach that that was proposed recently, which is, I think, rather awkwardly, despite its highly innovative cleverness, called the sending not sending protocol, where earlier I mentioned about how Alice and Bob send to each other weak optical fields, but here the theme is the same. But instead, the signal is read off, and the theme also remains the same in that it is about single photon interference and single photon detection. But rather than to both send fields, the data that's read off is based on whether one person sending and not the other person sending. So, I mean, after a bit of public announcement and classical post-processing, they will choose only those data from which one person, or for which only one person transmitted the field and one person didn't transmit the field. And in this case, it turns out that because it is premised on one person sending and one person not sending, these phase errors and alignment problems don't arise. But anyway, so that's just the overview of it. So I think that this twin field and its variants have a lot of, will I think have a great future as far as quantum technology is concerned. Thank you.
Should I share the screen? Yeah, am I audible?
Yes, yes, go ahead.
Yeah, okay. So thank you everyone for inviting me into this panel, and also thanks to all the speakers prior to me who have basically described the problems in a very thorough and a detailed manner. So what I am going to talk about is I'm going to talk about regarding the hardware aspects of the post-quantum cryptography. So as it was pointed out, the PQC algorithms are going to be an important aspect in the quantum cryptography research, and the topic of hardware security is also going to be applicable in case of post-quantum algorithms also. So the topic of hardware security, we have typically two parts. First part is the implementation of this algorithm. So whatever PQC algorithms, whether it's lattice-based or code-based, how to implement them efficiently on a hardware architecture. And of course, preventing the side channel fault attack or the hardware Trojan-based attacks on the cryptographic algorithms. So as it is already known, quantum computers are going to be arrive soon, maybe not in 20 years or 30 years, sometimes it will arrive. And at that time, the RSA relative curves and all the security protocols based on those algorithms are going to be vulnerable. So NIST has created this competition. Sorry for these slides, there typically has some error have occurred, but typically there are now round 4 results are there. In the round 4 results, we have crystal Kyber and crystal dilithium chosen as standard for the key encapsulation and digital signature algorithm. Alternatively, we also have BIKE, HQC, Psych, and classic MACLIS as the key candidate or the candidate for key establishment algorithms, and Falcon and Sphinx Plus as the candidate for the algorithms for digital signature. Now, please note that Psych recently, after the round 4 was published, has got broken, and therefore it is very important that we do not really focus on one particular algorithms. Rather, we develop a generic architectures or generic hardware framework which can support multiple different algorithms, such that if one algorithm gets broken or if the specification of the algorithm changes, we can very quickly switch to the new algorithms or new specification. Now, TLS 1.2, 1.3, we already have an OpenSSL benchmark or libraries which integrate OpenSSL NTRU, which is one of the round 3 candidate for the post-quantum algorithms. Now, when we talk about hardware implementation, there are two ways we can implement any hardware architecture. So one of the way is to you create a hardware peripheral. For this example, we are considering Psych P434 architecture, and you create an AXI interface to communicate between the processor ARM-based and the corresponding hardware accelerator. Now, this scheme works, but the issue with this kind of scheme is that the time to transfer the data, the post-quantum data has very large dimension, and the time to transfer the data from the software processor framework to the hardware is going to be much larger than the actual operation that is happening in the hardware. So as you can see in this example, we are spending around 5,000 cycles to transfer data, around 2,000 cycles to read the data back, but a simple multiplication which this architecture is doing, taking only 154 cycles. So for this kind of framework, we suggest that you kind of use an internal memory. In FPGA framework, we can use block RAMs to create this kind of architecture, and we can resolve this problem. So when you have this kind of memory, rather than passing the data, you can just pass the address of the data stored in this memory to do the corresponding operations. Now, this works, but the issue again is the overhead of this corresponding architecture. So in that regard, we can take advantage of the RISC-V phenomenon that has also recently occurred in the domain of computer architecture and organization. And in the RISC-V framework, we have the full control of the open instruction set architectures, and you can basically integrate the corresponding algorithms or corresponding frame architectures or hardware accelerators directly to the register bank of the RISC-V. So here you do not have any communication delay for the ASIC and communication delay for the AXI protocol, and therefore it is much faster than the ARM implementation or some fixed ISA implementation where you do not have the ability to modify the corresponding hardware or corresponding ISA. So once we fix this implementation framework, like whether you are doing ARM accelerator or RISC-V accelerator, and depending upon that, we create the basic framework of this architecture or this hardware accelerators. The other thing would be that how you can make sure that a single architecture can support multiple PQC algorithms. So taking advantage of the entity-based multiplier properties, we actually have developed a single architecture which uses a property called entity-friendly prime and entity prime lift, which can support all the listed lattice-based cryptographic algorithms. So in this case, you will have single entity multiplier, which can support New Hope, Kyber, which all were either in round 1, round 2, or round 3, the candidate of NIST competition. And therefore, even if, for example, tomorrow the Crystal Kyber gets broken and the NIST recommends to integrate Saber instead of Crystal Kyber, we can do that easily in the hardware framework without doing much modification. Compared to that, if you have a fixed architecture for Crystal Kyber and suppose Crystal Kyber exhibits some vulnerabilities in near future, then you have to completely replace the corresponding hardware architecture. Now, ASIC design is not cheap. So if you're creating an ASIC design or even an FPGA implementation, replacing that is not cheap. And therefore, developing generic architecture supporting multiple PQC algorithms is very important, as we never know when there could be a classical computing or even quantum computing algorithms that can break this system. One case study would be Psych, which has survived near 20 years of cryptanalysis, but recently got broken by a classical computing framework within 7 hours. So that is the reason, as a hardware engineer, I recommend to develop generic architecture for PQC algorithms. And of course, that also solve the problem of, this is a strategy that we use, and this is the corresponding entity architectures that we have developed. So this single entity architecture can support multiple, all the listed lattice-based cryptographic algorithms. So another important aspect of any hardware implementation is side channel security. So once we implement the computational intensive operations of post-quantum cryptographic algorithms on FPGA or ASIC, and we develop the corresponding hardware software co-design, we need to do the side channel analysis, and we can use the state-of-the-art side channel evaluation and leakage detection method to detect whether there's a leakage or not. For example, in this case, we are actually exhibiting the value of student t-test or TVLA, test vector leakage assessment, which are the de facto standard nowadays to detect whether there's a leakage or not. Without going into much details, if we can see a value above or below plus minus 4.5, we see there is a leakage. And when you are developing a secure or completely secure PQC algorithm, you need to focus on every aspect of that corresponding algorithm. Now, standard PQC algorithm, lattice PQC algorithm will have the hash function, which can be implemented by KCHAC, or we all need to have the sampler, need to have the operation of mask converter like Boolean to arithmetic or arithmetic to Boolean conversion. And as you can see that without the masked countermeasure, there is a very high amount of leakage which can reduce when we replaced the unmasked design with a masked implementation. So this will also allow us, like once we create this kind of generic frameworks and generic secure framework, this will also allow us to create a much more dependable hybrid system where we can support pre-quantum algorithms relative cut and the post-quantum algorithms, for example, say code or lattice together, because there will be a time where there will be switching over will happening, but at that time we would require to support both class of public key algorithm, like both pre-quantum and post-quantum public key algorithms. Now, generic architecture or generic hardware, generic secure hardware is going to be the solution to solve that problem. And also, There is a short signature scheme, the call for short signature scheme recently announced by NIST. So in that case, there will be more new algorithms will be submitted, the NIST call proposal, and which will have very short signature size. And that means that the field of PQC algorithms, cryptanalysis, and also the corresponding hardware design, side channel attack is going to be remain very, very interesting in the upcoming years. So in that note, I will conclude my presentation. Thanks everyone for their patience.
Should I share my screen?
Yes, I think we can share your screen.
Start. Please take about 5 minutes, possible.
Okay. All right. So I hope I'm audible.
I can hear you at least.
Great. So I will try to put forward the end user perspective and the end user impact of quantum computing on cryptography. There has been a lot of talk about impending doom on all classical cryptography because of the quantum threat. In fact, a lot of forums, panels have discussed this already. I would like to put forth a more end user perspective here. So as of today, as we speak, the highest number of qubits which has been successfully made stable by any company revolves around 65 and 66, with some well-known quantum computers managing to generate only somewhere around 20 to 53 qubits and not more. And I'll just skip through a couple of slides just to make this within 5 minutes. So one of the most interesting aspects to all cryptographers here is the ability for quantum computers to factor discrete logarithms, and which is expected to be quantumly very easy. So that's where most of the people out there are focused. One of the main things is for us to figure out how close are we to the impact, the expected impact on classical cryptography. Most of the esteemed panelists out here have already explained some of the cryptanalysis attacks which would be possible on both asymmetric and symmetric algorithms. But what we see or what we understand is that the total number of logical and physical qubits required for cracking these algorithms are quite some time far away in the future. So today we are somewhere here in the borderline where we are trying to explore quantum computing at this point in time. However, if we look at the total number of qubits that would be required in order to successfully break RSA 2048 using Shor's algorithm is quite high. So if we talk about the risk in short term is probably not very high, but in a period of 5 to 10 years or 10 to 20 years, that risk could be extreme, for which everybody has already spoken about the corrective measures being taken and discussed. So that will be all. I mean, this is all I can manage in 5 minutes. I hope that is okay.
Room for discussions. Open. Please just raise your hand and tell your name and the usual format.
Anyway, raise hand and in phantom theory you understand.
Yeah, we'll exchange some water.
Hello. So, sir, everybody says that source algorithm can break the integer, but it came in 2001 and factored only the number 15. 2012, number 21, and after that, nothing. 2019, 35 was tried and still it was unsuccessful. And as Mr. Prasoon told just some time back that RSA 1024 itself, millions of qubit will be required. And currently the highest is like, I think 127 qubit from IBM, and one more company is there which has 256. So are we just creating a hype about quantum computer? At least I do not see it in like next 2 decades, because in last 2 decades, the maximum factorization was done for only 21. So are we unnecessarily fearing it?
For what of this, I'll take start. Anyway, see, there is a what you call a kind of a commercial answer, and there is a academic answer. By and large, someday things will be factored. The current day 2048. Okay, the issue. I think the science is not worried about that. Both information security as a whole. Anyway, there is a time for change. One of the things is that you change to new things. Okay, so anyway, there was a time for crypto change, public cryptography. Okay, that may be various reasons. Okay, in fact, RSA itself, I used to say it is a beautiful thing done by the 3 professors in a classroom sitting in half an hour. They would have finished it, but they immediately patented it, 1978, then published it in CSEM, and the rest of the thing is 50 years it has stood, 78 or what, 40 years, and made huge money for MeitY and all the professors and so on. So there is a pressure perhaps to change anyway. RSA and ECC, it was attempted like that. BlackBerry phones company tried to advocate the use of elliptical cryptography in Canada, Waterloo, one of the main schools of thought on that. Somehow didn't succeed. Okay, BlackBerry phones itself we won't hear of. So there are different ways of thinking about it as a threat and other things. But more important, as we saw, new tech science, new technology, everything has to be driven. So now quantum science is driving a lot of things. So there will be many products, many spin-offs. That's what I also project. So in some sense, it will also be a endeavor to break 2048, and all this thing about millions of qubits, some of it is commercial, some of it is not scientific. Okay, so scientifically one knows a certain number of large qubits are required, but not only that, you can get around that. It's also known, reduce it, but then the more is other physics difficulties of decoherence and so on, which is also mentioned even in communication. It's fraught with many noisy environments and so on, which are, some of them are not known, but then one can get around them also. So there are, there'll be interesting science and research and development going on, and then there will always be this hybrid models and so on. So one of the best papers, I think, by Bernstein and so on, why all this thing fuss about breaking in polynomial time with Shor. Okay, say poly time for 2048 is just a few seconds on a quantum machine. Why a few seconds? Do it in a couple of days. See, now I told you 1 exaflop, 1 petaflop a year is the time for 2048, the best way. And I've attempted part of it in lower scales, best way, today's technology, today's science. So obviously the answer is trade-offs. So finally, that's engineering, all about engineering. engineering and commerce. You don't want to break it in 8 seconds, break it in 8 days. In which case there are other solutions. So you bring in new coding corrections, error controls, do small, I mean, very roughly stated. One scientist won't say like this, but there are ways to work around, okay, which is what the exciting games will be as far as 2048 track is concerned. Okay, that's all. Right? Of course, security-wise, there is one last angle that legacy is, what is that? You mentioned the word. Yes. You store today, break tomorrow. Huh? Store now, decrypt later. Wherever it's applicable, like countries sign some contracts of exchange of prisoners or something with digital signatures, that is really secret for many years. So you can break it. So this is the short answer. Right.
I'll just add it to you, like add to Professor's point. First thing is that the number of qubits which are required, let's say for RSA 2048, is roughly around 10 million noisy qubits. Okay, where we are having about 100 qubits in general, right? The companies which are working towards making scalable qubits, there are few companies like PsiQuantum, there is Xanadu, and all of them are aiming at 1 million qubits by 25-26. In fact, that is the only product they are coming up with. So, like, as someone who is working in this, I would definitely see that scalability was a problem when people were going with ion trap based quantum computers or something NMR based quantum computers. They had limits. Scalability was a problem. But with photonic based quantum computers, this is not a problem and is well accepted everywhere. Coming to your question about why we have to worry, I think we have to just look back at what advancement happened in computing. And I mentioned this, is that in 1977, similar things were proposed. Why did you have to increase the bit size, right, to 1024 or 2048? Was because that day the computing was mature enough to break the smaller key size, right? And that is what is happening even today. In fact, one of the proposals by Dr. Veni is exactly that. You have to increase the bit size so that you are safe against quantum computers. But then that is required. That has to be acknowledged. And when in 1994, when the Shor's algorithm came, people said that it is something which will take a century. In less than 20 years, you had a quantum computer, even though small, but you had it. And now it is true that you only have to worry when you want to have a confidentiality of 5+ years, because 27 to 30 is a time when you have a large scale quantum computer. So if you have a data which has to be confidential for that much time, that is where you have to really worry about. Otherwise, it's just like a data that is valid just for today. You don't really have to worry. So that is my answer to your question. Yeah. Shrikant, you want to answer something?
Anything else? Other idea?
I have a question. You mentioned you can break and you have a quantum computer in 2026.
Yes.
But my understanding is there is one challenge in quantum computing.
Okay.
Unlike the classic computing, if Dell builds, somebody else builds, the same algorithm works on both. But in the quantum computer, that does not work. Because the universality, like what exists by Turing, does not exist in the quantum computing theory. If you change one machine, you have to redesign the whole thing. Is that still true, or is it overcome?
So, I mean, it is being addressed. Like, I believe your question is, do we have a general purpose quantum, general purpose quantum machine?
It's not there.
No, I'm saying that it is being targeted. People are working on it. So that is my answer to it.
Targeting is an abstraction. It's not a real building.
Right.
Build a universal machine.
Right. I mean, yeah, you want.
Yeah, I just want to add something. I think I think I understand what you're saying, and I guess the answer would be that even designing a quantum software, there are no-go theorems against it, in the sense that, because if I'm right, software, let's say I have a number of, if I'm writing a program, I have if else loops, etc. So if I try to realize this quantumly, I have to keep adding ancillas and control operations, which will
one machine to another.
Right.
That does not exist in the quantum.
Yeah. So yeah, in general, software friendliness is not there. Yeah, you're quite right. So I suppose one.
Very serious problem. Of course, that's how quantum computing has to be addressed for certain algorithms.
Absolutely.
Not for a general
Yeah,
computing in general as of now. And there's a lot of things that need to be worked between, of course, quantum mechanics and computing. And that's a very serious challenge. But I think what you mentioned, quantum information processing, is a big thing that should go through for a varieties of things, but it may not be completely connected with the quantum computing. That's where I think headway like China builds a fiber optics or whatever that one is called.
Quantum communication networks. Yes.
In fact, in the race, surprisingly, Microsoft, which would have shown, I was jokingly put quantum Windows, quantum PowerPoint, and quantum MS Word and things like that, actually is silent. But on the science front, apparently their research teams are working on topological qubits or something, which is like something like what you might be hinting at, like a von Neumann architecture machine you can build to scale, and also matching.
No, always call a large machine on one implemented.
Yeah, correct. No, the stored program concept. Correct. So the stored program conceptual thing with the qubit match on a reconfigurable kind of a network is probably happening. And apparently Microsoft is going slow on, despite its deep pockets on the quantum machine itself. Unlike, the Googles and you hear them, not Microsoft. They tried something and then stopped.
It's a question of circuit building now.
Yeah, probably. But the corresponding physics is a different one. That's about it.
I just wanted to add quickly that the universality theorems that you have in classical, say for example, Church-Turing thesis holds good even in the quantum. Quantum computers don't affect Church-Turing thesis. They don't even affect for.
This is so robust.
Yeah. Yeah. Okay. Yeah. I get it. Yeah. But in terms of, yeah. I guess if I can summarize what, absolutely. Yeah.
Also cannot solve the undecidable problem.
Actually, can I ask a follow-up question on what Dr. Shamsundar said right now?
Yeah. What is it?
I was just wondering, I think the point you raised was very interesting, and clearly if you have to solve a new problem, you need a new quantum algorithm, and that is a non-trivial task. It's not like we can take a classical algorithm and just convert it into a quantum algorithm per se. But I think the question you were posing was, suppose you do have a quantum algorithm. So let's take the factoring algorithm that Shure has. The question now is, if there are two different quantum machines, you have the same number of qubits, but one is manufactured by D-Wave, the other is manufactured by Google, would the same algorithm work in both cases, or would you actually need to implement it in two different ways?
I think it has to be implemented in two different ways. There's no general algorithm can transfer on this to the another one. There's no general algorithm. People can transfer them, but it is case by case. Not a general one. That's a serious advantage in the, like one language to another, I can change kind of a thing is not coming. In fact, this was one of the main problems in NMR. If you had designed one algorithm for 8 bits, and now if you have to redesign, it becomes a real problem.
See, people, there are workarounds. In fact, there is some universality of some sort, like and or not gates, the quantum C-not gate, for example. That's in principle, paper, everything, there is universality and all that. The realization in the actual gating circuit may be different from the physics state, the quantum state. But apparently, the algorithm porting will not be difficult. But as what he referred to as, I think the quantum compilers, the front end and the back end, the input output, to prepare the state for a quantum machine and to be able to read out the quantum state at the end of wherever you are. To relate it to the current problem result or the issues, like in classical, the input output bottlenecks were there earlier times and so on.
I think more than that, right? What you're essentially saying is if you were thinking of doing things like debugging, that's really not something that you would be able to do in a very straightforward sense. I mean, from a very practical perspective.
Yeah, in fact, if I find it put, it's one field at least, it will bring in a physicist and a computer scientist and a mathematician to work together to run a program, which has not been the case in our current situation. First of all, getting them together is also difficult. Okay.
No, but that's true. But you're going back to sort of punch cards, essentially the same era in some sense. But yeah, sorry, go ahead.
Yeah, it's thanks for the pointing out. And I think, this debate has to go on and on, but we are also time. If no pressing hand raising, so we'll try to close this session with thanks to all the panelists, Tapas and Srikanth and Aryan and Debray and Prasoon. Thank you, and thanks for the audience.
Thank you, sir.
Madhu Madhuri.
We would also like to thank all the other panelists who have participated in this discussion. I may now request Professor Devavrata Das to kindly hand over the memento to the other panelists. Dr. Tapas Pandit. Dr. Srikanth. To Mr. Animesh. Thank you, sir. We would also like to extend our thanks to the speakers who have joined online, Professor Devipriya Roy and Mr. Prasoon as well. Thank you, sir. Thank you all.
So should we link it? Yes. I can play it on this for reading. No, yeah, please. It's okay. Oh, you. I thought you will connect him.
Yeah, good evening. Welcome to this keynote session. My good friend Jaideep has been woken up early to give a talk to us. So because of the hybrid mode, Professor Jaideep MeitY is a distinguished professor in the MSIS department of Rutgers University, and he is an alumnus of University of Mumbai and has a MS and PhD from Purdue University. His general area of interest has been data mining, data management, security, and privacy. And he has won several best paper awards, nearly 130 technical papers, and he's received the NSF Career Award, Rutgers Board of Trustees Research Fellowship for Scholarly Excellence, and Junior Faculty Award from Rutgers Business School. He is also, I think in my opinion, he is a fellow of IEEE and has been recognized as an ACM distinguished scientist. And then Jaideep can correct if I have done a mistake. And also, I think we worked together on running a ICIS couple of years back at Bombay. Jaideep, your time.
Thank you. Thank you very much, Professor Shamsundar. No, and especially for that kind introduction. So I'm really happy to be here today.
Sir,
Unfortunately,
your audio, we are not able to hear. I think you're muted.
Can you hear me now?
Yes.
Let
Sir, you're audible now.
Oh, okay. All right, perfect. Yeah, so again, thank you, Professor Shamsundar, for that kind introduction. I'm really happy to be here today, unfortunately, virtually, not in person. I was in India just last month, but unfortunately, the semester has now started over here, so I had to return back to the US. So let me get started. I mean, after that really interesting discussion, to something a little bit more pedantic, but something that is related to sort of the applications of public key infrastructures and general security infrastructures that we have, where we sort of see the field going ahead in I would say the next decade or so. And there is a sort of lot of interest in this, but I'll get into this general area of privacy preserving data sharing and analytics, some of the challenges that are there, and some of the things that sort of need to be done in this space as well. But again, thank you for this opportunity. If you have questions, please feel free to stop me at any point of time, and I would be more than happy to sort of answer those. So before I get started, the customary acknowledgements, quite a bit of the work that I'm talking about in this was funded by the National Science Foundation, by the National Institutes of Health, and the National Academies of Sciences in the US. And of course, none of this work would have been possible without my collaborators and students. The list below is very, very incomplete, but refers to the people whose work I'm in particular going to talk about a bit. So again, why are we interested in this notion of data sharing and analytics? Simply because we have a large quantity of data today. There's this huge promise of big data and AI/ML, vast amount of information being created, very little of it actually, which is being analyzed and sort of used. And for every organization, indeed every country, we really need to sort of make use of this big data or AI/ML technologies, because they have this potential to revolutionize innovation, competition, and productivity. And I just wanted to give you three very sort of obvious examples, if you will. But for example, in the healthcare sector, and we have specific figures for the US healthcare sector, use of these technologies would lead to sort of cost savings of over $300 billion a year, reduce healthcare expenditure by 8%, but more importantly, through personalized medicine, basically provide you better quality of life, better personalized treatments as well. Similarly, in the public sector administration, again, region, if you will, there can be a huge increase in productivity, and again, cost savings. For example, in the Europe public sector administration, the expectation is that it will save over 250 billion euros a year as well. And as we see in countries like India, other developing countries as well, this is even more important because essentially we need to make use of all of the resources that we actually have, and this not only increases trust but increases productivity as a whole. And the third and final example is just the US retail sector, which I'm not going to really go into, but of course there is improvement in productivity, but also in net margins that are possible through the use of these technologies. Okay, fantastic. So we have data, we really should use it, and we would be able to sort of realize great gains in a lot of different things. So what's the problem, right? Where is the rub? And the problem that we see, the peril, if you will, is that typically there is insufficient in-house capabilities or expertise for ingesting this data, for longer term storage, for computation, for analytics. But more importantly, much of this data is actually sensitive, and at least in the short term, if not the long term, if you will, and there is this threat to privacy and security. So there's the threat to individual privacy. If you remember what happened, for example, with the information that is being collected through Aadhaar and the data breaches that have happened in that space as well. But at a organizational level, there is also competitive advantage to be gained from information. And again, simply sort of having these global registries or simply going ahead and sharing this information can be problematic, either in terms of violating regulatory or confidentiality laws, or in terms of what use you can make out of this information. You can use it in ways that were very unanticipated and do fairly bad things as a result of this. So often data is strictly controlled, which is a good thing. But the bad thing is that it's stuck in silos, as it should not be, and it cannot actually be used. So just to sort of hammer the point home, because people may ask, what does it matter, right? I mean, a lot of data about me is already out there. Is there really this threat to privacy, and security? Is it really a big problem? What can you know from data? A huge number of things, as it turns out, right? So there have been attacks over attacks and all sorts of unexpected things. Human beings are very ingenious, if you will. So for example, even from the last name, from the surname, we are able to identify personal genomes, which is pretty surprising. Or you can identify participation in complex DNA mixtures, or I can look at your EEG data and so on and leak financial and identity related information. I can model the facial shape from DNA or participation from summary statistics, even something as simple as putting in reviews for Netflix, which Netflix doesn't allow anymore, but it used to. But let's say Netflix reviews or Amazon Prime reviews, you can link things back to IMDb and you can identify users. And indeed, you can even identify a complete patient's information from aggregate and anonymized queries. This is something that, in fact, we did a few years ago. But all of these things are easily possible. And more attacks are sort of being developed, which essentially say, hey, you know what, just going ahead and thinking that, you can't use data in bad ways is absolutely not true. So the list goes on and on. And often the first solution, especially from a governmental perspective, but in general that people rise to is just to say, oh, why don't I just aggregate data? Let's not worry, we are not revealing individual data points. Is that good enough? And remember, we are not just talking about things like encryption. Of course, you need encryption for data at rest. But when you're computing over data, especially when you're revealing the results over this, the question is, can I just aggregate and is that good enough? And of course, the answer for that is no as well. And one, super small snapshot that I just wanted to sort of briefly talk about. This is some work we did in 2013. It got the Distinguished Paper Award from the American Medical Informatics Association. We basically were able to run a bunch of queries against this very well-known and publicly accessible data sets called HCAP, which is the Healthcare Cost Utilization Project. It basically captures data from all of the hospitals in all of the 50 states in the US and makes it available in aggregation. So you can run sort of queries which are aggregate queries. You basically get contingency tables categorized by different sort of things. So in this case, for example, we were asking how many women had ovarian, or how many people had ovarian cancer, And can we classify that by age and by race and ethnicity? And the stuff that you see in yellow is everything that has been suppressed. This is aggregate information, things have been suppressed. But actually, you can run branch and bound sort of algorithms for inference, and you can just run queries against this. And we essentially found that, it was, in this case, one particular Native American woman who went to a privately owned hospital, who was exactly 75, did not pay by private insurance, stayed in the hospital for 34 days. And we even know how much she had to pay for this treatment and things like that. So again, just aggregation by itself clearly is not a solution. We need to go well beyond that, so to speak. So the question is, what can we do? And we want to link that back to sort of the infrastructures that we have, like public key infrastructures, and can we sort of create supporting infrastructure for what we want to sort of do? So again, we need to understand the data. We need to understand the usage. What is it that you need to do with this data? And then match the techniques to the required tasks. And from a privacy perspective, what you really need to do is ensure sort of three things. First is ensure process privacy, which means that whatever you're computing, the process of that computation should not be leaking any additional information, so to speak. The second is we want to ensure output privacy, which means that if you learn the result of this computation, then the result by itself should not be leaking any additional information. And I'll come and talk about this in just a minute. And finally, you want to ensure sort of control over the data used in this space as well. So every party, not just the individual, but organization, should be able to precisely control what data is used for what purposes in any given computation. So again, protecting the process. People here may be aware of this already, but there is a huge field or subfield of cryptography called secure multi-party computation, which basically enables this. Okay, and the idea is that, okay, if you have any function f and sort of n inputs, x1 through xn, which are distributed at those n different sites, we somehow want to compute this result y, which is the function f applied over x1 through xn, while revealing nothing to any site except its own input and the result. So every site should, of course, it knows its own input, it would get the result. And the reason why nothing is starred is that, of course, you're allowed to learn something more. Anything you can infer from the result and from your own input is fine, because that you would get in sort of in any case, even if there was a trusted third party to sort of do this. So this, the great news, this is a subfield of cryptography which has been around from the 1980s. One of the biggest sort of advances was to show that, hey, this is actually possible. Andrew Yao first showed that with the Yao's millionaire problem, that secure computation is possible if the function can be represented as a circuit. And the idea was simply securely compute each gate of the circuit and continue to sort of evaluate the circuit as well. And again, this was a, in some sense, the word seminal is really overused. So I will call it an earth-shaking result, because we know, theoretically speaking, that any computation that you would carry out on a computer can be represented as a circuit. And therefore, in theory, what this means is that anything that you want to do can be done in a fully distributed way, wherein you would learn nothing, so to speak, beyond your input and final output. And it was extended not just to, from two parties to multiple parties as well. So this has been around for now close to 40 years. So what's the problem? The biggest problem has been that, yes, this shows in theory that everything is possible, but in practice, there is this huge problem of efficiency. Because if you think of representing the computation as a circuit, and we are really talking about a Boolean circuit, you would have a huge circuit. And essentially, when you're talking about analysis over large quantities of data, this becomes even worse. I mean, this creates a, when the input data size is huge, you have this huge problem with sort of efficiency, which basically means that you can't just directly go and sort of do this. The good news is that recent work has made a lot of complicated analysis actually feasible. And I have some links over there. You are welcome to look at those. Slowly, we are maturing to the point where this could actually be provided as sort of pieces of software and sort of general analysis tasks can be carried out with techniques of this kind. But that's great, because again, what we need is infrastructure in order to do this that is already out there. And I'll come back to that in just a few minutes as well. The second part of the puzzle is protecting the output. And for this, for the most part, we can use something like differential privacy. And for those of you who have not been exposed to differential privacy, the basic idea is actually quite simple. Just consider two cases. One, again, a database where, two identical databases, except that one has John's information in it, the other does not have John's information in it. And any algorithm or mechanism that you are going to use can be considered differentially private if the output of that mechanism, the output of that algorithm over both of these databases is roughly equivalent. Okay, clearly not exactly the same, but it has to be roughly equivalent. And the reason why we claim this protects privacy is that someone who just looks at the output, what they get, is unable to figure out, oh, was the input the first or the second, which means they would not know whether or not John was part of the input that was used to compute this result. Okay, so it basically provides this plausible deniability for John, who can claim that, hey, I was never part of the result, never part of the input that was provided to this algorithm. And of course, in precise, if we go into this, there's a formal definition, there's a privacy parameter epsilon, and which has to be greater than 0, but smaller means more private. And what we really claim is that any mechanism M is epsilon differentially private if for every pair of neighboring databases, so X and Y that differ by one record, and for every possible output, if you will, the probability that you get that single or set of outputs for X and the probability that you get that, again, corresponding set of outputs for Y is bounded by e raised to epsilon. So is within a multiplicative factor of each other. And the smaller the epsilon, when epsilon becomes 0, as you can imagine, the probability is exactly the same, which means that, you've basically learned absolutely nothing, so to speak. But because this applies to all pairs of databases, if you will, in general. So this is a very nice sort of model. Again, this was created in 2006, so to speak. And if we sort of use this, we can guarantee to some extent output privacy, meaning just from the output, you would not be able to infer anything about people. So the question is this sufficient? Can I just go ahead and take SMC, take differential privacy, and say that I'm done? Does this solve the problem? Actually, not in theory, and also not in practice, as I'll just get to in sort of a few minutes. So by itself, this is great. This is a great starting point, but it's not sufficient. And I just want to give you one specific example of why, for example, this may not work. So in particular, say differential privacy won't work. And for that, I'm going to choose this example of outlier detection or anomaly detection, which again is a very, very standard data mining or data analytics task and has tons of applications in finance, healthcare, security, law enforcement, you name it, right? Finding anomalies or exceptions is really, really important. And it has lots and lots of different applications. So in particular, let's say you're trying to flag money laundering transactions in a privacy preserving manner. So first, why would you want to flag money laundering transactions? That's obvious, right? Because we want to know who is committing financial fraud. So the enforcement directorate, for example, would be very interested in knowing what's going on, just like the SEC over here, for example. But why privacy preserving? Because of course, for the people who are not doing anything wrong, we don't want that government, for example, or even banks have the ability to look at every single thing per se in terms of what we are doing. So again, I'll just show a very simple example where we are trying to do this identification using just the amount that is transferred. And you can think of the database as the number of such transfers that do actually occur. So here, anomaly, if you will, or a money laundering transaction is something that markedly deviates from other records. So something over here whereas normal would just be, say, sending money to your family or what have you, lots of different things over here. And accuracy clearly is mission critical to this application, if you will. We need to be able to identify the anomalies correctly. But we are going to focus on data dependent definition of anomalies. So this point here is an anomaly because it's very different from all of the other data points. Clearly, if everything was the same or similar to that record, it would not be considered an anomaly. It would really be normal. And then we, of course, have a privacy puzzle that if there's high accuracy, there's no sort of privacy for outliers. We will know what the outliers are. But if there's no privacy for outliers, because the definition of outliers is data dependent, we don't have any privacy for the data defined normals as well. We basically know what would be regions of space which are quote unquote normal. And then the question is, okay, so what do we do? You know, does that mean that we have no privacy for anyone, regardless of whether you are an outlier or whether you are normal or somewhere in between? And the answer is, you know, somehow our answer should not leak information about the normal records. We don't want to protect the anomalies because that is the required output, but we do want to protect the sort of normal records and be able to sort of do that. So I'm going to give you a very, very small overview of this. I won't go into details on this, but in particular, one notion of data dependent anomalies are what are called beta R anomalies, which was defined by Nor and Eng in 1998, quite a long time ago. Which is a very simple notion. Basically, it just says, okay, take a record and look around it. If it has beta or fewer records with distance r within the sphere from it, then it is an anomaly. Okay, so basically look around you. If you are alone and by yourself, you're an anomaly. If there are sufficient numbers of other records around you, you're not. And then I could just say, the anomaly detection function is, you know what, if I ask, is this kind of thing, you know, let's go over the database, look at all of the different types of things that could happen. Just tell me all of the anomalies. That's the anomaly detection function. And here, typically, outliers are a very small fraction of the total records in the database. And small changes in the database don't sort of alter the record's outlying behavior. So databases as a whole are pretty sparse. This is standard, you know, essentially this is what happens in real life anyway. So I just want to very, very quickly tell you why differential privacy has sort of poor accuracy in this particular space, right? So here are, and I'll just give you the intuition behind it. Here are two databases that are neighbors of each other. They are basically identical, okay? So the database is represented as a histogram. These are sort of the values which are being transferred. And the bar over here in the histogram is telling you how many such transfers occurred. And the two things are neighbors because they're identical. The only thing extra is that second last thing over there. And the anomaly detection function in this case says, oh, only this is an anomaly, whereas the anomaly detection function in this case is both of these are actually anomalies. Why is the other thing not an anomaly here? Because it's not present. If it's not present, it can't actually be an anomaly, correct? So actually, I'll ask even a much more simpler question, not what are all the anomalies, but is something an anomaly? So I'm just asking, is this kind of thing over here an anomaly for every database? So it's like someone saying, oh, if such and such a person was flying, you know, given this values, is that an anomaly? So it's just a simple anomaly identification question, so to speak. Now, the problem is that when you use a guarantee like differential privacy, you're basically saying, oh, for a question like this, for every possible pair of databases, you know, the answer, the likelihood of getting the same answer has to be roughly close to sort of each other. Now here, the answer in the first database, the answer is no, but in the second database, the answer is yes, which means whatever mechanism we are using, there's going to be an error either on the left or on the right. So in fact, we can show by the bound that the maximum error for one or the other has to be over 1 plus e raised to epsilon, which for small values of epsilon essentially means errors which are, you know, close to 0.5 or even worse, which is almost the same, you know, essentially as throwing a dice. And this means that we are going to make lots and lots of errors, not for the blue points, but basically for all of the anomalies and all of the empty regions in sort of space over here. And this it doesn't matter what differentially private mechanism you use, even the optimal differential private mechanism is still going to have precisely this problem. It simply cannot be sort of avoided. And this outlier identification query, forget outlier detection, even the identification is pretty much impossible. So this problem basically exists as a whole, and this bound, so to speak, that we looked at, actually, it turns out it really depends on whether the query is existence independent or existence dependent, whether it depends on the existence of a particular record. And when things don't depend on a particular record, then you can still use differential privacy, no problem. You can go ahead and use that. But when the answer depends on the existence of a particular record, like in this case, is this thing an outlier? It depends on whether the record is present or not. Then you cannot use differential privacy. We are basically kind of just stuck. So as I said, the difference is just whether the answer is contingent on the absence or presence of a particular record. So basically, if you're just asking, is there a flu epidemic? How many outliers are in the data? We can still use differential privacy. But if you're saying, what are the outlier records? Is the record I an outlier? You cannot use differential privacy, not to give answers with any reasonable sort of utility. So we sort of came up with a principled approach to private outlier analysis. And the key thing there is to look at whether the query is existence dependent or not. And if it's not, then you can use DP. But if it is existence dependent, then we try to reduce it, to decompose it into a set of sort of queries, which hopefully can be existence independent. And then you can still use DP. But in the worst case, you have to use some notion of relaxed differential privacy. There is no real way around it. And the particular notion, basic generalizations and variants don't work in this space. But the particular notion that we sort of proposed is something called sensitive privacy, which I'm not going to go into in a lot of detail, but I'm just going to show you one picture, so to speak, which will give you the overall sort of intuition of this. So, and this is just the difference between what we have and what we want, okay? So on the left, what we have is differential privacy, where you actually have same privacy for all. So as you see here, you get exactly the same privacy for everyone, which is a good thing. But on the other hand, what happens is that your accuracy really drops. So this is, by the way, synthetic data. It's just a Gaussian, but it serves to illustrate the point that you get good accuracy for this mass in the center, but for everyone else, including the spaces where nothing is happening, you get horrible accuracy. It's very close to 0.5, which again is the same as tossing a coin. What we want is to somehow vary the privacy by outlierness, which means the huge majority of points in the center, everyone who is normal is getting the same privacy as in the old case. But as you are, acting in a more and more aberrant fashion, the degree of privacy you have reduces. And what this lets us do is then have accuracy at all of the points, except at the boundary where things are still a little bit difficult, but you can improve the accuracy in every other space, so to speak. And the interesting thing is, on the left, we have the optimal DP mechanism. On the right, we actually have achieved precisely this using a specific sensitively private mechanism, which I don't have sort of time to explain, but I just want to give you the key intuition that all we are doing is requiring privacy protection of every record that either is or becomes normal under a small change in the database. So basically protect everything that is normal or that can potentially be normal under some kind of small change in the database. So the first part is the same as differential privacy. The second part is the only sort of different thing. And this matches very well with what you want to do with anomalies, because anomalies are records that markedly deviate from other records. So small changes in the database should not change the status of an anomaly itself. It will protect all the normal or potentially normal records, just not the sort of anomalies. So I won't go into more details on sensitive privacy in particular, but I am going to talk a little bit about what is the infrastructure that we need, and especially from a cryptographic perspective, what does this imply? What do we need to be able to do? So going ahead, what do we need, so to speak? Because what we really need, what this sort of serves to show, is that you need a more nuanced view of privacy. You need sort of ways of accounting for privacy when we are basically saying how much information is being revealed. You need ways to explain privacy, what information is being revealed about you, visualizing what is actually happening, and exploring trade-offs with privacy. What would I be able to do given what information I'm willing to reveal, and so on. And the key point there is sort of the infrastructural support for privacy. So I think this is where it relates very well to existing sort of cryptographic infrastructures as well. If I want to work on distributed data, can I come up with good architectures where, again, I can make use, perhaps have this infrastructure already set up. There could be a few sites, what have you, which would basically turbocharge the possible analysis of data in this distributed sense while providing key guarantees of privacy, so to speak. So the next generation of privacy protecting systems actually will consider new architectures, incorporate diverse privacy models, and even take a socio-cognitive sort of approach to solving these problems. So if you remember the old why Johnny can't encrypt papers, just having technology is not sufficient. We really need to actually explain and to understand when things work and how they work and why they work, so to speak. So just one short point, changing the architecture in particular, where I think we can really create cryptographic infrastructure for this. I think what we are more and more going towards is this notion of collaborative computing, privacy preserving collaborative computing, where the input data, whether it comes from organizations or from individuals, would get split up between sort of multiple servers. These servers can be placed in trusted entities. For example, one could be in C-DAC in Bangalore, another could be in C-DAC in Pune. It could be within universities, what have you. I mean, there can be a few trusted entities, absolutely. And now if the input data is split across all of this, you can still use sort of, garbled circuits, SNC approaches to sort of carry out computation over this information. And especially if we leverage the computing, leadership computing facilities and sort of the supercomputing power that we are, especially in terms of parallelization, that we are able to bring to bear today, I think it is possible to take existing functionalities and even come up with general purpose compilers that would let you then carry this computation out in general. A few other things though from the practice perspective. What if you want to enable privacy preserving sort of exploratory analysis? Can I get first cut, approximations of usefulness of data? As we know, in many cases, the real problem is not just, oh, I need precisely this, encrypt that data, send it over, and we are done. We don't know what we need, and we are not sure what kind of cleaning or aggregation sort of needs to be done. So potential solutions in this space, which are not cryptographic, but the basic idea is that of creating synthetic data or sample data sets that sort of preserve the structure and semantics of the original data, but not exact values. That would give you some way of sort of preserving privacy while giving a first order sort of approximation of utility, if you will. And then making it work in practice. Again, differential privacy as a whole provides a nice framework for quantification, but there are a lot of assumptions. There are issues about data imputation and data sampling, and even data dependence, so to speak. So like if I use this for the census, if I'm just counting the number of children in single parent households, we can basically double count. There can be other problems that sort of occur in reality as well. So I think we do need more work. And again, I stress the point that we need infrastructural support where we basically specify prefixed values and very standardized protocols that are used for some of these things. And one particular thing, one last thing with respect to this, I talked about enabling meaningful control over data. I think there we still need traditional sort of security technologies or models, if you will, like access control. But we can couple that with sort of new technologies like machine learning and analytics to sort of automate policy configuration and management. So access control is still key. You're going to need that in order to ensure that proper control is put over data. But the question is, as evolving situations occur, can we automatically, without having to involve the security administrator in every single decision, is it possible to learn sort of data sharing policies or to explain current access policies or impact of changes, and basically just make the job of the human, the very experienced human in that situation a lot easier. Can we sort of do that to make this happen? So one last thing, I will very, very briefly talk about this, because this was very interesting and very relevant for all of us. We've all been suffering for the past 3 years through COVID in any case. But I wanted to talk about crowd sensing of data, and again, infrastructural support, and how we can sort of make use of some of these technologies. So remember, at the start, we had lots of problems in terms of testing for sort of COVID. So it was a very difficult problem to sort of detect COVID hotspots, especially to track them over time. Interestingly enough, this problem of detecting COVID hotspots was actually anomaly detection or outlier detection problem, because a hotspot is an anomaly. But the good thing here is that knowing whether something is a hotspot or not doesn't depend on any single record. So it turns out that you can actually use differential privacy in this space. Okay, so we don't need to worry about relaxed models. Differential privacy as a model will actually work in this space, as long as you collect the data also in a private way. So one problem, though, is that if you're asking these questions, so we actually came up with this app. This was again supported by NSF and NIH, which would let us guarantee privacy while crowd sensing. So, you could ask questions, let me go to Google Maps and just draw a region and say, oh, is this a hotspot? I could ask how many people reported feeling symptoms in the past 8 days in New York City. And I would get an answer. Then I could just basically look at everything, the whole thing on the map, or something really, really small, my particular block, if you will, and ask the question. The problem is, once you open up such an interface to anyone and everyone, an arbitrary number of such queries can be asked, differing in sizes and regions. So one query doesn't leak a lot of privacy, but all of them taken together is a huge problem that actually adds up significantly. So we could use the epsilon DP Laplace mechanism, but after n queries, you lose privacy with every query essentially, and things are going to be horrible. We could have done something more different. You could have sort of this fixed grid, if you will, a very, very fine grid, if you will, and then you wouldn't have a privacy loss. But then guess what? Whenever you're looking for any region, now you have to aggregate over a whole bunch of these small regions, and you get errors from all of the underlying regions, so to speak. So you huge number of partitions, which requires huge space, but more importantly, it's very highly erroneous for queries for larger regions, which you absolutely need when you're looking for sort of hotspots. So what we ended up doing was a combination of techniques, which again, I don't have time and I won't go into, but I'm just going to briefly mention that the key idea here was sort of just to partition space. So spatial partitioning via a very well-known technique like quad tree. So you just take the unpartitioned space and just chop it into 4 quadrants and keep chopping up the quadrants while there is data in each of the quadrants. So I would just take this, which is everything, chop it up into 4 quadrants. And since there are only sort of more data in the top left and the bottom right quadrants, I further chop those up. And I create as many quadrants as sort of necessary but to answer queries. But the other interesting part was it's not just spatial data, it's spatiotemporal data, right? Because we care about the past 8 days or the past 14 days or what have you. So you need to sort of partition dynamically updating spatiotemporal data. So we have data at day 1, day 2, day 20, day 50, and so on. It's basically infinite time horizon, if you will, but a sliding window over that time horizon. So essentially for that, I'm not sort of going to go into this at all, but we have a very novel way of partitioning so that you don't create a tree at every single day, so to speak, and simply add up, again, have a privacy loss. You can actually minimize the privacy loss by being clever in the way of which days are you aggregating together to answer the maximum number of sort of queries. So we ended up sort of deploying this in reality in the world, through the Apple Play, through the Apple Store, through the Play store as well, and so on. And we reported on this very recently in IEEE Intelligent Systems. But again, this was where you develop an app. Now this part is secure. You are having the reporting of COVID-19 symptoms from individual users from their smartphones. You store the data in a secure database. And then in the background, every 24 hours, you get sufficient data, build these quad trees, and then update them. And now you can, when any query is posed, you can compute the queries via these quad trees and then go ahead and sort of answer this. So I would say you still need secure communication for the first part, but you need these underlying, differential privacy. And if you're distributing it, SMC technologies to sort of do the computation efficiently in the background as well before you're able to sort of answer these sort of queries in practice. And it gives you almost identical results with sort of guaranteed privacy. So, I'm just showing you a bunch of heat maps, if you will. One, the top level and the bottom level. One is in terms of the original counts, the other are the differentially private counts. And it turns out that they are pretty much the same. The same is true in terms of the stacked bar charts. I won't go into that, but you end up getting something that essentially works. So I'm going to sort of stop, if you will, and this is essentially, I think, my last slide, if you will, by talking a little bit about future directions in privacy. And where do we need to go, especially from a PKI infrastructure perspective as well. So some of the problems in privacy are, very straightforward in some sense that, we need to develop lightweight solutions that are robust to more powerful adversaries. Everyone just operates in sort of the semi-honest model at this point, where they expect people to follow the protocol. Does this always work in practice? And then how can we truly measure privacy along with utility so that exploratory analytics is truly possible? But more importantly, we are going to have this Internet of Things is happening, large sensory platforms, if you will, in places like this. How do we develop private in environments like this? How do we develop private analytics? And can we optimize for things like computational complexity or even power use? Can we develop cloud infrastructures that minimize the use of power in this particular space? And I think over here, we have a lot of lessons to learn from sort of existing infrastructures like the PKI infrastructure as well. And the question is, how can we deploy these things in practice so that they may actually end up being used? So not just in a theory paper or in the lab, but really have it be used in practice. And for those of you who are interested in things like this, the National Institutes of Standards and Technologies, NIST in the US. So the US and UK government in collaboration recently came up with a privacy enhancing technologies prize. There's a competition that is ongoing where they're looking at two sets of data. One is financial crimes data. The other is basically pandemic forecasting. So again, health data, if you will. And the question is, again, in these sort of distributed use cases, what are the privacy challenges and what are the privacy enhancing technologies that we can use to sort of make this happen in a accurate but yet scalable and private way, so to speak. And then the last point over here, which doesn't have directly to do with sort of PKI or with crypto, but which we've all realized, purely technical solutions are great, but they don't work in practice. Again, like encryption has been around for forever, and we are still finding out that people have trouble using it appropriately. So can we develop socio-cognitive ways to improve privacy? And can we look at the interaction between privacy and other properties such as fairness? What are the roles that we have in order to play so that we can make this happen in practice while ensuring all such properties are held appropriately. So with that, I will basically stop for questions. I hope I've not gone over time, but I did want to stop for questions.
Thank you, Jaideep, for an excellent talk on privacy. Any questions? Yeah. There is.
Hello. Hi, I'm Atul. I was having this discussion with the Animesh or T. I basically come from AI. This is in context of the earlier panel discussion. There's a immense perceived risk about quantum computing in terms of the existing cryptographic models. I'm just wondering, and maybe Dr. Jaideep, you mentioned heavily about analytics. So my question to you is, forget about QC, which is still fairly futuristic, but even the existing machine intelligence, has that been ever applied in terms of cracking the existing cryptographic models, even the most complex ones? I mean, we're not talking about brute computational power to crack cryptography. We're talking about intelligent computational power, I mean, any effort in that direction which you're aware?
Yes, there are. Okay, so again, there has been classical cryptanalysis, if you will, and which goes well beyond that of sort of brute force attacks in any case. But coming back to your question, absolutely, there is in fact quite a bit of work in this space. So even, for example, when you're thinking of differential cryptanalysis, you can think of timing attacks and so on. Now there is the use of basically large-scale computational power and data analytics technologies in this space, simply because, depending on the particular model, let's say you have a NCPA sort of system that you have to break, you still have sort of Oracle access to it. You can collect a lot of data points and then essentially figure out the right queries to ask. So there is some degree of work along these lines, and especially even from a hardware security perspective in terms of finding vulnerabilities against this. Yes, absolutely. I mean, this is a burgeoning area of work, if you will. The one thing I have not heard of yet is the sort of use of, since people like to put buzzwords together, I still haven't heard of anyone saying, oh, let's create a neural network to sort of encrypt or decrypt data on the fly. And that doesn't make any sense. And that's just a joke, but regardless. But yes, absolutely. There is the use of sort of modern ML technologies to sort of target this, if you will, or to improve this. I'm not sure if that completely answers your question, but I would be happy to discuss it afterwards as well.
No, sure, it does answer. I mean, in fact, I would just say that that is probably a more realistic and imminent threat, if at all, to these cryptographic models than a very perceived decades down the line quantum computing based threat. Anyway.
The differential privacy, in my view,
it
is applicable for a different class altogether, in a sense. Okay, so for example, if you have sensitive attributes which are not real or integer, adding error is not a easy thing. And if you, in fact, if you have many quasi attributes, how would you arrive at a probability distribution on the sensitive attributes so that the differential privacy can add appropriate error? That is not a easy thing. Actually, anomalies is not a thing that the differential privacy is going to handle, or it should not handle. And the classical anonymity, diversion, closeness, where you use a lattice-based kind of a thing, where you can suppress or not suppress, it is left to you, kind of a thing, or the other. So in a sense, I think there should be a good categorization, like even Apple and Google use differential privacy, but they use for a limited period of time. One does not know how much privacy is being given to a trusted party of Apple and Google. But Apple and Google are the ones who are trusted agents of the world, so they have all the data. So you can't question that kind of a thing or the other. And so, and that is the basic thing or the other. And if you want to find anomalies, the only way, in my opinion, privacy can be preserved is homomorphic encryption. Hopefully, it breaks a new company is going to give solution without encryption, I do not think utility and all these things can be preserved. But however, in my opinion, if you have a statistical database kind of a thing like a census data and all the other things, for which
Right.
I think otherwise you gave counterexamples for which there is a case against differential privacy being deployed by US Census Bureau. All of the examples are given there, kind of a thing. Thank you. And then we look forward to your new privacy model to see how it could be used, and in the COVID kind of a thing are there. Thank you, Jaideep, for giving
Sure.
your time and then giving. Thank you.
Thank you. Thank you very much for the opportunity.
Thank you, sir. We have come to the valedictory session of the conference program. So for that, I request the following members to the dais: Dr. Prashant Mishra, Dr. S.D. Sudarshan, and we have a special guest today, Mr. Anil Jain, CEO of National Internet Exchange of India. Welcome you to the dais. Mr. Ashish Banati. And we have a chief guest, Professor Debabrata Das, Director, IIIT Bangalore. Welcome you, sir, to the dais. And Professor R.K. Shamsundar, sir, please to the dais. Yeah.
Not seen you for a long time. Yeah, even a break.
Okay. Now, I request Dr. Prashant Mishra, the chair of the IEEE Computer Society, to address the gathering.
Good evening. I, as chair of IEEE Computer Society, probably this is the closing statement from Computer Society. I think this was the first time Computer Society and IS societies of IEEE Bangalore section came together to have this PKI conference. And I was present yesterday. I was again present today in the second half. And I must say that the proceedings have really come out well. We have a fantastic lineup of speakers, both from the paper point of view and also from the panels and the discussion point of view. I hope you have gained as much as we have gained by organizing this conference. And we were just discussing that we should have a follow-on series of this as well. So if you believe that this is a area that is very important and you would like to contribute to it, please look out for the next edition of PKI 2023, which may be announced very shortly. As I said, IEEE Computer Society is a competition society that looks at ways how we can contribute to the competition advancements of society. And PKI is an area that is very important in that regard. So along with this particular conference, there are other ways we are thinking of trying to contribute to the PKI ecosystem. And in that regard, I invite volunteers to join this endeavor. So if you have certain ideas as to how you can also contribute to growing this PKI ecosystem, please get in touch with IEEE Computer Society or any other relevant IEEE Bangalore societies, and we're very more than happy to talk to you and understand how we can take this forward. But without further ado, let me first of all congratulate you all for being here for 2 days, and I wish to see you all in the next edition that we announce very shortly. Thank you all. Yeah.
Thank you, sir. And now it's time for announcement of best papers. For that, we have Dr. P.V. Anandamohan, who has joined us in the online mode. Sir, are you able to hear us, sir?
Yes, I am able to hear.
Yes, sir.
Good afternoon. I am very sorry that I could not be there because of severe toothache since 2 days, and now slightly today it is better. So actually now we got 80 papers, and then we have got them reviewed, And we have included some papers, in the relevant areas also, like IoT, machine learning, and which have some relations with blockchain and all that. And I'm very happy to say that we have selected, that is based on the reviewers' reports, 2 papers. The first one is by Joel Hoglund, I think he is here, towards automated PKI trust transfer for IoT. I invite him so that he can receive the memento.
Sir, actually, he is not present. You can go ahead with the next.
Okay. Then the second
we
award.
We will send him the award of appreciation through email to him, sir.
Okay. The second award is for paper number 6643, PKI for IoT using the DNS infrastructure. That is by Sandoz Balakrishnan, Ibrahim Ayub, Benoit Ampo. Thank you very much.
So we request Mr. Sandosh Balakrishnan to the dais. I request Sri Anil Jain sir to present a small memento for this particular recognition. Incidentally, Anil Jain sir is the CEO of NIXI, National Internet Exchange of India, and this paper is also related to the subject area of DNS, which is to do with the internet. Thank you. Thank you. Thank you, sir. Thank you, sir. Thank you, Anand.
Welcome.
Yes. So now it's time to request our chief guest, Professor Debabrata Das, to give the address. Professor Debabrata Das is serving as the director of IIIT Bangalore. Before he joined IIIT Bangalore in 2002, he had served as at the GS Sanyal School of Telecommunication at IIT Kharagpur, and later at Kirana Networks in New Jersey, USA. Is the project officer of the project under National Mission for Interdisciplinary Cyber Physical Systems in the areas of advanced communication system from DST, Government of India. Is also the project investigator for a project from Tejas Networks on network node reliability. He was a project investigator of multiple DST sponsored projects and also industry sponsored projects from companies like Intel, Hewlett Packard, Microsoft, Motorola, Nokia, and also he has done his work mostly on the areas of broadband, wireless, MAC, QoS, energy saving, etc. His main areas of research interest are in the area of IoT, 5G, and wireless area networks, MAC, and QoS and power saving devices. Dr. Das has received his PhD degree from the Indian Institute of Technology, Kharagpur. He has more than 190 plus peer-reviewed papers in different transactions and journals and international conferences. He has received 6 Best Paper Awards. He has 3 US or Indian patents and 12 more are under review. He and his wireless network team had contributed ideas to the IEEE wireless broadband standard. He has received Professor K. Srinivasan Memorial Award in the year 2017 for excellent teaching in areas of telecommunication from IETE. He is also a recipient of IEEE Region 10 Outstanding Volunteer Award 2020, Global IEEE MGA Achievement Award 2012, and Outstanding Volunteer IEEE Bangalore Section Award in 2008. He is a fellow IETN as well as fellow IE and SM senior member IEEE. He was also chairman of IEEE Bangalore Section 2017, and Dr. Das is a technical steering. Is in a technical steering and empowering committee member of multiple departments in the Government of India and Government of Karnataka. Thank you, sir. We are privileged to have you here. We request you to address the gathering.
Good evening, everyone in this international conference on PKI and applications. And my sincere thanks to Dr. Sudarshan and Dr. Balaji for the invitation. I also want to thank our CCA team who has been working closely with C-DAC and MeitY for this, and medicinal secretary, Dr. Rajendra Prasad, and also want to thank CCS Mr. Arvind Kumar and Mr. Assis Banti here, and Dr. Shaundra Pandey and Mr. Saumuddin Khan, who has been attending all those meetings of this PKIs and taking India ahead in these important things. And before I go to the next step, my regards to the respected Professor Veni Madhav sir. Sir, my regards to you. And so Professor Sham Sundar here, my regards to you, sir. And also Dr. Anand Mohan, sir, he's there. He's my regards to you, Dr. Anand Mohan. And we missed you here, but your presence through virtual means a lot. And my heartfelt thanks to my IEEE Computer Society and IEEE Bangalore section, Dr. Prashant Mishra, and also Mr. Bindu Madhav, who belongs to C-DAC, but he is being the backbone and the pillar for all IEEE supports for this kind of conference. And Mr. Anil Jain from NICSI. So nice of you, sir, for coming with your busy schedule and talking to us, our participants. And thanks to C-DAC, CCA, and other dignitaries, and also attendees and speakers, as well as panelists, to make this PKI International Conference lively with discussions. It is an interesting area, and particularly the next generations which have been sitting at here, all of them has been participated with respect to the papers and also the as an attendee. And it is interesting to see the physical presence are 155 in this conference, and virtual participation is 450. It's pretty big number. A big thanks to all this organizing committee to bringing in such an important area in the conference, and let us give an applause to them. These kind of platforms with such a big numbers, one thing is clear, that this keynote speakers, two keynote speaker, I heard Dr. Jaideep Vaidya's excellent talk now, and other keynote speakers, and also the 5 invited talks and the 15 papers definitely flow the knowledge to these among themselves, and this platform brought in the discussions, and thank you for that, these organizations. And let me come to those areas which you have been dealt with in this conference. Is called PKI and IoT, PKI ecosystems, diverse applications of PKI, algorithms implementations, and security analysis and validations. And I'm sure all this learned from this panel discussions. Just now, Professor Veni Madhav sir just was leading that, and by eminent scientists who also the panelists spoke about it. It's very interesting to see the crossroad between the classical electronics-based security and the upcoming quantum, and the beautiful arguments all the panelists gave and the nice questions from the audience. This shows that, which one of the panelists was telling, that if I go back to 1960s or 50s, the electronics was at that state when people were imagining that what will happen. But if you look at now, the electronics computations and the memory and the algorithms and advent of AI, ML, and DL are changing the security world. But now the quantum is at the same stage with the qubits. And I'm sure what the panelist was telling, that 1 million of the qubits will be possible by 2025-26. Then the rest will be the history to watch for. But let me tell you, very interesting point. We are all doing the research, or the people who are doing the research, they're in one plane and one world much ahead. But the reality in the security is in a different plane, in the sense, these software developers, if you look at, they go to the open source and pick up the snippets of the softwares when they develop the products. And most of the times they don't check the security concerns with how much required to make your product more secure. So the reality of the world in the software side, which is mainly we are dealing with, of course, the hardware one, I was also listening to some of those panelists like side channel attacks and all. But the reality, but the truth is that our young generations who are all the generations, so the who are developing, the awareness of the security has to come to every one of us to make the things more secure. So in that sense, all those people I see, they pick up from the open source like GitHub and all the snippets of the softwares to build their products, has to be extremely careful and also to understand that what to be taken and what not to be taken, and before putting it, how to check that. I also think that CCA, C-DAC, and MeitY will continue this conference to build the learning to solve challenging problems in these areas of security, privacy, and leading to a trust. So thank you again, and Dr. Balaji and Dr. Sudarshan and the CCA team, and for inviting me for this conference. I have been involved in this for a long time, and I'm looking forward to continue this conference for betterment of more secure transactions. Thank you.
Thank you, sir, for motivating us and also setting targets for us. Now it's time for felicitations. Now I request Sri Ashish Banati, Deputy Controller Technology, the Controller of Certifying Authorities, to felicitate Professor Debabrata Das. Small. Now I request Sri Debabrata Das to felicitate Sri Anil Jain. Now I request Professor Shyam Sundar sir to felicitate Dr. Sudarshan. You felicitate, just do the remedies. Thank you, sir. Now I request Dr. S.D. Sudarshan, Executive Director, C-DAC Bangalore, to give the closing remarks.
Namaste and good evening. It is indeed a privilege to be in this August gathering. The dais that is now filled up here has people whom we can listen to them for next 10 years. Still it will be flowing. That is the kind of people we have, such eminent experts. So thank you, Professor, for blessing us, saying that, you know, this will continue forward. And Banati sir is here. You have said you should continue. I don't think there will be any questions on that. And Dr. Prasant Mishra has specifically said, looking at the quality, we should continue. And we heard Dr. Ananda Mohan mentioning out of 80, we have shortlisted, if you see, only 15. That shows on a very specific topic of PKI, we are getting this kind of papers, and in that further restriction in terms of selection, the quality is there. And Dr. Das specifically mentioned Bindumada sir, because IEEE Bangalore in particular has created a team to improve the quality of technical papers, how to do it, review better. So he has been leading that, and we can see the efforts bearing fruits. And then this time IEEE Computer Society along with IAS, this was a unique combination in one sense, but in another sense, it is a very mandatory combination, because anything without industrial applications, as mentioned by the chief guest, academicians versus what is in practice and the gap, it's very important. How do we address that? We already realized that we need to look at TRL 1 to 9 in a continuum rather than something that is seen in isolation. So from that perspective, this particular conference, spearheaded and guided by CCA, which is the statutory authority, they themselves coming and looking at how it should be taken forward. And as you could see from Nixie, we have the CEO himself, Sri Anil Kumar Jain here, who is actually taking into open market various technologies supported by government and industries. So the entire loop is closed. We are coexisting. And in terms of crossroads, I think both chief guest and our Professor Venimadhan, they brought beautifully how the crossroads are happening. The convergence earlier was actually lip service started, but any ideas fructify, and today we can see the coexistence of already demonstrated test beds where you use a kind of QKD, a quantum channel for key distribution, and then classical channel for high-speed data communication. So there is a place for everyone, and the conference has brought it out. The focus has been on public infrastructure, and this is something very relevant in COVID times. That was even discussed by Professor Jaydeep, how COVID hotspot and data privacy, as well as cybersecurity, they are all interrelated, how things can move forward. And the entire event, if you look at it, though the conference is for 2 days, we are fortunate to have a co-located events, a tech expo, which is started with a closed door discussions for cross-border communication across various things on 7th. And we had key people exhibiting some of the technologies. And then on 8th, we had a specific interactions among select people to see how things can reach the market in a beneficial way. And the Tech Expo continued yesterday so that all the conference participants can also get benefited. And the people who are showcasing the technologies could reach out to the community, which is combination of academic research, startups, industries, MNCs, regulators, government authorities, professional bodies like IEEE, all of them got benefited. So I have to, first of all, thank everyone for being part of this wonderful journey. All planning has no meaning if it does not fructify. Here it has fructified so nicely. Till 1 week back, we were not sure, given the rains and the kind of publicity with one sample Bengaluru becoming entire Bangalore, and as if Bangalore is become an island that is submerged in water. That is what was coming in. But the reality is quite different. And so thank you for being here 2 days. And that is an excellent thing. Let me say a few names, because success happens because of people working from behind. So we had patrons of the entire event. It started with Dr. Rajendra Kumar, Additional Secretary. He was also holding the charge of CCA last year. So last conference, he instructed that this should be technically very strong. I want peer-reviewed publications, which is internationally accepted. So that is where, not that we are not knowing each other, IEEE and CCA and MeitY along with C-DAC, this collaboration happened. So in true sense, they were the patrons, and the current CCA Arvind Kumarji, he followed it up after taking over so that there is no letup. And the Director General of C-DAC, he ensured that it is not one C-DAC Bengaluru because of location. We have other C-DACs participating in the expo, participating in the discussion today from Patna, from Noida, from Pune and other places. So the pan C-DAC presence also helped us. And the conference, I had not specifically mentioned so far, Professor Syam Sundar, veteran in various areas in theoretical computer science, all those things. He is the general chair. So he guided right from beginning, in spite of COVID, in spite of all the restrictions. He said, no, we will have a monthly meeting of all the key stakeholders, then bi-weekly meeting across sub-teams, and weekly digital update so that there is no letup. It was almost like a, in current parlance, Scrum type of activity to ensure that in spite of various things that can go right or wrong, because we never knew fourth wave will come or not, things will move or not. So he supported, guided from behind. Thank you, sir, for all the great work done. And then he came and he has been here since yesterday, full time. Day before yesterday he reached. He arrived and he had discussions both inside, outside. and he has given further ideas on several collaborations. And the general co-chair, the Mandy Friday of the conference is Dr. Prasant Misra. Still I have not learned from him, how do you manage work life and the professional activities balancing? Probably he is training his daughter with Odissi dance, how to balance, in various poses, managing in single leg, single hand. So thank you, sir, for all the full push. And yesterday, for some reason, I could not physically be there. So he was also IEEE IAS chapter yesterday. So all those things he has done. Thank you, sir. And the technical program committee, we had two stalwarts, Professor Chandrasekhan from NIT Surathkal and Dr. Ananda Mohan. They guided the technical aspects of it. The organizing committee was led by, of course, Banati sir sitting here, along with Sri Samsuddin Khan, Dr. Saundra Pandian, and Dr. Balaji from C-DAC Bangalore. Outreach, which is a very, very important activity today, getting a spot in media and reaching public in this information overload was very critical. And that was handled by Dr. Misbah from C-DAC and Prabhat Kumarji and Deepak Kumarji from CC office. They took care of it. And I think they have done definitely a wonderful job. And even now, as we talk, I'm finding continuously tweets are happening and people are liking, retweeting, and all is going on. And the entire administration and managing the funds, that was taken care of by Dr. Appaji. He is a veteran from IEEE Bangalore in general, but this time he represented Computer Society from this part. And Mr. Vinod Kumar from MeitY, Hamsuddin Khanji, and Mr. Sudhakar from C-DAC, they managed all those things. So I have to thank them. Then we had a web committee, and always issues comes with how the logos are to be organized, where it should be, what is the size, how it will look on Twitter versus on a web page. So Anup Kumarji and Bhupendra Kumarji, they managed the entire thing. We had a committee working on various facilities, starting from Ms. Divya and a complete team. In the interest of time, I'm not reading the names, but they are all from my colleagues from C-DAC Bangalore, because we're the host. And coming to the speakers, whom specifically everyone mentioned, we had Dr. Foda, who gave a talk from New York University online. And after the talk, in fact, I heard many people over lunch asked, we never knew such a professor existed, and who is speaking in this area so nicely. So some revelations happened, not that they are not existing, just that putting the spotlight to the right audience, that was important. It happened. Dr. Saxena, fellow in the office of PSA, ex-SAG director, he gave a very wonderful talk on the crypto and its evolution and how it is all the way going towards quantum-based things. So he covered an excellent thing. We had Dr. Viswas Patil from IIT Bombay. And then today morning, true to the conference where did it reach industry, we had Mr. Sukumara talking about how digital certification and PKI is actually useful to industry and how they are practicing as a global entity and a multinational company. And that was very wonderful. Again, during tea break, I saw a lot of interaction between various participants and the speaker. Dr. Jakob Nielsen from Trust Zone spoke about various technologies related to trust. And the panel just before this that we had, led by Professor Veni Madhavan, had a combination of a lot of academic, industry, and the entire gamut of world, supported by Dr. Tapas from IASC, Dr. Srikanth from Purna Pragya Institute, Dr. Basu from IIT Kanpur, Mr. Animesh from TACBIT Labs, and Mr. Prasun from Thales. So again, you can see the MSME Indian company to international companies and the IITs, they are all becoming part and parcel of the thing. And Professor Veni Madhavan has come physically all the way. So it has been a great support from him. In fact, once panel was finalized and everyone agreed, he was actually coordinating directly with them. That shows his commitment. In fact, when the RSA keys were being broken, I have attended some of his Blackboard teaching where he talks about how to see to the prime number and all. That enthusiasm has not gone down one even bit in the entire year. So thank you, sir. We had a Professor Ramesh Kari from New York University as well as Professor Jaideep Vaidya giving actual keynotes. That was wonderful. And we had a number of research papers. And because of the quality, the numbers were so limited that we did not have parallel sessions, so that there was no need to split the attention or choose between. Actually, there was no opportunity cost because everybody got 100% of their work. So that way the committee did a great job of making the program so that you attend all the talks without any compromise. And we thank all the authors for the nice presentation. The Tech Expo had Thales, eMudra, Odyssey, Versys, Precision, C-DAC, ProDigisign and Care4Sign. And we thank you for being here for 3 days with the entire stalls. And today also many of them are here, they are interacting. That is excellent to see because it's a Saturday and for industry, every minute matters and they have spent their quality time. That is one nice. And we had a cross certification and all what I mentioned. It was great to have people from abroad joining online. They are also regulatory authorities from the respective countries, Malaysia, Bangladesh, Iran, South Africa, and the European Union. They all participated. And we also had a representation from Asia Pacific PKIA Forum for that interaction. So that was very fruitful. Thank you to all of them. And various panel members, the logistics arrangements all have been wonderful. There are too many people to thank. So as we say, Paryantam they say in many of the slokas, to say that from start to beginning, I have just told a few names. That is the way it has happened. Just as a token, so that you know these people contributed. Of course, each one had a team. I will get the leaders only to get facilitated by the August gathering. So Professor Das, maybe if you can please felicitate Dr. Balaji. I'll request them to come. Yeah. So we have Dr. Misbah. Yeah. Then we. So we have Mr. Anup. So you cannot miss him anyway. So he is C-DAC Bengaluru on Twitter. Yeah. Gopinath. Where is Gopi? Yeah. And then Dr. Sanjay. So the team members actually probably will have something separately because on a Saturday you have spent already this much time and it is great to have all of you. And thank you all once again with folded hands. Namaste. Thank you. We look forward to you in the next edition and we'll continue collaborating. Thank you.
Thanks all. Thanks to all of you. Thanks for joining. Thanks. So we are closing the session now. Thanks to all our online participants and people who are watching us on YouTube Live, as well as people who have joined here. Thanks to all of you. Thanks.